Hi guys, I am Karthik Arora and I will be solving the educational DP contest. So this contest consists of 26 problems and I will be solving each of them one by one and guiding you through the solution to these problems. So in this video we'll be solving the problem A of the contest. So this is a comparatively easier problem but it is a very good problem for beginners who would like to develop a very good basic understanding of dynamic programming. So you can pause the video and go through the problem statement and then I'll explain it in my words. Alright, so the statement says that there are n stones, so you can say S1, S2 up to Sn, and there is a frog who's currently initially at the first stone, and this frog would like to reach the nth stone. So the goal for the frog is to reach the nth stone. However, there are some rules that he has to follow. So one of the rule is that he can only jump a maximum distance of 2, or his jump length is at best 2. So that means if he's at the ith stone, he could jump to the I plus 1th stone or the I plus 2th stone. Alright, and there is one more thing, that whenever this frog jumps from some stone of height hx to some stone with height hy, a cost of the difference between the absolute difference between these heights is incurred. So in this case, a cost of hy minus hx is incurred. Alright, so the goal is to find out what is the minimum possible cost in which the frog can reach from stone number 1 to the stone number n following all these rules. Alright, so if the question is not clear, we'll just go through a sample input and it will be clear then. So yeah, sample input 1. So sample input 1 says that there are 4 stones. The first has a height of 10, then 30, 40 and 20. Right, so here currently frog is here. He would like to reach S4 and okay, so initially the frog has a choice to either jump to S2 or S3. If he jumps to S3, the only choice left is to jump to S4. If he jumps to S2, then he has 2 more choices, either jump to S3 and then S4 or directly jump to S4. So out of all these possibilities, the frog should choose this one. From S1 he should jump to S2 and then to S4. In this way, a cost of, for the first jump, the cost is 30 minus 10 absolute difference plus jumping from S2 to S4, that is 20 minus 30 absolute difference, and this adds up to 20 plus 10 equal to 30. So the answer is 30. Alright, okay, we'll just go through another sample input. So okay, this is a comparatively easier sample. I'll just quickly explain this one as well. So there are 2 stones, both of the same height, 10 and 10. The frog is currently at stone number 1, and the only possible thing for him to do is to jump to stone number 2. Okay, and the cost incurred will be 10 minus 10 absolute difference equal to 0, which is the answer. Alright, so hopefully the problem statement is now clear and we'll discuss the solution to the problem. Okay, so we'll be discussing frog 1. Okay, whenever we're trying to solve a dynamic programming problem, there are 2 approaches and 2 ways or techniques to solve it. One of them is a top-down approach and the other one is a bottom-up approach. So I'll be simply discussing what are the differences between these 2 approaches. So in bottom-up approach, the code usually executes faster than the one in the top down. even for the same time complexities, the codes are usually faster here, because in the top-down version there are overhead of recursive function calls. Also, if we are able to come up with a bottom-up solution, it is usually easier to code, or the codes are much shorter. So short codes, good for contests and everything. Whereas top-down is usually more natural or intuitive. So it's more natural, especially for beginners. They'll find top-down to be more intuitive and natural compared to bottom-up. So for this problem, I'll be discussing a top-down solution, and then we'll be implementing it bottom-up. Okay, so yeah, the problem said that there are n stones and frog wanted to reach from S1 to Sn. He was at S1. Now think of it this way. The frog wants to reach Sn. What will be the final jump that the frog makes? The final jump will be either from the second last stone to the last stone, or from the third last stone to the last stone. So the final jump will be either of these two. There are just two possibilities, two ways to reach Sn. Either make the final jump from last stone to the either make the jump from the second last stone to the last stone, or from the third last stone to the last stone. There is no other possibility. So if I knew what is the minimum or the least costly way of reaching Sn minus 2, I could find out what is the least costly way of reaching Sn from Sn minus 2. And if I knew what is the least costly way of reaching Sn minus 1, I could find out what is the least costly way of reaching Sn from Sn minus 1. So in short, if I knew both the least costly way of reaching Sn minus 2 and Sn minus 1, I could probably find out the least costly way of reaching Sn. Alright, so let's just discuss it a little bit more. So let me define a term now. So I'll define dp of I. This means dp of I here represents what is the minimum cost of reaching stone number I from stone number 1. So min cost to reach stone I starting from stone number 1. Alright, of course our goal is to find out dp of n, the minimum cost to reach stone n from stone 1. Okay, so we'll try to write what dp of n is in terms of Sn minus 2 and Sn minus 1. So we observed that there are just two ways of reaching nth stone. So in this case, or let's just consider this case first, the cost incurred for jumping from second last to last is the absolute difference between their heights, and plus what is the minimum cost to reach Sn minus 1, which is dp of n minus 1. And the other way to reach the nth stone is from Sn minus 2, and in that case the jump cost will be sorry for the technical interruption. So we are considering the second case. The other way is to jump from the n minus 2th stone to the nth stone, and in that case the cost will be the absolute difference between hn minus 2 and hn, plus what is the best possible way or the least costly way to reach to n minus 2th stone. That will be simply dp of n minus 2. Alright, and we'll choose the better of these two options, and better here means minimum. Okay, so I'll recommend you guys to try and write what dp of I will be. So you can pause the video and try, otherwise I'll explain it to you. Okay, so I could reach the ith stone from the I minus 1th stone, and the cost incurred for that jump will be absolute differences between the heights, and the minimum costly way or the least costly way to the reach to the I minus 1th stone. And the other way is to reach ith stone from the I minus 2th stone. In that case, it will be the absolute differences between I minus 2th stone and the ith stone. The cost of this particular jump, cost this much, plus what is the minimum least costly way to reach to I minus 2, which is simply dp of I minus 2. Alright, so this is the recurrence and we are going to implement this recurrence. Yeah, and this should give us the answer at dp of n. Okay, so I'll be implementing this code bottom up now. Hopefully this is clear. If it is not, it will be clear once we code the solution. Okay. Alright, I'll be coding it up now. So first of all, I'll be taking the input, the number of stones n. Then we'll have a vector integer ar that represents the heights of the stones as given in the input. And I'll be making a function named solve, which will solve the problem and return me the correct answer. It will receive this vector, and I could have passed the number of stones as well, but I'll just use the size of this vector for that. Okay, so we are numbering the stones from 0 to n minus 1 now, or maybe it will be more clear if we use 1 based indexing for now. Okay, so I'll be taking 1 based indexing and my array sizes will not be n but n plus 1. Okay, so the solve function will take the inputs and return me the correct answer to the problem. I'll just pass the array and the number of stones. Okay, I'll declare a vector int dp to store the intermediate results. Of course, this will also be of length n plus 1 because we are preferring 1 based indexing here. Okay, so here is an important question. What will be dp of 1? So dp of 1 is basically the minimum cost to reach from stone 1 to stone 1. Since the frog was initially at stone 1, so there will be no cost of reaching it, and dp of 1 will therefore be 0. Okay, now I'll be calculating dp of n iteratively in a bottom up manner. So I'll calculate dp of I for I equal to 2, then dp of 2 first, then dp3, dp4 up to dp of n. So I'll be calculating from I equal to 2 up to n, and after this loop I should have my answer at dp of n. Alright, let's see what we need to write here. So we saw that, just a second. Okay, so dp of I equals to, there were two ways of reaching the ith stone, either from the I minus 1th stone or the I minus 2th stone. So we had to choose the better of these two. So better is obviously the smaller one. So this will be option 1 comma option 2. Option 1 comma option 2. Okay, so we have two options now. Integer option 1, which is simply jumping from the I minus 1th stone to the ith stone, and in that case, first of all, we'll add the cost of the jump, which is simply absolute difference between ARI and ARI minus 1, plus dp of the minimum possible cost to reach to the I minus 1th stone. Okay, and we'll have option 2 as well, and option 2 will be jumping from the I minus 2th stone to the ith stone. So the jump cost is this one plus the minimum possible cost to reach the I minus 2th stone. Alright, so dp of I is equals to min of these two options. Alright, so guys, this code should now work, except that there is one small mistake here. We say that for the ith stone there are two possibilities: either reach the ith stone from the I minus 1th stone or from the I minus 2th stone. However, for the second stone there is just one possibility, that we can reach the second stone only from the first stone. Alright, so in that case option 2 should be eliminated, right? So either I could make another if statement and do it, like if I is equals to 2, or I could simply add here if I equal to 2, then maybe the cost should be infinite because it is not possible to do it, and otherwise we'll simply let option 2 exist. So if I is equals to 2, we eliminate the possibility of an option 2. Alright, so infinite I've defined as 10 to the power 9. Okay, we'll just run the sample input 3 and check if our solution is correct. So output is 40, so hopefully this code will run. I'll just submit and I will talk about a few important things regarding this code. Okay, so here a few important things here are that first of all the space complexity and time complexity are big of n, because we have taken this n sized dp array and we have looped from 2 to n, so it's a big of n time complexity algorithm. Moreover, one more thing that I would like to discuss here is that we could have avoided taking this entire dp array, because the ith dpi only depends upon two previous states. So we could have simply kept 3 variables and we could have saved some memory here. Alright, yeah, so the code got accepted. Other than that, I used integer here because the constraints allowed me to use an integer, otherwise I would have used a long. The constraints were n up to 10 to the power 5 and heights up to 10 to the power 4. So I knew that the maximum the cost could ever go is up to 10 to the power 9. So that is why I used an integer. So guys, hopefully the lecture was helpful to you and it helped you build your basics of dynamic programming. I'll see you in the next videos. Thanks for watching. Hi guys, my name is Karthik Arora and today we'll be solving the problem B, frog 2. So the problem B is very much similar to the problem A, frog 1, and there are just minor differences. So I'd like you to go through the problem and then we'll attempt. Alright, so the problem says again that there are n stones. Just a second, I'll change the ink. Yeah, so the problem says that there are n stones and the frog is initially at stone number 1 and he would like to reach the stone number n. And in the process of doing so, whenever he jumps from some stone of height hx to hy, a cost of the absolute difference between these two heights hy and hx is incurred. And the frog here can, in the previous problem, the frog could jump at most a horizontal distance of length 2. In this problem, the frog can jump a horizontal distance of length k instead of 2. So if he is at the ith stone, he can jump up to the I plus kth stone, right? So like from the ith stone, he can go to I plus 1, I plus 2 and so on till I plus k. So if k were, let's say 2, so if k is 2, then the problem is same as the previous problem. And let's just say if k is 3 and there are say 5 stones, s1, s2, s3 and s5, s4 and s5, and if the frog is as s2, he can directly jump to s5 as k is equals to 3. So he could make a direct long jump to s5. Alright, so hopefully the problem is clear we'll just try out a sample. So the first sample input, there are 5 stones. The first has a height of 10, then we have a height of 30, 40, 50 and 20. Okay, frog is initially here. So since k is equals to 3, the frog could go from S1 to S2, S3 or S4 in the first jump. Okay, and let's say if the frog went to maybe S3, in the second jump he can jump to S4 or S5. So out of all the possibilities, the best possibility or the possibility which makes the cost minimum is when the frog jumps from S1 to S2 and then jumps from S2 directly to S5, and in that case the cost is 30 minus 10 plus the absolute difference between 20 and 30, which is 20 plus 10 equal to 30, and which is the sample output. Alright, so let's just quickly see the second sample input. Okay, so here we have 3 stones, 10, 20 and 10, and k is equals to 1. So the frog can only jump to the immediate next stone. There is no other option for the frog, so he has to jump from S1 to S2 and then to S3. There is no other possibility for the frog. Alright, in this case the cost is simply 20 minus 10 plus 10 minus 20 absolute difference, which is 20. Alright, so hopefully the problem is clear, guys. Also the problem is very much similar to the previous problem, so we'll just discuss a solution to this one. Okay, so this is frog 2. Okay, so we'll attempt this problem in a very much similar manner as we attempted problem A. Okay, so we have n stones. We want to reach the nth stone starting from the first stone. In the previous problem we saw that to reach the nth stone, the frog has to make the final jump either from the second last stone or the third last stone. So the essence was that to reach the ith stone, you had to make either a jump from Si minus 1 or Si minus 2. However, since now the horizontal jump is k, at most k, so we can land on Si even from Si minus k. Okay, so now there are k possibilities of reaching the final, basically the final jump. There are k different possible jumps to reach Sn. Alright, so we are again going to define a term called dp of I, and as in the previous problem, dp of I will represent the minimum cost to reach stone I. Okay, so we saw that dp of n will be our answer. Dp of n will be our final answer, which is the minimum cost to reach Sn. Alright, and okay, so let's try and write a recurrence for dp of I. So dp of I will be, so basically the frog will be making a final jump from some state j to the state, basically some stone j to the stone I. Alright, so the final jump will be from some stone j to some stone I. In the previous case, j was either I minus 1 or I minus 2. Okay, but here the possibilities are different. So let's say that the frog was on the jth stone and he makes a jump to the ith stone. What is the minimum possible cost for doing that? Okay, so first of all, there will be a cost incurred for jumping from stone j to stone I, which is the same as the absolute difference between the heights of the two stones, plus what was the minimum possible cost to reach to the jth stone. Okay, which is simply dp of j by definition. Okay, so but now what is j here? J, in the previous problem we know that j is either I minus 1 or I minus 2. However, j can be the values for j over here can be more. So we would like to choose the the value which results in the minimum possible cost to reach the stone I. Okay, so we would like to choose minimum over all valid values of j, over all valid values of j. So let's just see what j can be. Okay, so j can be either I minus 1, or it could be I minus 2, or it could be I minus k. Okay, so basically these are the stones from which I could directly jump to stone number I. Okay, so a recurrence will become dp of I equal to minimum hi minus hj plus dp of j, which is the minimum cost to reach the jth stone for all j starting from I minus 1 to I minus k. Alright, so all these are all the possible values, and we are choosing the best out of all the possible options available to us. Alright, so this is the recurrence which you are going to implement, and we need a base case. Okay, so what is the minimum cost to reach to stone 1, or what is dp of 1? So dp of 1 is simply 0, because the frog is initially at stone number 1 and he does not need to make any jump to reach to this stone. So with these observations, the recurrence and the base case, we can implement a solution to the problem. Okay, now I'll be opening up the IDE and we'll be coding up a bottom-up solution to this problem. Okay, so here I've just taken the input, the number of stones and the horizontal length the frog can jump, the at most how much stones he can skip, k, and then I've taken an array to store the heights of the stones. Again, I'm using one based indexing here, and again there is a function named solve which will solve the problem and return me the correct answer to the problem. So as discussed, what I'm going to do is I'm going to declare a vector dp. This will store the intermediate results. Again, this will also be of size n plus 1 because I'm using one based indexing again. dp of 1 is 0 as discussed. Now we would like to calculate the answer for the ith stone, the minimum possible cost to reach the ith stone. Okay. Alright, so we'll be calculating first dp of 2, then dp of 3 and so on, and we'll finally calculate dp of n. dp of n should be the answer, which is the minimum possible cost to reach the nth stone. Okay, now here we are supposed to evaluate all the possibilities and choose the best one out of those. So let's just say that currently our answer is, for dp of I, let's say currently dp of I equal to infinity. Okay, as and when we see that there is a better option available to us, we'll update dp of I to that. Okay, let me just write dp of I equal to infinity. Now let's say for integer j equal to I minus 1 and j is greater than equal to 0 and j minus I, and j minus I should be, or basically not j minus I but I minus j should be less than equal to k. Alright, because we can only jump from a stone that is at most k stones behind the ith stone. Also for maybe the stone I, if the k is 10 or maybe 2, we don't need to consider the 0th stone, we only need to go up to the first stone. So in fact j should be greater than equal to 1. Okay, because for any ith stone, we could, the leftmost stone from which we could jump to the ith stone is stone number 1. Alright, and j minus minus. We're basically considering all the possibilities, and we'll update dp of I equal to whichever is better, either the current answer or the new possibility. The new possibility is simply jumping from the jth stone to the ith stone, and that jump will cost us AR of I minus AR of j, the absolute difference between these two values, plus whatever is the minimum possible cost or the minimum cost to reach the jth stone. Okay, so it looks alright to me. Yeah, so let's just try a sample input and then we'll discuss the time complexities and stuff. Okay, let me just try a harder sample case. Okay, so the answer should be 40. Alright, so it's giving the correct answer. I'll just try and submit. Okay, so this should most probably get an AC verdict. Till then I'll just discuss the time complexities with you. So here again the memory occupied is big O of n, and as discussed in the previous problem, the memory could be big O of k instead of big O of n, but I choose to take big O of n memory here. And time complexity for this is interesting. Okay, so first of all we are looping from 2 to n, and every time we are looping from I to all the states, all the k states behind, the immediate k states behind I. So for every state we need to look at k other states. So basically the transition time is big O of k and the number of states is big O of n. So overall complexity will be big O of n into k. Okay, so the solution got an AC. Here you can see that n was up to 10 to the power 5 and k was up to 100. So 10 to the power 7 operations is very much doable in 1 or 2 seconds. So I guess so I hope the video was helpful to you, and I'll see you in the next video. Thank you. Hi guys, my name is Karthik Arora, and today we'll be discussing the problem C, that is vacation. Alright, so this is a very interesting problem, I would say. It's a nice problem, and you could expect similar dynamic programming problems in your interviews as well at product-based companies. So you can go through the problem statement and then I'll explain it to you in my words. Okay, so there's a boy whose vacations are about to begin, and there will be n days in his vacations, and n can be up to 10 to the power 5. On each day he can choose to do one of the 3 activities. He could either choose to swim, catch bugs, or do his homework, right? And each of the activity on a particular day has some associated happiness points. All right, so if we are talking about the ith day of the vacation, swimming has, or activity A has some happiness points AI, catching bugs or activity B has some happiness points BI, and doing his homework has some associated points CI. All right, so interestingly all these are positive. Cool. So yeah, on the ith day he could choose to do either of these. However, the only catch is that if he chooses to do some particular activity on day I, then at day I plus 1 he cannot choose the same activity again. So basically on 2 consecutive days the activities should not be same, otherwise he will get bored. So this has to be avoided, right? So if he does his homework on a particular day, the next day and the previous day should not be spent doing homework, right? So we'll go through, and yeah, and what we need to find is that we need to find the maximum possible happiness that can be obtained by doing the activities in a particular order, so that the maximum happiness that he gains throughout the vacation is maximized. Alright, we'll just go through the sample input and we'll try to solve it. Okay, so you can see the input format. So firstly we have n, the number of days in the vacation. Then we have A1, B1, C1. This represents what is the happiness that you get by doing activity A on day number 1. So n is the number of days. This is A1 is what is the happiness that you will get by doing activity A on day 1. What is the happiness you will get by doing the activity B on day 1 is B1, and similarly C1. So AI, BI and CI represents what is the happiness you will get by doing these particular orders A, B, C respective, these particular activities A, B, C respectively on the ith day, right? So let's consider the sample input 1. So there are 3 days. So let's say D1, D2 and D3. And the activities are A, B and C. By doing activity A on day 1 I gain 10 points, doing it on day 2 I gain 20 points, and doing it on day 3 I gain 30 points, right? For B also we have 40, 50 and 60. C 70, 80 and 90. Okay, so if the constraint wasn't there, we can clearly see that we could have done activity C on day 1 and again C on day 2 and again C on day 3 and gained a total of 70 plus 80 plus 90 happiness points, which is 170, 240. Alright. However, you cannot do the same activity on 2 consecutive days, so the answer is not 240. Alright. So the answer instead is we can do activity C on day 1, then we can switch to doing activity B and we can do activity C again. And in that case, our answer will be 70 plus 50 plus 90, which is 210 as in the sample output, right? So hopefully the sample input 1 is clear. We'll discuss the sample input 2 as well. So the sample input 1 says that there is just 1 day of vacations and activity A gives you 100 happiness points, activity B gives you 10 happiness points and C gives you 1 happiness points. So obviously you will choose to do activity A and get 100 points. Alright. So okay, you can go through the sample input 3 if you wish to, and then we'll discuss the solution to the problem. Alright. So we're solving problem C, vacation. Just a second. Yeah. Okay. So first of all, let's think of brute force solution to this problem. Okay. So one of the first thing that might come to anyone's mind is that, okay, let's just try out all the possible ways to do the activities on the n days, right? And we'll choose the best possible valid way of doing activity, and whatever the maximum score we get out of those activities, we'll choose the best possible answer. So basically we'll consider all the possible ways of doing activities throughout the n days, right? So at the first day you have 3 possible options. You could do any of those activities. On the second day you will have 2 possible options because you can do any 2 activities other than the activity you did on day 1. Again you'll have 2 options, and on the nth day as well you have 2 options, right? So if you think of evaluating all the possibilities and choosing the best possibility, the time complexity for that will be exponential, right? Because the number of valid ways to do all the activities throughout the n days is 3 into 2 into 2 so on till into 2, which is 3 into 2 to the power n minus 1, right? And n is up to 10 to the power 5, right? So obviously this solution will time out and this is not feasible. So let's think of a better dynamic programming solution to the problem, right? Okay, so think of it this way. So on the nth day, the boy can either do activity A, B or C. Even in the best possible answer, on the nth day, one of these activities will be done, right? So let's try to find out what is the best possible answer if the boy does activity A on the nth day, right? So we'll try to find out what is the best possible answer if boy does activity A on day n. Also, we'll try to find out what is the best possible answer if the boy does activity B on day n, right? And similarly, we'll also find out what is the best possible or the maximum possible happiness that we can obtain if the boy does activity B, C on day n, right? So our final answer will be one of the best of these three, right? So basically best here is maximum. We'll like to have maximize the happiness. So our answer will be maximum of these three possibilities, right? So now we need to think how can we find out the maximum of these, basically how we can find out these things 1, 2 and 3, right? Okay. So we were thinking about the answer for all the days from 1 to n, right? Now if we think that we will do the activity A on day n, now we have to think about the first n minus 1 days, right? So if I did, let's try to solve for one. I did activity A on day n, right? Now we are trying to find the best possible answer for all the days from 1 to n, and given that I am doing activity A on day n, right? So I'll be gaining an points for doing activity A on the nth day. However, I can no longer do activity A on day n minus 1, right? So now I would like to find out what is the maximum happiness I could obtain if basically for the first n minus 1 days, given that I could do either activity B or C on the n minus 1th day. Okay, try to understand this. So this will be 1 an plus best possible answer given that I do not do activity A on day n minus 1, right? Alright, so let's just define a few terms before we go towards the solution. Alright. So let's say dp of n. dp of n here represents the best possible answer for the first n days. So this is basically what we would like to find out. dp of n is what is the maximum possible happiness that the boy can achieve in the vacations. I define dp of n0 as the maximum possible happiness that the boy can achieve in the first n days, given that he does the activity A on day n, right? So I'll write the definition: maximum possible happiness for days 1 to n, given that boy does the activity A on day n. Boy does activity A on day n, right? Similarly, let's define dp of n0, n1. This is the maximum possible happiness for all the days from 1 to n, given that the boy does activity B on day n, right? And similarly, I'll define dp of n2. So this is basically the maximum possible happiness that the boy can achieve for all the n days from 1 to n, given that he does the activity C on the nth day, right? Now we'll try to relate these states with each other and come up with a possible solution to the problem. So I'll be erasing this now. Yeah. Okay. So we have thought of dp n0, dp n1 and dp n2. So if we were able to find out all these three things, our final answer will be maximum of all these, right? So our final answer will be maximum of these three possibilities, because there is no other possibility the boy has to do one of these activities on the nth day, and we're considering all these possibilities then, and our answer will then be the best of these three options, right? However, now how do we find out what is dp of n0, n1 and n2? Okay, so let's try to write the recurrence or a transition relation for dp n0. So dp of n0, okay, so this means that I did the activity A on the nth day. So first of all, my happiness increases by an because I am doing activity A. Also, now I am left with the first n minus 1 days, right? And I would also obviously want that the happiness again for those n minus 1 days is also maximized. However, I am not allowed to do activity 0 on day n minus 1, right? So I could either do activity 1 or 2 on day n minus 1. Okay, so what if I do activity 1 on day n minus 1? For that, the maximum happiness achievable is by definition dp of n minus 1 at 1, doing activity B on day n minus 1. And similarly, I could choose to do activity C on day n minus 1, and in that case the maximum possible happiness achievable is dp n minus 1 2. So this becomes maximum of either do activity B on day n minus 1 or do activity C on day n minus 1, right? Okay, now let's try to write recurrence for dp n1 and dp n2. Okay, similarly dp of n1 will be, I am doing activity B, so that gives me bn points, plus maximum of, for the n minus 1th day I cannot do the activity B, so it will be dp n minus 1. I could do A input, and I could also do activity C, right? So hopefully these recurrences are clear to you, and now we'll try to write a generic recurrence. Okay, so with these observations, a recurrence will become dp of I. What is the maximum possible happiness that I can achieve in the first I days, given that I do the activity J on the ith day, right? And J can be 1, 0, and J can be 0, 1 or 2, right? So dpij will simply be whatever is J. If J is 0, then we'll have AI points, then otherwise J is 1, we'll have BI points, and so on. So let me just make it dp0 for now, dpi0, and it will be AI points for doing the activity A, plus maximum of, since I cannot do the activity A on the I minus 1th day now, so it will be either I do activity B or I do activity C, and whichever yields a better result for the first I minus 1 days, I'll use that and add AI to it to get dpi0. So hopefully the recurrence is now clear. We can write similar recurrences for dpi1 and dpi2 as well. And finally, I'd like to discuss a base case with you, right? So if there is just 1 day, maybe we could also think of 0 days, but let's just say if there is only 1 day, so it will be dp of 1, and there's just 1 day, and on the first day I do activity 0. This will simply be A1 because I'm doing that activity on that day and I'm getting the happiness points for doing it. Also dp of 1, 1 will be B1, and dp of 1, 2 will be C1. Okay, so with these base cases and the recurrences, we have now come up with a solution to the problem, and I'll just implement this in the IDE. So if it's not clear with the implementation, it will be more clear now. Okay, So let's just go to the IDE now. Okay, so here I've just defined a structure activity that is A, B and C, and it's just storing the happiness points. A represents the happiness points for activity A, B represents for B and C for C. Again, I have a solve function which I'm going to implement right now. I've just taken the input, the number of days n, and the happiness on each of those days. I'll be calling solve to solve the problem and get the answer, right? So here I do not need to pass this k. Okay, so as we discussed, we have a two-dimensional DP here. I'll be declaring a DP array. Let's just say integer DP, and it will be n plus 1 because I'm using 1 based indexing again, and we can have this as 3, right, because we need DPI0, DPI1, DPI2, right, and we had a base case for DP of 1, right? So DP of 1 at 0 is simply going to be AR at 0 dot A, and DP1 1 and DP1 2 are similar and are the base cases, right? Now I'll be doing a bottom-up implementation, and I'll be iteratively calculating DP of I, j for all the valid values, right? Finally, my answer will be maximum of DP at n 0, max of DP of n 1, again, DP n and 2. Alright, so hopefully this is clear. I'll just evaluate using the recurrence. I'm gonna evaluate all the valid values for DPIJ. So for integer I goes from 2 less than equal to n and I plus plus. So as we discussed, if I do activity A on the ith day, I'm going to gain AR at I dot A points, plus I could choose to do either activity B or C on the previous day. So DP of I minus 1 or just a second, or DP of I minus 1 2, that is I could either do the activity B or C on the previous day because I am doing activity A on the current day, right? So this is DPI0. Similarly, I'll write recurrences for DPI1 and DPI2. So DPI1 will simply be I'm doing activity B on the ith day, so I'll add the happiness points I get from doing it, and on the I minus 1th day I have to avoid doing this activity, so I could either do activity A, which is represented by this, or I could choose to do activity C represented by this. Similarly, I'll write DPI2 equal to, so I'm doing activity C on the ith day, I'll get the happiness points for doing it, plus I cannot do the activity C on the I minus 1th day, but I can either do the 0th activity A or B, and I'll choose the better of these two options, right? So hopefully, I guess the code is now done. We'll just try a sample input here. Okay, let's just try the sample input 3. The answer should be 46. Okay, so there's some small error, I guess. Let me just quickly check what's the problem. Alright, so we're returning this, and okay, DP of 10, DP of 11. This looks alright. Here we have used okay. Alright, so yeah, there's one small mistake we did in the base case, that is, since it's a 1 based indexing, I had to use AR at 1 instead of AR at 0, so it's alright. Let me just check again. So it's now giving 46. Yeah, that was the expected output. Let me just try and submit it. So hopefully this will get an AC. Till then I'll just discuss the time complexity and space complexity with you. So just use this structure for a better representation of my vector instead of using 3 vectors. Here this DP array will consume big O of n memory because it's simply n into 3 sized array. Therefore the memory consumed is big O of n. 3n is simply big O of n. Also time complexity will also be big O of n since I'm simply looping from 2 to n. Alright, so space and memory complexity are clear. And here I've used this integer because the happiness points were at most 10 to the power 4 and there were at most n days. So even if he got 10 to the power 4 happiness each day, even then our maximum possible happiness is 10 to the power 9. So I chose to use integer instead of a long. Alright, so let's just check. So yeah, it got an AC. So guys, hopefully this video was helpful to you for understanding basic dynamic programming. And I'll see you in the next video. Thank you. Hi guys, I'm Karthik Arula, and in this video we'll be solving the problem D, that is knapsack 1. So this is a classic dynamic programming problem, and if you'd like you can go through the problem and then I'll explain the problem statement. Okay, so the problem states that there are n items, alright, and n can be up to 100. So there are n items, I1, I2 up to in, and each item has an associated weight and value, right? Wn and Vn, right? So there are n items and each item has an associated weight and a value, right? And we also have a knapsack, right? So we have a knapsack that can accommodate at most a weight of W, right? So if I pick some of these items from some of these items, right, then the sum of their weight should be at most W. The sum should not exceed the capacity of the knapsack. So the constraints are n is up to 100. The capacity of the bag is up to 10 to the power 5 and the values can be up to 10 to the power 9, right? So we'll just check a sample input and understand the problem better. So yeah, you can check the input format. First we are given the number of items n. Then we are given the weight of the knapsack, that is basically the capacity of the knapsack, W. And then we are given the weights and the values of all the items, right? So here's the sample input 1. And it says that there are 3 items. So there are 3 items and item 1 has a weight of 3 units. And the value associated with this item is 30. Item 2 has a weight of 4 and the value associated is 50. Item 3 has weight 5 and value associated with it is 60. So we would like the capacity of our knapsack W is 8. So what we would like is we would like to choose some of these items, basically a subset of these items, such that the sum of their weights is at most 8 and the value is as much as possible. So we would like to maximize the value we take home in our knapsack, right? Okay, so in this case I could either choose 30 and 50 and this item and this item, and my total weight becomes 3 plus 4, which is 7, which is less than equal to 8, and my value becomes 50 plus 30, that is 80. Alright, and one more possibility is that I could choose this item and this item. In this case my weight becomes 3 plus 5, which is equals to 8, so less than equal to 8 is followed, and overall value becomes 30 plus 60, which is 90, and which is the correct output. One thing to note here is that I cannot pick this item and this item together because the weight will exceed the capacity of the knapsack. Alright, so let's also try the sample input 2 before we move on to the solution. So in this case there are 5 items and each item has a weight 1, and the value is, I guess, 10 to the power maybe 6, 8 or 9, and it is possible to take all the items because overall weight will still be less than equal to 5. Alright, so we'll take all the items. Also, thing to note here is that the answer may not fit in a 32-bit integer, so we'll use long, right? Okay, so we'll just leave sample input 3 for now and move on to the solution. If you'd like, you can go through it once on your own. Okay. So we're discussing the problem E knapsack, and let's discuss a brute force solution first. So basically what we are supposed to do is we are supposed to choose a subset of the items out of the n items, right? So the number of subsets of a set is 2 to the power n, right? One possible solution to the knapsack problem is to take all the subsets and then check if the currently taken subset fits into the knapsack. If it does, check the value we get from that subset, and then among all the possible subsets, whichever gives the maximum possible value, we'll choose that as our answer. So basically choose a subset, check if this fits into the knapsack, and if it does, then what value does it produce. So among all the possible subsets, we're going to select the best subset, and since there are 2 to the power n subsets, and for each subset we'll have to check whether it fits or not, the time complexity will be big O of n into 2 to the power n, and n is up to 100, so this is not feasible, right? Okay, so we'll move on to a better solution. I'll be discussing 2 ways to approach this problem using a DP approach, and then finally I'll be implementing it in a bottom-up manner. Okay, so now we have just a second. Okay, so now we have n items, I1, I2 up to in. Okay, and we would like to basically, let's say we have the first n items and we could choose a subset of these items so that the value is maximized and the weight is at most W, right? So let me just define my problem as this: dp of n comma W, right? This means this represents the definition of dp n comma W is what is the maximum possible value that can be obtained if I take a subset of the first n items such that the capacity of the knapsack is W. So subset of items from 1 to n and capacity is W. Okay, so let's think. Now let us think about the nth item. Okay, I could either take the nth item or choose to leave it. If I take the nth item, then I will get a value of Vn. However, I will lose a capacity of Wn. Okay, so there are 2 possibilities. One of them is I take the nth item, and the other is I do not take the nth item, right? So let's see what happens in both of these cases. Okay, so if I do not take the nth item, I'm left with a subset of items from, basically I'm left with the first n minus 1 items, and I could choose a subset of these items only, and I'm left with a capacity of W. However, if I do take this value, then I'm left with the first n minus 1 items and a capacity of W minus Wn, but I now have a value of Vn added to my bag, right? So we'll try to write a recurrence. Basically, we'll try to define dp of n comma w into smaller sub problems of the similar type. I'll just erase this and then we'll see how it works. Okay, so let's say we have dp n comma w, that is the first n items and a capacity of capital W, right? Now we had two options. Option one was I leave the nth item, I do not take it. In that case, my answer will be the same as that for n minus 1 comma w, because no value is added to my bag and no capacity is lost, except that now I can no longer choose the nth item. Okay, and the other possibility was I get a value of Vn and I lose a capacity of Wn and I'm left with the first n minus 1 items, right? So this way we have broken down a recurrence into two smaller sub problems, and we can choose which the better of these two options. So I'll just choose the maximum of these two, right? This is one way to approach this problem, and this is absolutely correct. We can approach it top down. I could write a recursive code to this problem. We could think of a simple base case as well. So this is one way, and I'll be discussing another way, but let's just finish this way first. So let us discuss what could be a suitable base case for this. So if I'm left with no items, in that case, so basically if I'm left with no items, that is dp of 0 comma anything is simply 0, because since I have no item to select, I cannot gain any value. And maybe another base case could be also we'll have to maintain capital W. This has to remain greater than equal to 0 at all times. So yeah, this could work as a nice base case, and then we could simply implement this top down. Alright, so I would also like to discuss another approach to this problem, and we'll be implementing that one and that too in a bottom up manner. I'll just erase this now. Okay, so let's define dp of I comma w, and this time this means that I could select a subset of items from the first I items such that basically what is the maximum possible value if I select a subset of the items from the first I items such that the sum of the selected items is exactly W, right? Exactly small w. So basically in this definition, dp of I comma w will be that I have selected some items that give me the maximum possible value and their sum of weights is exactly w. Okay, so this is my dp, and now let's try to break it down into some smaller sub problems and see how it works out. Okay, so again we'll have a similar approach to break it down into smaller sub problems. So for the ith item, I could either choose it or I could either leave it. There are just two possibilities, and we'll use the one that gives us a better result. So choosing this item gives us vi score, and we are left with I minus 1 items, and now their sum should be w minus wi, right? Because the total sum of the selected items has to be small w, and since the ith item's weight was wi, so the remaining items should sum up to exactly w minus wi, right? And in the other way, we could simply choose to leave the ith item, and then we're left with the first I minus 1 items, and their sum of weights should sum up exactly to w, and we'll choose whichever of this is better. Alright, our final answer will simply be whichever of this is higher. So dp of n, I have the first n items and x, their sum could be anywhere from 0 less than equal to x less than equal to capital W, because the selected items weight is x, their weight is at least 0 and at most capital W, because otherwise if it is greater than W then we exceed the capacity of the knapsack. So we'll simply select whichever of these is the highest. For all x from 0 to W, we'll choose the maximum one, right? So this is one thing, and again we'll discuss base case. So base case here could simply be dp of 1 comma x is 0 if okay, so we have only one item and we would like its weight to be exactly x. So what is the maximum possible value I could gain by choosing a subset of the first one items such that their weight sums up to exactly x, right? So again, for one item, if I choose it, the weight will definitely be wi. So if x is not wi, so there is no way of choosing a subset of the items from the first item itself so that the sum of weights sums up to x, and otherwise dp of 1 comma x is v1 if x is equals to wi. So hopefully this base case and the recurrence is clear to you. Now I'll be implementing this in code and we'll see how it goes through. Hopefully after the code the solution will be even more clear to you. I'll be implementing it bottom up. Okay, now I'll just erase this out and we'll go to the IDE. Hi, so now I'll be implementing the code for the solution we discussed in the previous video. So alright, there is a structure item here and I've made a structure. This basically holds the weight and the value of the item. This is the main function. This is simply taking the input. So this is an integer n and w. N is the number of items, w is the capacity of the knapsack. Again, I've taken array to hold the values and the weights, basically to hold the items, and again I'm using 1 based indexing, so the size of the array is n plus 1. Here I've simply taken the input and I've called the solve function. This will return me the answer to the problem, right? Okay, so here as we discussed, I'll be declaring a dp array of a two-dimensional array. So first dimension was representing the what items, the first I item, so it is n plus 1. Then the second dimension was representing the capacity of the knapsack, and that's it, right? Alright, so we discussed a base case that for the first item we said that dp of 1 for any value other than the weight of this item will be 0. So and dp1 at the weight of this value at the weight of this item will be the value of this item. So ar at 1 dot wt equal to ar at 1 dot val, right? Okay, other than this all values will be 0 here. So for every value other than this should be 0. So I guess I should simply write this code above it. For every value from, basically for every weight value from 0 to w less than equal to capital W, w plus plus, and dp at 1 comma w is 0, and then here we'll overwrite for the weight of this item, we'll assign it the value of that item. Alright, so base case is clear now. We'll simply be implementing it bottom up now. So for every first I items I equal to 2 to I less than equal to n, we'll be calculating what is the best possible answer for a particular weight. Okay, I select the first I items and now I think that I say that the weight of or the sum of weights of the selected items should be exactly WT, right? So WT goes from, or small w in fact, right? W goes from 0 to capital W, W plus plus, right? So we discussed there were two possibilities. Either I take this item or I do not take this item. So let's say if I do take this item, then it becomes I do not take. Let's just first say I do not take this item. Then that one is the simpler case. This simply reduces to dp of I minus 1 comma w, right? And the other cases in which I do take this, in that case I'll be adding the value here plus I'll be left with the first I minus 1 elements and a capacity of W and capacity of capital W, sorry, small w minus the weight of this particular item, right? Yeah. So that's all right now. Also, my dp of I comma w will be the higher of these two values. So maximum of what it is right now, or if I take the item, then what it is. Alright, so now my answer should be available at basically the highest of dp of I comma x, where x goes from 0 to capital W. So maybe I could simply use max element dp at n dot begin, in fact I'll just say dp of n comma dp of n plus capital W plus 1, right? So the maximum element here should be my final answer. Just one thing to note here is that if the capacity was less than the weight of the current item here, I couldn't have chosen the item, right? So I'll just add a if condition here. If the weight of current item which I'm thinking about taking is greater than the available capacity, then simply continue, right? Because there's no way I could take this item, right? So hopefully this should give me the correct output. We'll try a sample input and see. Okay, let's try sample input 3. Answer should be 17. Okay, this is a small error, I guess. LLSolve does not name a type. Alright, actually I haven't added the header I usually use, right? Okay. So small errors, I guess. Max element. Oh, just a second. Yeah, sorry for this. I'll just include the required headers. So this bits slash std C++ contains all the necessary functions and data structures that you'll need while programming for any competitive programming contest. Okay, so we're getting the correct answer. I'll just try and submit if it gets an AC verdict. Until then, we'll discuss the time complexity and the space complexities. So first of all, here we are using a dp n cross w. So obviously the space complexity will be number of items into the maximum possible capacity of the knapsack, that is n into w, and here the number of states is n into w. And so this loop will run n times, this loop will run w times. So the overall complexity is going to be n into w, as the transition time here is big O of 1. Finally, this operation works in big O of w as well, max element. So overall our time and space complexity is simply n into w, right? So hopefully this is clear. Okay, so the solution is getting a w here. I'll just quickly check what's the problem here. So basically for this this particular sample input, I'm getting the incorrect answer. So yeah, the reason for this is that we were supposed to use longs here, and there was an integer overflow. So these are important things to take care of while in a programming contest. Let's just try and submit again, and hopefully this time it will work. Yeah, alright, so it worked. So guys, thanks for watching, and I'll see you in the next video. Hopefully this was helpful to you. Thanks, bye. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem E, that is knapsack 2. So the problem D and E are identical, other than the only difference in D and E is the constraints. So yeah, the difference in the constraints is that in problem D, W was up to 10 to the power 5. However, W here is up to 10 to the power 9. Okay. So why we cannot use the same solution as we used in D is because the solution we had come up, just a second. Yeah. So because the solution that we had come up was big of n into w time complexity, right? And there w was up to 10 to the power 5. So we were doing proportional to 10 to the power 7 operations, which is very much doable in the time limit. However, for the exactly same problem statement, if we use our code which we used previously, in this case w is up to 10 to the power 9, and we'll be doing a total of 10 to the power 9 into 100, that is 10 to the power 11 operations, right? And that will definitely time out for in 2 seconds. Yeah, it will time out. So we need to think of a better solution, or maybe a different approach to the same problem, right? So here, one thing that we might be able to use to our advantage is that the values of the items, the value of an individual item is in the range 1 to 1000. So at most, in value of any individual item can be at most 1000. Okay, so maybe we can use this to our advantage. I'll ask you to try and think of a different DP approach to the same problem, and then we'll discuss it together. Alright, so I'll quickly move to the solution, and we'll skip the sample input output for this one because the problem statement is similar to D. Okay, so we are solving problem E knapsack 2. Yeah, so first of all, I'll give you a hint to how we can think of a solution to this problem, and then we'll move on to the actual solution, right? So what I'll recommend you guys to think, I would like you to think in this way. If I would like to select a subset of the first n items that has the sum of the values of the selected items exactly v, what is the minimum possible weight in which I can do it? Okay, so I'll just rephrase it. I have the items from 1 to n. I select a subset of these items, such that the sum of values is exactly v. Then what is the minimum weight of basically the sum of the weights of these selected items? So basic idea is, what is the minimum weight in which I could get a value v? Okay, so try to think of it in this way. Alright, so let's move on towards the solution. So imagine I define a term. Okay, I'll just define a term for now. dp of I comma v. Here I represents that I am selecting a subset from the first I items. So basically I'm given with the items from 1 to I, and I wish to select a subset of these items such that the sum of the values of the selected items is exactly small v. Then dp of iv represents the minimum weight, the minimum sum of weights of selected items, so that sum of values of selected items is v. Okay, so how can this be helpful? Let's say if we are able to evaluate dp of n comma 1, basically if we are able to evaluate dp of n comma x for all possible valid values of x, think can we reach the solution if we know dp of nx for all valid x? We'll just erase this and we'll try to write a recurrence and see how this may help to solve the problem. Okay, so let's say I knew dp n comma x. Okay, then if I know that dp of n comma 1 is some value, maybe let's say w1, dp n comma 2 is some value w2, and so on till w max, right? So dp of n comma max is some w max, right? Then I'll find some value, basically let's say if vi is a value so that dp of n comma vi is less than equal to the capacity of the knapsack, then vi is a feasible value. Basically it is possible to get vi as our solution. So I'll simply choose the greatest x among all the valid x, where dp of nx is less than equal to w. So choose the greatest x so that dp nx is less than equal to w, and this way we can get our answer, right? So hopefully this is clear to you. Now we'll simply see how we can actually write a recurrence for this and calculate our answer. Okay, so now we'll try to write a recurrence. Let's see dpiv. So as we discussed in the previous problem, I'll be thinking about the ith item. Since we are thinking about the first I items, I'll think either I can take the ith item or I can choose to leave it. In the case that I do take the ith item, or let's say I leave it for the easier case first. So if I leave it, then I'm left with I minus 1 items, and the sum of their values must be v. Okay, however, if I choose it, then one thing that happens is a weight wi is added to basically a weight wi gets added to dp of I comma v, since this item is being put into the knapsack. So the minimum dpiv was representing the minimum possible weight for selecting some items so that their value sums up to small v, and since I've taken an item whose weight is wi, so definitely the knapsack already has a weight of wi now, right? Okay, and I would like to add the minimum possible weight in which I could select a subset of items whose values sum up to v minus vi. Since I just took an item whose value was vi, now the remaining items that I'll be selecting from the first I minus 1 items need to have their sum of values equal to small v minus vi. Okay, so hopefully these recurrences are clear to you, and once we have this recurrence, we can think of implementing the solution given that we know of a base case. Okay, so let's think of a base case now. So what could be a valid, useful base case here? So what will be dp of 1 comma x? Okay, so if x is equal to the weight of the first item, then not weight but maybe value. So if x is equals to the value of the first item, then I could get this value by choosing the first item, and in that case the minimum possible weight of my knapsack will be w1, right? So w1 if x is equals to v1. What if x is not equal to v1? So if x is not equal to v1, there is no possible way in which I could basically gain a value of x, no matter what capacity of knapsack I use. It is impossible for me to basically select exactly x value if x is not equal to v1. Okay, so dp of 1 comma x in that case could be maybe infinity, because it's impossible to do that other than dp of 1 comma 0, because there is a way to get a value of 0 by not selecting the first item, and in that case the minimum value of the knapsack I need is 0 because no weight is added. Okay, so hopefully these base cases are clear to you, and now we'll move on towards the implementation. I'll simply be implementing this bottom up using the recurrence and the base cases. Okay, so now I'll be erasing it and we'll implement the code. So here I've simply written the code to take the input, and I've made a structure item just as in D, and this is the solve function which will be returning me the answer, right? So here I've taken the input, and then let's implement solve as discussed, right? Okay, so first of all we'll declare a dp array to store intermediate results. This should be of size n plus 1 because first dimension was the I in the first dimension represents, I am thinking about the first I items, right? So it's n plus 1. Now this second dimension can be up to the maximum possible value that I could achieve, that is some max val. So here the maximum value possible to gain is the number of items into, let's say, 1000, because according to the constraints the maximum value an individual item can have is 1000. So the maximum possible value for me to gain is by selecting all the items, and all the items have their values as 1000, so n into 1000. Alright, so I'll now be implementing it bottom up, and we'll be calculating the intermediate values iteratively. Alright, first we should also define the base cases. So as we discussed, the base cases will be infinity for basically for dp1x. All the base cases will be infinity other than when x is equals to 0, because in that case I could choose to leave the first item and the weight of my knapsack is 0. And the case in which x is equals to the weight of this first item, x is equals to the value of this item, because then it is possible to gain this value by having a knapsack of the capacity at least the weight of the first item. Alright, so I'll simply first of all declare all these values as infinity. So for val from 0 to max val, dp over 1 val, let's declare it infinity. I'll just define what infinity is. Since the maximum possible weight of the knapsack is 10 to the power 9, I'll define my infinity as 10 to the power 9 plus 1. Alright, so I've defined infinity as 10 power 9 plus 1. Now the other base cases, that is dp1 0 is simply 0, and dp of 1 at the value of this item, since it's possible to get this value by choosing a subset of the first one items, the minimum possible weight to do so is the weight of the first item. Alright, so let's calculate all the values iteratively. So integer I equal to 2, I am choosing the first I items and thinking about taking a subset of these first I items. So I want the value, the sum of these values of the selected subset of these first I items to be exactly V. Now we'll be writing the two recurrences. So first of all, I may choose not to take the ith item. In that case, my dpiv will simply be dp of I minus 1 v. Since I did not choose this item, I have the first I minus 1 items to choose from, and their sum of values should be exactly equal to v. Okay, now the second thing is I may choose this item. So I can only choose this item if the v is the overall value that I need to get. Alright, and if the value of this particular item is greater than the value I really need, I cannot choose this one item. Okay, so if array at I dot val, the value of this item is greater than the value I require to choose or to get, then I cannot really take this item and I'll simply continue. Otherwise, the second possible option is that I take this item in the way, in this option, when I take the item, I need the knapsack to be of at least the capacity of the weight of this item, since this has to be added, and dp of I minus 1 comma v minus the value of this item, since the remaining items should sum up to v minus the value of the ith item. Alright, also it might be possible that not choosing this item is a better option. In that case, I'll choose the better of these two options, and better here means smaller, as we are looking at the minimum possible capacity to get value v. Alright, so after this we said we'll choose the largest x among all possible valid x such that dp nx is less than equal to the capacity of a knapsack. So here for every x from 0 to x less than equal to Maxwell x plus plus, if dp at nx is less than or equal to the capacity of a knapsack, that is capital W, I'll just declare a variable answer here. Okay, I'll just take this array to also be LL. Yeah, so if dpnx is less than equal to W, my answer is equals to X. Alright, so this answer can definitely be integer here, as the maximum value itself is integer and we're returning a value, and I'll return the answer. Alright, so this return type should also be integer. So this should hopefully work. We'll try out a sample input. The answer for this input should be 17. Okay, there's some error. Val was not declared. Okay. This is line. Yeah, alright, so since this is V, okay. Okay, I guess there's some issue here. Okay, so since it is timing out, so maybe some of my loop variable. Yeah, alright, so I haven't incremented this, and now it should probably work. Let's just check the answer now. Alright, so I'm getting the correct output. Let's just try and submit. Till then, I'll just discuss the time complexities with you guys. So yeah, first of all, Maxwell. Here Maxwell is n into the maximum possible value for an individual item. Let's say maximum possible value for an individual item is V. Right. So Maxwell is simply n into V, and our table size is n into V. So space complexity is n squared V. Our transition time as well was big O of 1. So overall time complexity will also be n square V. One thing I'd like to discuss here is that we could have done it in a better complexity than n square V. We could have done it in the space complexity only, not the time one. We could have done it in time, space complexity big O of n into V. How? Since any dp of iv only depends upon the previous state, right? It only depended upon dp of I minus 1 comma something. So we just need to keep two states, right? Basically two vectors. One vector of Maxwell, which represents the current I am trying to calculate, and one vector for the previous I minus 1, which for the results that I'll need to use to calculate this particular I, right? In this process, I'll be able to eliminate this dimension. I'll just keep two vectors, okay? Right. So I choose not to implement this only because this is a little bit more implementation heavy, and here our focus is on learning how to implement dynamic programming properly. Also, this will pass, this solution will pass, right? Okay, let's just check. So yeah, it's getting an AC. So hopefully guys, the video was helpful to you and you learned another problem. Thanks for watching. Hi guys, I am Karthik Arora, and in this video we'll be solving the problem F, that is LCS. Alright, so you can go through the problem statement. So this is a very commonly known problem and it is a standard dynamic programming problem. However, we are asked a variation of this problem. Usually in the LCS problem we are asked to find out the length of the longest common subsequence of two strings. In this problem we are asked to find out the longest common subsequence itself, right? So let's just go through the sample input. Yeah, so we have the first sample input. We have the two strings AXYB and ABYXB. So the output for this is AX and B, or it could also be AYB, right? So the answer should either be, our output should either be AXB or AYB. Alright, cool. In the second input we have AA and XAYAZ, and our output should be the AA, alright, because the longest common subsequence here is AA. Okay, sample input 3 is A and Z and the output is an empty string. Cool. Alright, so let's move towards the solutions. Okay. So we're solving problem F, that is LCS. Okay, we're given with two strings S1 and S2. Let's say it's C1, it's a collection of basically characters. C1, C2 up to Cn. Let's say the length of string 1 is n. Similarly, S2 is C1, not C1 maybe. So let's say S2 is some other collection of characters. So S1, S2, S3 and so on till Sm. So length of S2 is m, right? So normally to solve the LCS problem we have to find the length of the longest common subsequence. However, here we are supposed to find out the longest common subsequence itself, right? Okay, so first I'd like you to solve the simpler version. Okay, let's just solve the problem that we need to find out the length of the longest common subsequence. Okay, so find the length of LCS. This is the problem we will first target, and then we'll see how we can use the results of finding the length of LCS to actually find the LCS itself, right? Okay. So, to find the length of the LCS, let's say we are considering the strings S1 and S2. Okay. So, what happens if C1 and S1 are equal? So, if C1 and S1 are equal, our longest common subsequence is definitely at least 1, right? C1 equals to S1. Then our longest common subsequence is at least length 1, and we're left with the substrings or suffixes C2 to Cn and S2 to Sm. And if we could find the LCS of these two, C2 to Cn and S2 to Sm, the length of that, then our final answer will be 1 plus the length of LCS for remaining substrings or remaining suffixes, right? But this is the case when C1 and S1 are equal, alright, but it is also possible that they are not equal. So if C1 and S1 are not equal, then we can be sure of one thing, that either C1 does not participate in the longest common subsequence or S1 does not participate in the longest common subsequence. Okay, so think about it and then I'll prove you how it is correct. Okay, I'll prove the correctness to you. So I'm saying that the strings are C1 to Cn and S1 to Sm, and I'm saying that if C1 and S1 are equal, then our answer reduces to 1 plus length of basically LCS of C2 to Cn comma S2 to Sm. So this is very much obvious, because we are getting 1 in our length and we're left with the remaining prefixes. So whatever is the longest length of the longest common subsequences for these two, we'll simply add that to 1. But this was the case when C1 was equal to S1. Now I said that, okay, if C1 is not equal to S1, I claim that either C1 does not participate in the longest common subsequence or S1 does not participate in the longest common subsequence, meaning that only one of these will participate now. Okay, so imagine that in our LCS C1 participates and S1 also participates. Okay, let's take the contradictory case that C1 participates in our LCS and so does S1. So if that happens, then C1 is not equal to S1, right? Then C1 will be equal to some other character of S, maybe let's say Si. So C1 and S1 would have matched with each other and our LCS would start with C1, right? Okay, because C1 is the first character of C, so our LCS has to start with C1 because C1 matched with some character of S and it is a part of LCS. However, since S1 is also a part of our LCS, so S1 must have matched with some CJ. And since S1 is the first character of the string S, then S1 and S1 also participates in being the LCS, then definitely S1 should be the first character of LCS. But this is the contradiction that C1 and S1 both cannot be the first starting character of our longest common subsequence, and therefore in our answer only one of these will participate. Alright, so with this we can conclude that if these two are not equal, our answer will be either the longest common subsequence of C1 C2 Cn comma S2 to Sm or the length of the longest common subsequence of C2 to Cn and S2 to S1, S2 to Sm, right? So definitely we'll be choosing the one which yields a better result, right? So we'll be choosing the max of these two. So with this we can come up with recurrences. I'll just define dpij. This is the length of longest common subsequence, or just LCS. So this is the length of the LCS for strings ci, ci plus 1, so until cn, and sj, sj plus 1, so until sm, right? So dpij is defined as this. Alright, and now we'll write recurrences. So consider dpij. So if si, or basically ci, so if ci equals to sj, in that case dpij becomes 1 plus dp of I plus 1 comma j plus 1, right? Because as we discussed, these two characters match and these two will be included in our LCS, and now we just need to find the length of the LCS for the remaining two strings, and in the other case our answer will be the better of the two. Either I choose that C1 can no longer participate, basically Ci can no longer participate in the LCS, and that is dp of I plus 1 comma j, or I choose that okay, sj can no longer participate in being the LCS. In that case it is dp of I comma j plus 1, right? So yeah, we have a recurrence. Now we just need to find a simple base case and we can go towards the implementation of finding the length of the LCS. However, we still need to discuss how to find the LCS. Okay. So first of all, let's just think of some base case. So if one of the two strings is an empty string, then the LCS is definitely 0, because LCS of empty string comma any other string is 0. Okay. So let's just say that our base case can be if I is greater than n, or if j is greater than m, then answer will be 0 in that case, right? Because that represents an empty string. Okay. So now we know how to find the length of the longest common substring. We know how to find length of LCS. We just need to see how do we find out the actual LCS, okay? So let's say that, yeah, initially we had complete strings from 1 to n and 1 to m. Basically we had the complete strings C1 to Cn and S1 to Sm. Now let's say if C1 and S1 were equal, then they will definitely form a part of the LCS. So I'll do LCS dot append C1, right? Because C1 and S1 are equal and I just need to find what is the LCS of the remaining two strings, right? Okay. And in the other case, right, when C1 and S1 are not equal, then I am left with two strings, and one of the strings is C2 to Cn. Basically then I am left with two options, right? One of the options is to remove C1 and find the LCS of these two things, and the other option is to remove S1 and find the LCS of these two things, right? So whichever of these is better, I'll go to that option, isn't it? So if now, since I've already calculated the length of the LCS, I know what dp of 2 comma 1 is and what dp of 1 comma 2 is, right? So whichever is better, I'll go to those substrings and I'll keep repeating this process till I have enough characters in my LCS so that the length of the string LCS is actually equal to len of LCS, which we found out using our algorithm. Okay, so once we implement this idea will be even more clear. Let's move on towards the implementation. Okay, now I'll be removing this and we'll be implementing this code. Here I've just added some code for the input and stuff. I'll be explaining it quickly. Here I've taken the input string s and t. Solve should solve the answer problem and return me the answer to the problem. This should be a string because our answer will be a string. Alright, this will help me find out the length of the LCS given two strings s and t, and I and j simply represents what part of the string we are looking at currently. So basically the suffix I is the point from where string s begins and we have to take till the end, and j is the part from where the string t begins and till the end I'll take the suffix. Okay, again string get LCS will be the part which will help me to get the LCS. We'll see how it works. Alright, so I'll also be passing it the length of the LCS. Okay, so we have string solve LCS. First let's find the length of the LCS, which is len LCS. I'll pass string s and t. Initially I am looking at complete strings. I wish to find the LCS of complete strings, so I pass I and j as 0 because this is from where I have to consider the string s and t from the 0th index till the last index. So with this I'll get the length of the LCS, then I'll return get LCS with this length, and this should solve the problem. Okay, and I'll be implementing length LCS in a top-down manner this time. I'll explain how top-down codes work. First of all, I'll be declaring a global array, although this is not a very necessary thing to do, but I find it easier. So I'll be declaring a global array integer dp, and this will be max length, max plus 1 and max plus 1. Here max represents the maximum possible length for string s and or t. So let's just say max is 3000, I guess, in the problem statement. Yeah, so it's up to 3000. Okay, so hash define max 3000. Alright, okay, one more thing. So yeah, here's the thing, how top-down codes work. I'll give a brief introduction to that. So here is how a top-down code works. So a top-down code is something like this. You have a solve function. You have some input variables or parameters p1, p2 and so on till pn, which define a sub-problem to be solved, right? Then at the top of the solve function, you check if this is a base case, if this sub-problem can directly be solved. And if it is a base case, you solve it and return the answer for this base case. Next, you check if this sub-problem was seen before this, or have I seen this sub-problem before and I know the result. So if the sub-problem is seen before, or if dp of these parameters is already calculated. Okay, so if it is already calculated, we do not calculate it and return the answer. Otherwise, we call our recurrences to solve the problem. So this is how a top-down code will usually look. So for beginners, they can see how it will usually work. Right, and now we'll be implementing our code top-down. Okay, so here to check dp is calculated or not, we need a special value that indicates that it is not yet calculated. In this case, I'll be taking dpij equal to -1, indicating that it is not yet calculated. Okay, so since initially no value has been calculated, so I'll initialize the dp array to -1. So mem set dp -1 size of p. Alright, so this initializes the dp array to all values -1. So as I said, first we check for a base case. Base cases were if I is greater than s dot length, in fact equal to, since we are using zero based indexing, or j is greater than equal to t dot length. Alright, in that case our answer was simply 0 because one of the strings is empty. So this is, we checked, first of all we checked if it is a base case or not. Next we check if this problem, if sub problem is already solved or not. So if this sub problem was solved earlier, then it would not be -1. So if it is already calculated, then return the answer. Great. Next is, if it is not solved earlier by us, then we'll solve it this time and we'll be implementing a recurrence, right? So here we have two options. Option number 1 is, in fact we don't have two options, there is just one option. There's just one option, and that is if si and tj are equal. If si is equals to tj, then in that case our answer will be 1 plus len LCS of s comma t comma I plus 1 comma j plus 1, right? And in the other case, when these two are not equal, now we have two options. Either our answer will be len LCS of st I and j plus 1, or it will be I plus 1 and j. Basically one of the character will be excluded from our LCS. That is what this represents, right? So whichever of these two is higher, will return that. Great. One more thing that I didn't mention is that after doing this calculation and calculating everything, we should store it for future uses, right? So I'll be storing it before returning, so that if next time same subproblem reappears, we already have the solution to this subproblem. So alright, length LCS is now done. Okay, we just need to write this get LCS function now. Okay, so I'll declare a string LCS here. Initially it's empty. Now I have two integers I and j. I indicates what part of string s I am currently looking at, and j indicates what part of string t I am currently looking at. So I'll also need string s and string t, of course. Yeah, I am passing these by reference, and I'll explain it to you later on why this is necessary, especially in the len LCS function. So initially I'm looking at the entire string, so I and j are 0. Now let's say while I have not got all the characters that I need, so while length is greater than 0, so every time I get a valid character, I'll decrease this length. Let's say len represents the required len LCS must reach. So first of all, if s at I and t at j are equal, if that is the case, first of all I'll be doing lcs.pushback, because I found a valid character to be added to my LCS s at I. Other than that, I'll be incrementing I and j. Also, I'll be decrementing len, the number of required characters. Okay. And in the other case, this is a little interesting case now. So else which one should I increment, I or j? This depends upon what gives us a better result. Is dp of I plus 1 j a better thing, or is dp of I j plus 1 a better result? Okay, so if dp of I j plus 1, this basically means that if incrementing j gives me a better result, I'll increment j, otherwise I'll increment I. Okay, so dp of ij plus 1 is greater than dp of I plus 1 j, then increment j and don't touch I, else increment I. Alright, so and at the end of this code I'll return my LCS. So now this should work. Let's just try a sample input and we'll see. Okay, we'll try this one. So there's some problem here. Yeah, I should also pass s and t. The answer should be okay. Alright, so we're getting the correct answer. I'll just try to submit this. So yeah, hopefully this should work. Till then we'll just discuss the time complexities. So the the number of states here is 3000 cross 3000, or the length of the two strings squared. So the time space complexity is simply big O of n squared, and the transition time here is also big O of 1, so time complexity is also big O of n square, right? Okay, so I'll just check if it got an AC verdict. Yeah, so it passed. So guys, hopefully this was a helpful video to you. One more thing that I would like to discuss here is that passing these strings by reference to the function len LCS was very much important, because otherwise every time len LCS is called, string s and t will get copied because we are passing it by value, and that copying will be very costly because the strings are of length n and each time we'll be making a big O of n copy, and in that case our solution's time complexity will degrade to big O of n cube, right? Because every len LCS call will be a big O of n time call, because there is a copy process going on, and the transition time becomes from big O of 1 to big O of n. Alright, so I hope it was a helpful video to you guys. I'll see you in the next video. Thanks for watching. Hi guys, I'm Karthik Arora, and in this video we'll be solving the problem G, that is longest path, right? Okay, so this problem states that we are given with a graph G, and the graph has n vertices and m edges. Okay, now the problem is asking us to find the length of the longest path in the graph. Okay, and one thing to note here is that the graph G does not have any directed cycles. So since G is a directed graph and there are no directed cycles in the graph, this means it is a directed acyclic graph, right? Okay. Also this means that we will not encounter any graph that has a cycle. Okay, so this is not a valid input for this problem. Okay, so let's go through the sample inputs and the problem will be clear to you. Okay, so first of all you can see the input format here. First of all, we are given the number of vertices in the graph, then we are given the number of edges, and then we are given m x1 comma xi comma yi pairs. Here xi comma yi represents that there is an edge from xi to yi. So basically there is an edge from node xi to node yi. Okay, so let's look at some sample inputs now. So in the sample input 1, we are given this graph and the answer is 3. This is because the longest path starts at the node number 1 and ends at node number 4. So there are 3 edges in this path, 1, 2 and 3. Therefore our output is 3, the length of the longest path. Alright. So sample input 2 is also very much clear. Here we can see that the longest path starts at node number 4 and ends at node number 6 and has a length of 2. Alright. So let's just look at sample input 3 also. So here also it is quite clear that the longest path is starting at node number 5 and ending at node number 3. And since there are 3 edges in this path, so we have to output 3. Alright, so guys, hopefully the problem statement is clear to you. We just have to find the length of the longest path in the directed acyclic graph. And we need to output this length, not the path, just the length of the path. Okay, so let's move towards the solution now. So we are solving G longest path. Just a second. Yeah, so here the observation will be that the longest path in the graph starts at some particular vertex. Alright, so let's say let's just number the vertices of the graph from 1 to n, right? So either the longest path starts from node number 1 or 2 or so on till n. Okay, so if I knew the longest path that starts at node number 1, the length of the longest path which starts at node number 1, and I knew the length of the longest path that starts at node number 2, 3 and so on till n, I could basically compare all these values, and whichever of these values is the largest one, that is going to be my answer, right? So this is quite a straightforward observation, that because our path has to start at some vertex, so if we knew the length of the longest path starting at each and every vertex, we could simply compare and choose the maximum out of all these, right? So with this observation, I'll define a term, dp of u, as the length of the longest path that starts at node u. Alright, so once I have dp of u for all u from, let's say, 1 to n, I will choose that dp of u which is the largest, right? Okay, but now again the point is, how do we calculate dp of u? Alright, so let's think of it this way now. So I have a node u, okay, and I want to calculate the longest path that starts at this particular node. So imagine the case in which there is no directed edges coming out of this node, right? There's no directed edge coming out of this node, and in that case any path that starts at u has to end at u, because it is a directed graph and no edges going out from you, right? So its out degree is 0, and in that case the longest path starting at node u is simply 0, because the number of edges in this path is 0 and the path is simply u. Okay, now think of this. We have a node u and there are some number of nodes, let's say v1, v2 and so on till node number vn. So there are n nodes, not n, let me just take some other node symbol for this. Let's just call it x. So there are some x number of nodes from which there's a directed edge from u to them. Okay, so Now my longest path that starts at node number u is at least 1, right? Because there is some neighbors to which we can go from u. Alright, so it is at least 1. So dp of u is at least 1 and plus something. Okay. Now what is the length of the longest path that starts at node v1? It is dp of v1, right? And again for v2 it is dp of v2, and for vx it is dp of v of x, right? So I'll be going from node number u to that node from where the length of the longest path is maximum out of v1, v2 and vx, and I'll be choosing that one, right? So here we'll choose the maximum of all the children or all the nodes from that can be visited from node number u. Alright, just a second. Yeah, okay. So I'll be choosing the maximum. Basically I'll write a recurrence and try to see if you understand it. Okay, so as we discussed, we have a node u and there are some outward edges from u. We said that in this case dp of u will be at least 1, because yeah, one edge is definitely there. We can go to some of its children. Actually we could traverse one of these edges and reach some children, but which child should we go to? That will be maximum over all the children of u, or basically let's just say child here means that there is an edge from node u to v. Okay, so max dpv, so that there exists a edge from u to v. Alright, so guys, hopefully the solution is quite clear to you. It was quite a simple solution, given that if there is no out degree then dp of u is simply 0. In this case I cannot go anywhere. Alright, there was no outward edge, there were only inward edges, so the longest path that starts at node u is simply 0, because there's no way to go anywhere else. And if there are some paths to which we can go from starting from node u, then my answer will be 1 plus whichever of this places give me the highest length of the longest path. Okay, so let's say from this guy I have a length of longest path maybe 5, and at this guy I have a length of longest path maybe 3. Here let's say I have it 0. So if I would have gone here, if I would have gone this way to this child, then my answer would have become 1 plus 3, right? If I would have gone here, my answer would be 1 plus 5, and if I choose this child, my answer will be 1 plus 0. So obviously I'll choose the maximum of these and my answer will be 6. Okay, so I'll just show you the same thing on a sample input, and then it will be very much clear to you guys. Let's take a sample input. So maybe let's just go for this graph. If it is still not clear, you should watch how I solve for this graph, and it will be clear to you, right? Okay, so there's an edge from 1 to 2, 1 to 3, 3 to 4, 2 to 4. All right. I guess this was the graph. I'll just check again. Yeah, right. Okay, so here dp of 4 is the longest path that starts at node number 4, which is 0. Okay, and dp of let's say 2, dp of 2 is simply 1 plus dp of 4, which is 1. Then we have dp of 3, and that will be 1 plus max of dp2 comma dp4, and the higher of these two is dp of 2, which is 1, so it will be 2, and finally dp of 1 equal to 1 plus max of dp2 comma dp3, right? And it will be 1 plus the max of dp2 and dp3 is 2, and we get our final answer as 3 because the highest of dp1, dp2, dp3 and dp4 is 3. So my final answer is 3. Alright, so guys, hopefully now the solution is clear to you and we can move towards the implementation. Alright, so again I'll just explain you the input and the template that I've written here. So here I've taken this vector integer graph. This will be used to store my graph, and let's say graph at I represents the ith node, and the vector represents all the neighbors of the ith node. Alright, integer dp here simply represents the values which we discussed, the length of the longest path starting at some particular node. So dpu dpi equal to length of longest path starting at node I. This function will take a node and it will calculate dp at source. Okay, solve will take a node to calculate dp source. Alright, again we have, here I've simply declared dp to be -1, indicating that this particular value is not yet calculated. And again here I've taken the input, the edges u and v, and for every edge graph at u dot pushback v, this represents that there's a directed edge from node u to node v. Here I've declared the answer to be 0, and I'll be calling solve I to get dp of I, and whichever of these is the highest, that will be my answer, and I'll print it here. Okay, so we now just have to implement this solve function. So as we saw that if let's say if we already have the answer for src, in that case src will not be -1. That means we have already calculated the answer for this particular node. Then I'll be returning the calculated answer. Okay, and otherwise I'll be calculating the answer for this node. So as discussed, the answer for it will be, first of all I need to check if there is any child of this particular node. So let's just say, alright, so bool leaf. So basically if there is no child for this node, I'm just calling it a leaf node. I'm saying that it is a leaf node, and for every child of this node, for every child of graph at src, okay, so if there's any child, first of all this is not a leaf, so I'll declare that leaf is 0, and then I'll be asking what is the length of the longest path starting at this child. So I'll be calling solve of child. Okay, and this will return me some value. Let's just store it somewhere. So integer best child maybe. So best child is simply the child to which we should go from here. Okay, so that is cool now. So return, see, if it were a leaf then the answer will be 0. So if this was a leaf, then length of the longest path starting here is simply 0 as we discussed. Otherwise it is 1 plus best child. Alright, and while returning I'll be storing my answer, so that next time if someone asks me what is the length of the longest path starting at this node, I'll simply return dp of src. Alright, so according to me this code should not work. We'll just take a sample input. So the answer for this is 3. Okay, so we're getting the correct answer. I'll just submit and we'll see if it works. Okay, moreover, let's just consider this time and space complexities. So first of all, this loop is big O of n, because basically this loop runs n times, and the solve function. So here for every child I'm looking at all of its for every node I'm looking at all of its children, right? So let's say if some node has k1 outward edges, some other node has k2 outward edges, overall it will be summation ki through all of the nodes. This loop will run summation ki times, and this will be equal to the number of edges in the graph. So overall my algorithm is big O of n plus m, right? Okay, so hopefully this will be clear to you. And the space complexity here is simply big O of n, the number of nodes, because I'm declaring a DP array of size n. Alright, okay. So yeah, it got an AC. So guys, hopefully the problem was helpful to you. I'll see you in the next video. Thanks for watching. Hi everyone, my name is Karthik Arora, and in this video we'll be solving the problem H, that is grade 1. Alright, so you can go through the problem statement and then I'll explain it to you in my words. So we're given a grid of size H cross W, so there are H rows in the grid and W columns. Okay, some of the cells of this grid are blocked, okay? So this means that we cannot move through this particular blocked cell, right? So what we need to do is we need to find the number of paths that start at 1, 1 and end at H, W. Okay, so starting from the top left, we would like to reach the bottom right, and we want to find the number of paths, the number of different paths which exist that go from 1, 1 or the top left to the bottom right. Okay, also that from any cell I, j, I could either move right or downwards. So basically, if I'm at this cell, I could either go to this cell or this cell. There is no other way. Also, since the number of paths can be very large, extremely large, we have to find the number of paths modulo 10 to the power 9 plus 7. Alright, so let's just look at some sample inputs and then we'll move towards the solution. So here we have the input format. First we are given the dimensions of the grid and then the grid itself. Okay, so let's look at the first example. Alright, so we're given a grid of size 3 cross 4 represented in this figure, and they say that there are 3 paths and they have highlighted the paths. Okay, so it's quite obvious and we can clearly see the 3 paths, so the answer is 3. Yeah, so one thing to keep in mind is the constraint of moving only towards right or down. There's no other way, you cannot move up or left, so you have to go right and down. Okay, cool. Then we have this 5 cross 2 grid, and here the number of possible paths to reach from top left to bottom right is 0. Why is it so? Because let's say I go down, then I cannot move down from the initial cell because there is a blockage. Just a second. Yeah, so I cannot move from here to down since it is blocked. I'm forced to move to the rightward cell, and then I'm forced to move downward because there is a wall to the left. Again we have a blockage here and I'll reach here. Now it is not possible to move left. We are only allowed to make right and down moves, and here right is also blocked and down is also blocked, so the number of paths from top left to bottom right are 0. Alright, so guys, hopefully the sample inputs are clear to you. We can just see the sample input 3 as well. Okay, so we'll see it later. If you would like, you can validate it for yourself how the answer is 24. Okay, so guys, let's move towards the solution, and we have to print the answer modulo 10 to the power 9 plus 7. Okay, so solving H grid. Just a second. So I would recommend you guys to pause the video and think for the solution, and then I'll help you out. Okay, so guys, we're given a grid, and some of the places contain, some of the cells of this grid contain an obstacle to which we cannot move. We're allowed to move to either the right cell or the down cell from any particular cell. Okay, and we would wish to reach cell n comma m. So basically my problem is to find number of ways starting from 1 comma 1 and ending at n comma m, and I'm taking n as the number of rows and m as the number of columns. Okay, so let's think of it this way. What is the number of paths that let's say start at this cell and end at this cell? So let's say if it were a 1 cross 2 grid, so what is the number of paths starting at 1 comma 1 and ending at 1 comma 2? It is simply 1, right? Because there is just one way you go right, there is no other way. So here we can see in this grid as also the number of paths that start at this particular cell and end at this cell is 1, isn't it? Because the only path is going towards the right. Okay, also think of this thing. How many paths that start here and end at n comma m? Again, we have only one option, and the option is to move downwards, and then so we have a total of 1 paths. Okay, now think for, let's say, okay, first we'll try to think of this cell. Again, here there is only one path, and that is go down, and then you reach n comma m. There is no other possibility. Rightward cells are already blocked, so this will also be 1. Again, similarly, this will also be 1, right? Okay, now let's say there were some obstacles as well. Let's try to find what is the answer for this cell. I'll just draw the enlarged version of this 4 bottom right cells. Okay, so we knew that the number of paths that start at this cell and end at n comma m is 1. Here also the number of paths starting at here and ending n comma m is 1. Now what is the number of paths that start at this cell and end at n comma m? So basically, so any paths that start from this cell, I could either go right or down. So any paths that start from the cell to the right and reach n into m, let's say there was some path p that was starting at this cell, let's call it p1, some path p1, which can start at this cell and reach n into m. Okay, and there are some paths, there is some path p2 that start at this cell and end here. Then we can be sure that all these paths can also be achieved from this cell, right? Because if I move right, then we can follow p1 to reach n into m, right? And if I move down, then I can follow the steps followed by p2 to reach n comma m, and that way I can reach n comma m. So let's make it more concrete now, hopefully getting the intuition behind the solution. So basically, if I had a very large grid, and let's say I was thinking about what is the number of paths that start at this particular node and end at n comma m. Okay, so from this node I knew that I can either go right or I can either go down. So if there existed some path that started at this node and ended at n into m, then definitely from this cell also the same path can be used, except we can prefix it with a right move and then the same path p1. Okay, so if there exists 100 paths that start from this particular cell, there are 100 paths that start at this cell, then all these paths can also be used by our particular, let's call this cell, just a second, I'll number it so that it's more clear to you. So this is 1, 2, 3 and 4. Similarly 1, 2, 3, 4, 5, 6 and 7. So any from 2, 3, we're trying to find the number of paths from 2, 3 to n, m or 4, 7. And let's say I already know the number of paths that start from 2 to 4 and end at 4,7 is, let's say, some x. So since there are x paths that start at 2,4 and end at 4,7, I know that all these x paths, if I start from 2,3, I can go right, and I then can follow any of these x paths to reach 4,7. So one thing is for sure, that all these x paths can be used by 2,3 to reach to n, m. So we have a x, alright, and let's say the number of paths that start from the down cell, that is 3,3 is y, and reach n 4,7 is y. So I can prefix all these paths with a downward move, and then use the path used by 3,3 to reach 4,7. So all these y paths can also be used by 2,3, right? So in that way, the total number of paths that start at 2,3 and end at 4,7 become x plus y. Okay, so now I'll try and write a recurrence for this. Okay, so we're thinking about the number of paths that start at the cell I, j, and we already know, basically let's just define dpij as the number of paths that start at cell I, j. So number of paths starting at cell I, j and ending at, just a second, and ending at cell n, m. So as we saw that dp of ij can be written in terms of dp of basically the number of paths starting at the cell I, j can be written in terms of the number of paths that start at the right and the down cell, right? So if both of these cells are unblocked, right and downward cell, dp of ij will simply be dp of I plus 1, j, because I can make a downward move, and then any path that was starting from the cell that is exactly down to ij can be used by I, j to reach n, m. Alright. Also, I could have made a rightward move, and in that case any path that had started from cell I, j plus 1 could be used by cell I, j by first making a right move and then following the same path followed by I, j plus 1 to reach n, m. So dp of ij will become this in that case. Okay, so if one of these cells is blocked, okay, either the right cell or down cell is blocked, then the number of paths is simply 0, right? Okay, and if ij itself is blocked, and in that case dp of ij is 0 if grid at ij is blocked. Okay, so we'll simply perform this algorithm on a sample input, and then we'll go towards implementing the code. So if it's the recurrence is not yet properly clear to you, once I explain the input, it will definitely be clear to you. Okay, so let's just take a small input and try our approach. Okay, let's try this on 5,5, right? I'll just make this grid quickly and we'll see how it works. 1, 2, 3, 4 and 5, right? 1, 2, 3, 4 and 5. Just a second, I think the grid is a little larger. Sorry. Alright, so we have an obstacle here, then we have an obstacle here, and here. Okay, so as we discussed, the number of paths that start at this node and end here is 1. Even the number of paths that start at this particular node and end here itself is 1, and that is an empty path. Here again it is 1. Here it will be the number of paths that start here plus the number of paths that start here, that is 2. Alright, again here it will be 2 because downward here the answer is 0 and 0 plus 2 is 2. Here it will be again 0 because only one path exists to the right and that is an obstacle. Here also it will be a 0. Here it will be 2 plus 0, that is 2. And here again it will be, just a second. Alright, yeah, 2 because I could start from here and I could follow either this one path and reach here, or I could follow this path till here and do this and reach here. So 2 right. Okay. Again this will be 2, then again 2 plus 2 4, again here this will be 6. I'll quickly fill this array. This will be 0 0 0, and this will be 2 plus 0, that's 2. This will be 6 12. Again this will also be 12, then this will also be 12, and overall this will be 12 plus 12 24, which is the correct answer. So guys, hopefully the recurrence was clear to you, and now we can go towards the implementation. So I have again written the sample input, the sample code. Okay, so here I've taken the input. N and M is the number of rows and the columns in the grid. I've declared the grid globally, and then I've taken the grid input here, and solve n comma n should return me the result. Okay, so I'll implement this bottom up. So first of all, let me just declare a vector or maybe integer dp or dp array. And this will be n plus 1 comma m plus 1. Alright, now let me just, yeah, so dp of n comma m will simply be 1 because the number of paths to reach from n comma m is 1. Alright, and I hope I can assume that this cell will not be blocked. Actually moving right or down, find the number of moves. Okay, so I'm assuming that this path cannot be blocked. We'll see if okay, yeah, so 1 comma 1 and h comma w are empty squares, so yeah, it cannot be blocked. So dp n comma m is simply 1 because the number of paths to reach from the last cell to itself is an empty is just one path, that is an empty path, and so dp n m is 1, the number of paths. Okay, now I'll do this. For integer I equal to, I'll first calculate for the bottom row. I stays greater than equal to 1 and I minus minus. Again I will select the rightmost column first. So for integer j equal to m, and j stays greater than equal to 1, j minus minus. So first of all, if there is if this particular cell is blocked, so if the cell is blocked, how will I know if it is blocked? Grid at ij will be a hash symbol. Yeah, okay, also this should be char. So if this particular cell is blocked, then simply dpij is nothing but 0. Okay, otherwise my answer at this particular point will be okay, as we discussed in the recurrence, my answer here will be dp of I comma j equals to, either I can go right downwards. In that case my answer is dp of I plus 1 comma j plus, if I go rightward, then dp of I comma j plus 1 will be added to my answer. Okay, also I need to make sure that if this is the rightmost if this is the bottom row cell, then definitely I cannot go downwards. In that case I just have to check, is this the bottom cell? So if I is equals to n, there is no way to go down, and in that case this term is 0, otherwise use this term. Okay, similarly, if this is the rightmost column in which I'm currently standing, that is if j is equals to m, then there is no way to go right, and in that case this will be 0, otherwise use dp of ij plus 1. So guys, I guess this should be clear to you. And okay, so after this I should be returning dp of 1 comma 1, and I assume that this should give me the correct answer. Just one thing here. Firstly, dp of n comma m will be seen, and there is no right or downward cell, so I just need to make sure that if I equals to, basically if this is the bottom right cell, in that case I should not be doing anything, right? So if n equals to m, n, and j equals to m, in that case simply continue. Alright, so I guess this code should work. We'll try out a sample input. One thing I forgot to do is to take the answer modulo. Alright, so there's some problem in the code. I'll quickly go through and check. Okay, so it's nice to see how to solve when you're stuck. Okay, so dp of nm was 1. I went from, alright, this was okay. J starts from m, and dp nm will be skipped if j is n and j is n. If this particular point, okay, yeah, so I forgot this else. I'll run it again and see. So I'm getting the correct output here. Just one last thing I'll do is take the modulo here. Moreover, I'll also like to take the dp array as long, just to avoid any possible case of overflow. So I'll just declare this long. This can be integer because finally I'll be returning an integer. The only reason why I made this a long is because I could have made an integer overflow here. Okay. No, I don't think I can. So yeah, integer will be fine because these values are already under 10 to the power 9 plus 7, and 2 times 10 to the power 9, 7 will be less than the maximum possible value for an integer. So this will be alright. I'll just check one more sample input and then we'll submit. So the answer for this case should be okay. I'll just check. Yeah, we're getting the correct answer. I'll submit and we'll discuss the time and space complexities. Okay, so first of all, the space complexity is the grid size n into m. Okay, and again, time complexity is also same as the grid size because the transition time is again big O of 1. Transition time is basically the number of states any given state depends upon. So the state depends upon only 2 states. So every state in fact depends upon only 2 other states. So transition time is big O of 1, and overall time complexity is big O of the n into m, the grid size. So alright, I got an ACE. So guys, hopefully the video was helpful to you, and I'll see you in the next video. Thanks for watching. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem I, that is coins. So the problem statement says that we have n coins and n is a positive odd integer. Okay, and what we need to find out is that given these n coins, we have tossed all the n coins. What is the probability of getting more heads than tails? Okay, however, these coins are not normal coins, these are biased coins. And the ith coin has a probability of getting a heads. If you toss the ith coin, there's a probability pi of getting a heads. Okay, so these are not normal coins, these are biased coins. Alright, so all we need to find out is what is the probability that once we have tossed all these n coins, what is the probability of seeing more heads turned up than the number of tails that turn up. Okay, so let's look at a sample input and the problem should then be clear to you. Okay, So we're given in this input 3 coins, and the first coin has a probability of 0.3 to come head when it is tossed, second has 0.6 and third has 0.8. We need to find out the probability of getting more heads than tails, right? So the output for this is 0.62, and let's see how it is 0.612. Output is 0.612. Alright, so in this case the favorable outcomes will be either I get 2 heads and 1 tail, then I'll have more heads than a tail, or I get 3 heads and 0 tails. So these will be the favorable outcomes. Alright, so this for 3 heads and 0 tails there is just one possible combination. Okay, it's HHH. I get heads on all the 3 coins, and the probability of this will be 0.3 into 0.6 into 0.8. Alright, so 0.3 into 0.6 into 0.8. Alright, whatever it is, we'll calculate that. Then for 2 heads and 1 tails there are, let's see how many possibilities. I could get a head, head, tail, or I could get maybe a head, tail and a head, or I could get a tail, head, head. Okay, so the probability for this case will be getting a tail head on the first coin is 0.3, then 0.6, and then getting a tail on the third coin is 1 minus 0.8, which is 0.2. Alright, similarly we can write probability for these two cases. Let's call them P2, P3, call it P1 and P4. So 0.612 will be P1 plus P2 plus P3 plus P4. So therefore the sample output is 0.612, and hopefully the problem statement is now clear to you. You can also refer the explanation that AdCoder has provided. Yeah, so the explanation is just the same. They have added all the probabilities of these favorable outcomes, and therefore the answer is 0.612. So guys, hopefully the problem statement is now clear, and if you'd like you can go through other sample inputs as well. I'll just move towards the solution now. Alright, so we are solving I coins, right? So according to the problem statement we have n coins, and the probability of getting a head for the first coin when it is tossed is P1, similarly P2 and up to Pn, right? We would like to find out what is the probability of getting at least n plus 1 by 2 heads, that is number of heads should be greater than the number of tails. So let's say if n is 5, then we need at least 3 tails, right? Because 5 plus 1 by 2 equals to 3, right? So yeah, just a second. So we need n plus 1 by 2 heads, at least n plus 1 by 2 heads. So we'll try and keep this solution simple as possible. Okay, so think of it this way. I have the first n coins and I would like to get at least x heads. Okay, then while tossing the nth coin, there are two things that may happen. One is I might get a head with a probability of Pn, and the other case is that I might get a tail with a probability of 1 minus Pn. Alright, so in the case I get a head, I would like to find out what is the probability of getting exactly at least x minus 1 heads. In the case I get a head, I'd like to find out what is the probability of getting at least x minus 1 heads in the first n minus 1 coins. Is it right? Okay, so in the other case, when it is a tail, I'd like to find out what is the probability of getting at least x heads in the first n minus 1 coins. Why? Because I still need at least x heads even after tossing the nth coin. So I would like to find out what is the probability of getting at least x heads in the first n minus 1 coins. So with this, there must be some intuition towards a solution, maybe a top-down recursive brute force solution, which we'll try to optimize further. Okay, So let's say I define terms now. Okay, I define dp of I comma x as, on tossing the first I coins, the probability of getting at least x heads, getting greater than equal to x heads, right? So dp of ix is a probability, and we would like to relate this term to smaller terms and build up a recurrence. Before that, let's look at what is the solution to our problem. The solution will then be dp of n comma n plus 1 by 2, right? The probability of getting at least n plus 1 by 2 heads after tossing all the first n coins. So we would like to find this out, and having defined this term, let's think of some recurrence. Okay, so while I toss the ith coin, okay, then it comes up head with a probability of pi, right? Okay, and then I'm left with the remaining I minus 1 coins, and there I would like to have at least x minus 1 heads. Okay, so my dp of ix breaks down to, I toss the ith coin and I get a head. Okay, so for that my probability was pi that I get a head, and then I need to multiply this with what is the probability of getting at least x minus 1 heads in the remaining I minus 1 coins. Okay, so that is simply dp of I minus 1 comma x minus 1, right? The other possibility is that when I toss this coin, I do not get a head but I get a tail. In that case, the probability of getting a tail is simply 1 minus pi, right? And then I will be tossing the remaining I minus 1 coins, but I still need at least x heads because this coin gave me a tail. Okay, so I'll multiply this with dp of I minus 1 comma x. So with this we already have a recurrence. Okay, we just need to think of some simple base case, and then we can move on towards the implementation. So let's think of this. Let's say I have 0 coins. Okay, so I have 0 coins. What is the probability of getting at least 1 head? Obviously it's 0 because I do not have any coin. I am not going to get any head since I am not tossing any coins. So I can say that dp of 0 comma x is 0 except when x is equals to 0. So what is the probability of getting 0 heads given that I have 0 coins? So by tossing the first 0 coins, that is by not tossing any coins, what the probability of getting at least 0 heads is 1, because of course I'll be getting 0 heads, so the probability will be 1. So dp 0 0 is 1, and if x is not 0, then dp of 0 comma x is 0. Alright, so having discussed the recurrence and the base case, we'll move towards the implementation, and if anything is not yet clear with the implementation, things will get even more clear, right? Let's move towards the implementation now. Okay guys, so now we'll be implementing the idea that we discussed. Okay, so here I have simply taken the inputs, right? I've taken the number of coins, then I've declared this one based array which will be storing the probability of the ith coin. When tossed, it shows a head, so basically it is the probability array. Then this pr double is a macro that I'll explain quickly. So pr double takes some value x and it prints using set precision. Set precision basically tells the compiler up to what decimal places should the number or the double be displayed. Fixed is basically a notation. Otherwise, this is done to avoid outputs like 1, E6, something like those. Okay, so fixed is needed for that. And now I'll simply be implementing the solve function. The solve function returns me what is the probability given first when I toss the first I heads of getting at least greater than equal to heads, number of heads. Okay, so let's just call this x. So solve function returns me what is the probability when I toss the first I coins, and the number of heads that appear on those coins is at least greater than or equal to x. Okay, so at least x. Also guys, I forgot to discuss one of the base cases here, right? So imagine that x is negative, so x is less than or maybe even equal to 0, and you wish you are about to toss I coins. Then what is the probability of getting x coins? Okay, so if x were 0 or less than 0, then no, let's say you were tossing first 2 coins, what is the probability of getting at least 0 heads? Obviously it is 1, because even if a tail appears, then also the probability will be 1, right? And similarly, okay, so let's just take the case that x is equals to 0, or if there are exactly 0 heads, at least 0 heads required, then no matter what, however I toss the first I coins, I get 0 heads, or I get 1 head, or I get all heads. All those combinations are included, and all those are at least 0 heads, right? So this I'll be adding to my base cases now, right? And I'll be implementing the code now. Okay, so initially I'll check for the base case. If x is equals to 0, then the probability of getting or tossing at least 0 heads is 1. If I is 0, so if I have 0 coins left and x is not 0, if x was 0, then it would have been returned here. So if I'm tossing the first I coins, the probability of getting any positive number of heads is simply 0. There's no way of getting any number of heads, right? Okay, now finally I'll be tossing the ith coin. Since I'm thinking about the first I coins, I toss the ith coin. With the probability AR of I, it shows a head. Okay, and now I want for the remaining first I minus 1 coins to have at least x minus 1 heads, and in the other case I can toss it to be tail with a probability of 1 minus AR at I, and for the remaining I minus 1 coins I'd like to have, for the remaining I minus 1 coins I would like to have at least x heads. Since I did not toss a head this time, so for the remaining I minus 1 coins there must be at least x heads. Okay, now what I'll be doing is I'll be returning this value as my answer, and while returning I'll also store the result, because otherwise I'll be solving the same sub problems again and again in the future as well. Okay, so I'll store dp of I at x equal to this. Also, one thing I'd like to do is, if the sub problem was already solved previously, then if dp of I at x is not equal to minus 1, then return dp of I at x. Also guys, one thing I'd like to mention here is that you should always avoid comparing two doubles directly with double equal to or not equal to, because there could be problems with precisions, and let's say one of the doubles is 0.99999 and the other is exactly, and let's say other is minus 1.00001, then they'll compare to be not equals. Okay, so here what I'm going to do is, if the probability represented by dpix is a valid probability, or let's say if it is greater than maybe minus 0.9, I'll return it. Otherwise I'll assume that the sub problem was not previously solved by me, and I'll solve the sub problem. Okay, and here I've initialized all the probabilities to minus 1, indicating that they're invalid initially. Alright, now we can try a sample test case. Okay, so this code should now work properly, I guess. And we're getting the correct output. I'll be submitting this code. Also, I discuss a few things with you. So guys, I submitted these two codes as well. Okay, so the problems here were, in this case the only problem was that I did not pass my array by reference. Okay, so the only difference here was that this was not being passed by reference, and that is why my time complexity had degraded from big of n square to big of n cube, and that is why I received a TLE verdict here. Okay, and in this case I was not storing. After solving a sub problem, I forgot to store this. Okay, so this part I forgot to store, and therefore I was getting a TLE. Reason being, I am solving the same sub problems again and again, and the time complexity is exponential. I have cut those two parts out here because to save your time only, and I cut the part here. You could see the code. So the only difference is that I did not pass it by reference. So this shows the importance of passing these vectors by reference, and otherwise whole copies are being generated. Alright, so here I'm getting an AC. The space complexity and time complexity are simply big of n square, although I really feel that this dimension could have been 1501, but I choose to keep it 3000 because both ways the time and space complexity are still big of n square. So guys, I hope the video was helpful to you, and you learnt another dynamic programming problem and the importance of passing by reference, storing solved results in a top-down approach, and I'll see you in the next video guys. Thanks for watching. Hi guys, my name is Karthik Arora, and in this video we'll be discussing the problem J, that is sushi. Yeah, so you can go through the problem statement once on your own, and then I'll be discussing the prerequisites for the problem and also the problem statement in my words. Yeah, so the problem statement here says that we are given with n dishes, right? And each of these dishes will have some number of sushi inside it. So let's say that the ith dish has AI sushi inside it. So we have these dishes D1, D2, so on till Dn, and they have some pieces of sushi inside it, right? And AI can be up to 3, so a dish will have either 1, 2 or 3 sushi inside it. And then what we do is, we have n dishes. In one operation we will choose a number randomly from 1 to n, so it could be either 1, 2, so on till n, and it will be chosen randomly. It's just like rolling a dice, and whatever the number appears on the dice, we pick that dish and we eat one piece of sushi from that particular dish. So if the random number appeared to be I, I'll pick the ith dish and eat one piece of sushi from it. Again, I'll do this operation, and I'll keep doing this operation till all the dishes here are empty. Okay, so let me just show you an example. Yeah, okay, we need to find the expected number of times we'll have to roll the die in basically to eat all the sushi. Our end results should be that each of the dish has no sushi inside it left, and we need to find the expected number of times the dice will be rolled to achieve this state. Alright, so we'll first consider the easier sample input, that is sample input 2. Yeah, so here what happens is there is just one dish and it has 3 sushi inside it. First time I roll a dice. Now of course here I am going to select a random number from 1 to 1, so of course the random number has to be 1, there is no other possibility. I'll select this dish and I'll eat one piece of sushi from it. Cool, now 2 pieces are left. Again I roll the dice, I get 1. Now I eat one piece of sushi from this dish. Again, one piece of sushi is still left, so I roll the dice again, and now I am left with this empty dish. And since all the dishes in this input are empty, so the number of operations that I performed to reach this state was 3. And no matter how I perform the experiments here, my operations needed to reach the empty state is always 3 in this case, right? Okay, so here the answer was 3 because I had to roll the die 3 times or select a random number thrice. Okay, cool. Let's look at sample input 1 now. So in this case, when I perform one experiment means that I actually simulate the task of selecting a random number, then eating a dish, and so on. The number of operations that will be needed will differ by large amounts. Okay, in different experiments the number of operations will differ. We just need to find the expected number of operations, and this the like AdCoder says it's 5.5. Let's see how. Okay, so if I have this, let's say I perform one experiment. In the first turn I could get a random number 1 and my dishes will look like 0 1 1. Let's say I get a random number 3 this time and then it will look like this 0 1 0. Let's say I get 1 again, then I have 0 1 0 because the first dish is empty anyway, so of course I cannot eat anything, but one operation is still wasted anyway. And now let's say I get 2. Now I'm finally at the correct state and the number of operations required by me were 1 2 3 and 4. Alright, so in this experiment the number of operations were 4, but in a different experiment they could be maybe 100 or 500 as well, because I could have eaten the first dish here and I could have kept on getting the same random number 1 again and again. Alright, it could be even infinity. So yeah, I hope you get the point. And the minimum it could be is 3, because I could select the random numbers maybe 1 then 2 then 3 and the operation needed will be 3. All we are asked is, we are asked to find how it is like what is the expectation of the number of operations that a person will have to perform. Okay, so before we understand how this is 5.5, we need to go through a little bit of theory of expected values and then we'll come back to this thing. Yeah, so now I'll be giving a brief explanation of expected values and a little bit of probability theory, and then hopefully you will be able to quickly understand the solution. For the people who already have some background knowledge on these concepts, they may skip this part. However, I hope this will be helpful even if you have the basic understanding. Expected values, right? So let's say you have a random variable x, okay, and you're conducting some experiments E, right? After conducting the experiment E, you get a value for the random variable x associated with that particular experiment, right? So let's take an example of an experiment and a random variable. So let's call our experiment rolling a dice. So our experiment is rolling a dice and this dice has 6 faces. So any number from 1 to 6 can appear, right? And let's define a random variable x as the number appeared on the die, as number that appeared on the die. Right, so we define expected value of x as expectation x. Of course, here let's say I conduct the experiment first time, I can get a 1, then in that case my x1 will be 1, the value of random variable when the experiment was conducted the first time. Maybe second time I conduct the experiment, I roll the dice and I get a 4, then my x2 will be 4, and so on. I could conduct this experiment n times, and let's say the last time the value could be maybe 3, so it could be anywhere from 1 to 6, right? Alright, so we define expected value as you perform the operation n times and you see what is the average value received. Okay, expected value is simply the average value over all the experiments. So the only thing here is that you perform this particular experiment infinite number of times. Okay, so here the expectation value will be perform the experiment n times, so limit n tends to infinity and summation xi over n. This is the definition for expected values. So basically I am going to perform this experiment of rolling a die again and again and again, and keep noting the numbers that I get. I'll add them up and then I'll divide by the total number of experiments I've performed. So expectation of x will be, if I perform this experiment infinite number of times, then this quantity or the average will be my expected value of x. Alright, so of course evaluating this value is not practical this way. However, there are different ways to calculate. before discussing how we can calculate this analytically in a better way in which it is possible to do it, I'll just show you a code and we'll see what answer we're getting there. Right. So here I've defined this function roll dice. This simply generates a random number from 1 to 6. Okay. And then here I have a sum which is initially 0. I say I am going to conduct the experiments, let's say 1000 times. Now I conduct these experiments, I roll the dice and I see what was the number that appeared on the dice and I add it to the sum. And after 1000 times performing this experiment, I'll see what value I'm getting, the average value that I'm getting. Alright. So if I do this 1000 times, I am getting 3.577, and since ideally this thing should be infinite instead of 1000, but it's not possible to make it infinite here. Let's just check maybe 10 to the power 5 now. Let's see where this value goes to. Alright, so it's 3.49 now. It's very close to 3.5. Let's see how and determine how we could actually calculate this value analytically. Okay. Alright, so we'll be discussing the contribution technique to find expected values. Okay. Contribution technique. So we said that we're going to perform the operation n times and the limit under the limit n tends to infinity. But the thing here is that we cannot really perform the operation infinite times. Now whenever I perform the experiment E, I know that the value that is going to appear is either 1, 2, 3 or up to 6 because I'm rolling a die and these are the only possible values, right? So my xi is going to be either of these values. Now if I knew basically the fraction of experiments in which my value will be 1 and the fraction of operations in which my value will be 2 and so on till 6, what I could do is, my formula was summation xi over n and limit n under the limit n tends to infinity. So let's just remove this limit for the time being and let's say my formula is this, right? Now if I knew the fraction of experiments in which xi equals to 1, then what happens is my formula will become f1. f1 is the fraction of operations in which I'm getting a 1, and let's say f2 is the fraction of operations in which my dice shows me a 2. Okay, so in those cases the xi will be 2, so it will be 2 into f1, right? Then again, sorry, 2 into f2, right? f2 is the number of experiments or the fraction of operation. Let's just say f2 is the number of experiments in which out of n in which the dice showed me a 2. Then again, let's say f3 is the number of experiments in which the dice shows me a 3. In all those cases xi is 3, so overall it's contributing 3 into f3 to the total sum. Similarly 4 times f4 plus 5 times f5 plus 6 times f6, okay, whole over n. Now what we have is, we have this. We have overall our expected value ex becomes f1 plus f2, 2 times f2, 3 times f3, 6 times f6 whole over n. Okay, so f1 was the times or the number of experiments in which the dice was showing me a 1. Okay, so now think of what is fi by n. Okay, so fi by n is simply the probability of getting an I on the dice, right? The probability of rolling the dice and getting I on the face of the die. So f1 over n is simply the probability of getting a 1 when you roll a die, right? Equal to probability of getting a 1 when you roll a die. Alright, so f1 by n, it is quite simple. What is the probability to roll a 1? It is simply 1 over 6. Since there were 6 possible outcomes, then f1 by n will simply be 1 over 6. The probability to get a 1 is 6 because there are a total of 6 outcomes and only one of them is favorable to us, so it's 1 by 6. Similarly, f2, f3, f4 and f5 and f6 is also 1 over 6. And now we can evaluate this formula. Okay, now we can simply evaluate our formula by substituting 1 by 6 instead of fi's, and it becomes 1 over 6 plus 2 over 6 plus so on till so you can calculate this thing and this thing will turn out to be 3.5. okay, you can calculate it and you'll see that this value is 3.5. so as we saw, we were getting a very close value to 3.5 in our code as well. Okay, so this is called the contribution techniques. Instead of conducting the experiment infinite times, we convert it to probabilities. Okay, I'll just give you one more brief short example of expected value and then we'll move to the actual dynamic programming problem. So let's say in this question, our experiment is rolling a dice till you get a 6. Rolling a dice till you get a 6. Alright, and let's define our random variable here to be number of times you have to roll a die before you get a 6. So number of times dice is rolled. Okay, we wish to find out what is the expectation of x. Okay, so what is the expected number of times you will be rolling the dice? So again, we can simply do this experiment in finite number of times and see what the value comes out to be. The other thing is to use contribution technique here. Okay, so in how many experiments will this value be 1? The number of times the dice has to, what fraction of experiments this value will be 1. So simply, if you start an experiment and you roll a die, what is the probability of getting a 6 in the first turn? It is simply 1 over 6, right? It is simply 1 over 6 plus, again, what is the probability or the fraction of operations in which this particular value x will be 2? It will be when you roll a dice, you do not get a 6. For that the probability is 5 over 6, and then you roll a die again, then it is 1 over 6, and here the xi is 2, so you multiply it by 2, here you multiply it by 1, because we are finding the expected number of operations. So the experiments in which the fraction of experiments, these are the fraction of experiments in which x turned out to be 1 and they contribute 1 to the overall sum, this sum, right? And here these are the fraction of operations in which the xi is 2, so you multiply it by 2, this is the contribution to the overall sum. Again, in what is the fraction of operations in which you have to roll the dice thrice? These are the operations in which first you roll any other number than 6, then again you roll some other number than 6, and then you roll a 6. Overall you multiply it by 3. So this thing will become something like this. It's 1 by 6 into I and 5 by 6 to the power I minus 1 summation, and I goes from I goes from 1 to infinity. All right. Yeah, so this is the expected value, the expected number of times you'll have to roll a die before you actually get a 6. And you can evaluate this using maths, learned in 12th standard, or you can google it. This thing will become 6. Okay, so I've written a code which simply performs this experiment infinite number of times or a lot number of times and then produces a result. Let's just check what result it gives. So this function get6 simply generates a number. If it is equal to 6, it returns the number of times the die had to be rolled. Else, one time the dice has already been rolled and it sees now how many times will I have to roll a die. So this is basically performing our experiment, and I'll perform this experiment a lot number of times. Let's firstly do it 1000 times and I'll see what value I get. This value should be 6 if I do it infinite number of times. For 1000 times this is 5.73. Let's do it 10 to the power 5 times. And yeah, it got a lot better. It became 5.99. So hopefully the expected value concepts are now clear to you, and we can move on to the real problem that we're trying to solve here. So we are solving J sushi, and okay, so as I taught you the expected value idea, that perform the experiment infinite number of times and then average out the values you get, and that is the answer, basically expected value. So here also we could have done the same thing. The only problem is that we cannot perform the experiment infinite number of times. So here I've written this small code. This is simply doing the simulating. This is simply simulating this thing mentioned here. Okay, so you can look at this code, the experiment. So while not done, like while not all the dishes are empty, done simply checks if all dishes are empty. If they are, then you don't need to perform any more operations. Otherwise, select a dish randomly. From 1 to n, I select a random dish and I eat one dish from it. If the dish is empty, of course I cannot eat. Otherwise, I eat one sushi from it, from the dish. And then I add 1 to the number of operations, because I just rolled a dice here, and one operation for that, plus the number of times I still have to roll the dice to eat all the dishes. And overall this is the experiment, and let's try and conduct this experiment 1000 number of times on our sample input, and let's see what output we get. So for 311, the actual answer is 5.5, and let's see what we get. Oh, just a second, sorry. Yeah, so we should get 5.5 if we do this infinite number of times. We're getting 5.538, which is quite close. Okay, let's try this one too. So the answer for this is 4.5. And we're getting 4.466, which is quite close. If we do this more times, I guess the solution will keep getting closer to 4.5. So guys, hopefully you understand the idea of expected values and probabilities, and we'll solve the problem now. So by making it 10 to the power 5, our answer almost became 4.5. okay, right. So guys, now let's solve the problem. Enough of background to expected values, and now you will be able to understand. Okay guys, so we are now solving J sushi. Okay, so if you want to go through the problem statement, you can use the previous video, right? Okay, so here let's say you are at a state A. Initially the input, we are at state A. Okay, and we want to reach this A state simply represents some number of dishes with some sushi inside them. Okay, and you wish to reach some state, let's say end E, and the state is simply all the dishes with 0 sushi. Okay, this is the initial state and this is the end state. Okay, so let's say you roll a dice and you know that you could either reach to some state S1, S2 and so on, some number of states. Okay, so let's say you knew that with P1 probability you are going to reach state S1, and with P2 probability you will reach the state S2. Finally with Pn probability you're gonna reach some state Sn. Okay, right, and you wanted to find the expected value to reach the expected number of operations you need to perform to reach from A to E. Alright, so first of all, this is one operation, so one for this, because sure, you will be rolling a dice and then you will be going to some other state from A. That is, going to some other state is basically eating a sushi from that some number of days by rolling a dice, and then you reach to either of these states. Let's say you knew the expected value or number of operations that you have to perform to reach from S1 to E, and from S2 to E, and so on from Sn to E. Okay, let's say you already knew this. Then the expected number of operations to reach from A to E is simply 1 for the current operation that you perform by rolling a dice and reaching some other state, plus P1 times the number of operations that you have to perform, the expected number of operations that you have to perform to reach from S1 to E. Let's call it, let's just say S1 is the expected number of operations, or maybe small s1. S1 represents the state, and S1, small s1, represents the number of expected number of operations you have to do to reach E from capital S1, plus P2 S2, plus so on till Pn Sn. Okay, so guys, if you have some ambiguity in this, you can view the previous video. Yeah, this is simply through the contribution technique to expected values and using the results of other states. Okay, yeah, so here let's think of what one state is. Okay, so a state can be something like this. If there are 3 dishes, I could represent my states as this, and let's say for some other sample input, when there are just 2 dishes and the first has 1 sushi and the second has 2 sushis, the state could be this. Okay, and then let's say I was at this state, I could either go to the state 0, 2, or I could go to the state 1, 1, right? And the probability of reaching this state is simply 1 by 2. Same with the probability of reaching this state is also 1 by 2. So my expected number of operations here will be 1 plus half into, let's just say S1 is the number of operations needed here, plus half into S2. Alright, because this is true because when you conduct this experiment infinite number of times, from this particular state you will be going in half of the times you will be going to the state, and the other half of the times you will be going to the state. So you can simply say that, yeah, this will be the fraction of contribution that S1 will make to my overall result, and same way half will be the contribution this state will make to your overall result. Because on conducting these experiments infinite times, you will have 50% chance of going here, and in the other 50% cases you go here. So overall, using the formula we had of summation xi by n, limit n tends to infinity, and applying the contribution technique, you have 1 plus half S1 plus half S2. Alright, again you can go from the state to either the same state itself, or you could go to 0, 1. Alright, so either you could go to the same state or to 0, 1. Again, in how many cases will you go to the state 0, 1, and in how many will you go to 0, 2? This will again be 1 by 2, 1 by 2. Overall, we would wish to reach 0, 0, right? Okay. So before we move forward, I would like you guys to make an observation here. I will help you through it. So what will be the answer for 1 comma 2? We saw that the answer is 4.5, right? So will you expect the answer of 2 comma 1 to be the same or different? So by intuition this is going to be same, because even this state will depend upon two other state, and that will be 1 comma 1 and 2 comma 0, which are basically the same states. There's no difference in these two. So for more clarity you can say that, okay, you are at the state maybe 1 comma 0 and you have some expected operations to reach 0 comma 0. Even if you are at the state 0 comma 1, these expected operations will be exactly same. All right, okay, so we can make an observation and conclude. So basically first let's write an observation. So the observation here is that the ordering of the dishes does not matter at all. Ordering does not matter. So the answer for 1 2 3 4 5 is just the same as 5 4 3 2 1. Okay, like I'll make it more concrete. Ordering does not matter. Ordering of the dishes does not matter. So answer for the dishes, let's say I have 3 dishes, maybe 2 comma 2 comma 1, this will be the same as the answer for 1 comma 2 comma 2. Same way you could think of like the answer for maybe 2 comma 3 comma 1 comma 2 comma 1 comma 3 is the same. The answer for this will be the same as the answer for 1 1 2 2 3 3. All right, so our observation is that the ordering does not matter, and from this we can conclude that what really matters is the number of dishes of a particular category that you have. Okay, what matters here is the number of dishes of a particular category. So what matters is D0, the number of dishes that have 0 sushi, D1, D2 and D3, the number of sushi that have exactly 3 sushi in them, the number of dishes that have exactly 3 sushi in them. Okay, so now we can move forward to the recurrence and the solution to the problem. All right, so now let's say you are at some state in which you have maybe x dishes with 0 sushi, y dishes with 1 sushi, and z dishes with 2 sushi. Also let's just say, let's call O. Okay, O is the number of dishes that have 0 sushi in them, and then x for 1 2 and 3. all right, yeah. So from particular state OXYZ you can reach the following states. Okay, so one way you can eat a dish, you can select a dish in one operation that leads that is basically a dish with 0 sushi, and you reach the same state. Okay, right. Or you could eat a dish from maybe a you could eat a sushi from a dish that has 1 sushi in it, and then you will reach the following state. Okay, you will have one less dish with 1 sushi because you ate it, and y and z are unaffected here, but O becomes O plus 1 because now the sushi from the dish you ate is now empty, so it contributes to the 0 dishes, right? Okay. Or one more state that you can reach from here is you could eat a sushi from a dish with 2 sushis, and you reach O comma x plus 1 comma y minus 1 and z. Same way you could reach the state O x y plus 1 and z minus 1 by eating a sushi from a dish with 3 sushi, right? So these are the states your particular state depends upon. So if you knew the expected number of operations for this state and this state, you could write a recurrence. However, there is a problem that the state also depends upon itself. So I'll be writing a recurrence, but let's just make a small observation first, okay? So here x plus y plus z plus o is simply equal to the total number of dishes. So I don't really need to keep track of o, as o can simply be found out using n minus x plus y plus z. Okay, yeah. So now I'll be writing a recurrence. So let's say dp of x, y and z as the expected operations needed to reach from the state xyz to the state 0, 0, and here x means the number of dishes that have one sushi in them, 1 dishes. Y means the number of dishes that have 2 sushi in them. Then same as z as the number of dishes with 3 sushi in them. Alright, so this represents the expected number of operations to reach the state 0, 0, 0. Alright, okay. So our final answer will simply be dp of initial state, and let's say we had counted the number of sushi initially. The number of dishes with 1 sushi were 1. Same way the number of dishes with 2 sushi were 2, and the number of dishes with 3 sushi was 3. So our final answer will simply be dp of 1, 2, 3. So we need to see how we can find a recurrence for dp xyz, and our work is done. Okay, so as we saw, dp of xyz depends upon 4 states. Alright, 1, it depends upon itself, okay, because you could pick a dish that has zero sushi inside it, and you could read the same state. Let's say that the probability of doing that is pz. So first of all, I am rolling a dice, so I'll be adding one operation for that, right, plus the probability of choosing a dish with 0 sushi in it. I call it pz for now. We'll see what it really is. We'll write a formula for pz as well. So we read the same state by selecting a dish with 0 sushi, or I could select a dish with 1 sushi. Let's say the probability of doing that is px. Oh, just a second. Let's call this p0, and yeah, I'll call this px, the probability of selecting a dish with 1 sushi. And by doing that, I read the state x minus 1, y and z. If I select a dish with 2 sushi in it, I call the probability of doing that py. I read the state dp of x plus 1, because I ate a sushi from a dish with 2 sushi inside it. One sushi got eaten up, and now that dish has 1 sushi, so x increases therefore, and y had decreased, plus the probability of selecting a dish with 3 sushi in it is pz, and I read the state dp of x comma y plus 1, because a dish had 3 sushi, now it has 2, so y has to increase because of this thing. And finally, this is my recurrence, right? dp of x, y plus 1 comma z minus 1. However, we could from here we could have gone straight away towards the solution by implementing this recurrence top down or maybe bottom up. However, there's a small problem in implementing it. The problem here is this, that dp of xyz depends upon dp of xyz. So what I'm going to do is, I'm going to take dp of xyz to the left hand side and simplify the equation further. So I'll just erase the top part. So my dp of xyz, after taking it to the left hand side, it would have become dp of xyz common 1 minus p naught, right? So dp of xyz, and I'll take 1 minus p naught to the right hand side in the denominator. Overall it will become 1 plus px dp of x minus 1 yz plus py into dp of x plus 1 y minus 1 comma z plus pz dp of x dp of x y plus 1 and z minus 1, right, whole over 1 minus p naught, right? So guys, hopefully the recurrence is now very much clear to you. Let's just discuss a base case, and with that we can move on to the implementation for the problem. Yeah, so what is the expected number of operations for dp 0 comma 0 comma 0? It is simply 0, because all sushi has already been eaten up and you do not need to perform any further operation. So now I have a base case and a recurrence. Okay, now we can move forward towards the actual implementation of this problem. However, for more precision, what we can do is we can minimize the number of division operations that we'll be performing. Okay, so let's first of all think what is px, py, pz, alright, and p naught. So px was the probability of selecting a dish that has one sushi in it, right? So px was simply the total number of dishes, and yeah, x over the total number of dishes. Similarly, py is the number of dishes that have two sushi over the total number of dishes, and pz equal to z over n. Now what is p naught? P naught is the number of dishes that have 0 sushi in them over total number of dishes. So we have total number of dishes minus x plus y plus z as the number of dishes with 0 sushi whole divided by n. Now as you can see that there is n in all these denominators, what I'm going to do is I'm going to simplify the equation further, and what will happen is here we have px and there is a denominator n. Again here we have py with denominator n and pz with denominator n. One thing that I can do is I could multiply throughout with n. Okay, and let's see what is 1 minus p naught. So 1 minus p naught will be, this will be n minus n plus x plus y plus z, right, over n, and this will cancel out. So we have x plus y plus z over n. So we have n in both numerator and denominator. If I multiply 1 with n, so I'll write 1 equal to n by n, and then my equation simplifies to okay, so like my equation will simply simplify to where I'll have a denominator x plus y plus z. I'll quickly write it and you guys can see. So my equation simplifies to dp xyz is equals to n plus x times dp of x minus 1 yz plus y times dp of x plus 1 y minus z plus z times dp of x comma y plus 1 comma z minus 1, and whole of this divided by x plus y plus z. Alright, so now guys, now we can move forward towards the implementation, and let's see if and that will make it even more clear to you. Alright, so let's see. Yeah, I'll be removing this now. Sure, here I've simply taken the input CNN. Initially there are 1, 2 and 3 number of dishes, and I've taken the input, and if it is a dish with 1 sushi, then 1 plus plus, then 2 and 3. This basically represents the initial state. N is the total number of dishes I have, and the solve function will return me, I'll call this x, y and z here now. The solve function will simply return me the expected number of operations which I'll be printing. So x, y and z. Alright, so first of all I'll check if all of these are 0, then required operations is 0, that is our base case. If x is 0 and y is 0 and z is also 0, then simply return 0. Alright, and now I will check if this particular value has been calculated, if this particular subproblem has already been solved by me. So if dp of x y and z represents a valid value, that means it has been calculated, then I'll return it. So what can be a valid value for the expected number of operations? So it will definitely be greater than 0, and since I don't wish to directly compare doubles, I'll write greater than maybe minus 0.9. I could have written minus 0.5, minus 0.3 or any other value, given that my valid expected operation lies are greater than 0. Alright, so any negative value means that this has not yet been calculated. Sure, this looks alright to me now. And if I haven't ever solved this a problem, I'll be solving it now. I'll say double exp as the expected number of operations I'll be doing. Exp equal to the recurrence which we thought of, which is n plus we have x into solve of x comma y comma z, x minus 1, I eat a sushi from a dish with only one sushi, plus y into solve of x plus 1 comma y minus 1 comma z plus z times solve of x comma y plus 1 comma z minus 1, and finally I'll be return dp at, I'll return while storing my value exp, and our denominator, the denominator was x plus y plus z. So guys, I think this code should now solve the problem. I'll simply try a test case. Yeah, it should work. Alright, there's some problem here. Sure, we have x into solve of this plus y into this. Okay, error too few arguments. Okay, I haven't passed in. Okay, right. One more thing I'd like to discuss is I haven't taken care if my x, y or z can go negative, right? It is possible that they might go negative, like x may be 0, y may be 1 and z may be 1, and I call this particular state, then my x will become minus 1. However, here although the equation will still be 0 into, but then I'll be stuck in infinite recursion, isn't it? So if either of these is negative, right, if x is less than 0, basically if either of these is less than 0, I should return some value to stop my infinite recursion, right? So I'll be returning, so here one thing to note is I could return any value honestly, because overall whatever value I return, it will be multiplied with a 0. So let's just say I return a 0. Since if x is negative, it would have been 0 before this call, and then 0 into any value is 0. So this is simply done to stop my program from going into an infinite recursion. Alright, so there's some problem again. Let me just check. Alright, so I'm a little unsure about this error. Let me just check what it's saying. So it says line 4 20 killed, run.std error. Okay, so I think this has to do something with input and output. Okay, let me just remove this print statement, maybe then it works. Alright, I think there has to be something in the compiler, although I do think that the code is right. So let me just submit and check. Alright, so the code looks alright to me. Let me just submit. If it doesn't work, then we'll see why we are getting that error. So I think it is running on AdCoder properly. So guys, till then I'll just discuss the time complexities with you. So here the space complexity is of course n cube, right, because we're taking 3 dimensions and n was up to 100, so TLE should not be a problem. Space complexity is n cube and time complexity is also n cube, given that a particular state depends upon constant number of states, or 3 to be exact. So both time and space complexity here are n cube, and I've taken this dp dimension, dp array of 301 cross 301 cross 301 size. Alright, so just let me check now. So yeah, it's getting an AC. So probably there was some compiler specific issue here. Anyway, thanks for watching the video guys. Hopefully you liked it. I'll see you in the next video. Bye. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem K, that is stones. Okay, so this not a very hard problem. You can go through it once and I'll recommend you to think of a solution. Okay, right. So we're given with a pile of stones. The pile initially has K number of stones. Okay, so just a second. Yeah, so the pile has initially K stones. Yeah, and we're given with a set A1, A2 and up to AN. You can assume this set to be indicating the set of valid moves. Okay, so basically if there are 2 people playing and the person who is about to make a move can remove either A1, A2 or AN stones from the pile, and then the turn comes to the other person, right? So the loser in this game will be the person who is unable to make a move when his turn comes. And remember that you can only remove either A1, A2 or AN. Basically one of the numbers in this set is a valid move, right? So you must be able to make a valid move, otherwise you lose. So this guy Taro will be beginning the game and we need to determine whether he can win it or not. Alright, so let's just go through a sample input and it will be more clear to you. Right, so here we are given with the sample input 2, 4. That means n equals to 2 and k equal to 4 means there are 4 stones in the pile. Okay, and the valid move set is 2, 3. And when Taro begins, what he can do is he can either take away two of the first bricks or 3 of the first bricks or stones. Okay, so let's say if he would have taken away 2 stones, then the other person is left with 2 stones and he can take away them, and then Taro will be left with no stones in the pile and he loses. However, since both players will be playing optimally, this guy will remove the first 3 stones, since 3 is also a valid move, and then the turn will be given to the second player. Okay, now he's left with 1 brick, but of course he cannot remove this 1 brick since the valid move set is just 2 and 3, so he will lose, and therefore the answer here is 1. Same way you can go through the second sample input also. A good explanation is given by AdCoder, and we'll move to the solution now. Alright guys, we are solving K stones. Okay, so let's say that currently there are I stones in the pile. I stones in the pile. Now the player who is making the current move would like to remove that many number of piles, such that basically he would like to remove a particular number of piles, stones from the pile, so that when the other player plays with the remaining, let's say I minus k stones, I minus x stones in the pile, and the other player plays, he loses. So basically the goal of the current player is to remove some x stones from the pile in such a way that when the other player plays with the remaining I minus x stones, he loses, right? Okay, so we will try to determine whether is it if it's possible for the person who's making the first move, given that there are I stones in the pile, to win or not. Okay, so I'll be defining a term now. Let's define dp of I. dp of I is that there are I stones in the pile. If the player who's making the first move, okay, if the player who's making the move now, given that there are I stones in the pile, is able to win, then dp of I is 1 if win, otherwise it is 0. Okay. Cool. So we now know we have defined a term. We'll try to relate this to find maybe dp of k. dp of k will be either 0 or 1. 1 if the player who's about to make the first move can win, and in that case our answer will be first, and otherwise our answer will be second. Cool. So hopefully till here everything must be clear. We'll see how we can find out dp of k. Okay, so think of it this way. We want to find out dp of k, right? Now this guy can make us reach either of the following states. We can go to k minus a1, and we'll be like, we can go to k minus a1 by removing a1 stones from the pile, or we could go to k minus a2 by removing a2 stones from the pile, and so on till we can go to k minus an by removing an stones from the pile. Now think of it this way. Let's say we know dp of k minus ai, right? If either of this state says 0, right, this means the person who's going to make a move from the one of these states basically. So let's say k of a minus I, dp of k minus ai is 0, then the person who's making the current move can make the other person reach this particular state, and the other person loses, so this guy will win. And since they are playing optimally, so he will definitely make such a move so that the other person can no longer make a winning move, right? So hopefully this is clear. So even if one of these states k minus ai is 0, even one of this state is 0, then we can reach that state by removing a1 stones from here, and you reach k minus a1. And since this is a losing state for the person who makes the first move when the stones in the pile is k minus a1, then k will be a winning state, right? So if you can reach to from a given okay, I'll just repeat it. So if from any given state k you can reach to a state k minus ai, which is a losing state for the person who plays first, then k is a winning state. Cool. K is a winning state if from k it is possible to reach any other state that is a losing state. Alright, so okay, let's think of one more case. What is dp of 0? dp of 0 is of course a losing state, so we say it is 0. Since there is no stone to remove, you cannot remove any, and the person whose turn it is of course loses. Now what is dp of I, or dp of x? Okay, what is dp of x? So as discussed, dp of x is 1 if dp of x is 1 if dp of x minus ai equal to 0. So if any state, for all ai, if any state dp of x minus ai is 0, then dp of x is 1, because then we'll remove ai stones from the pile, and the other person who has to make the first move will now definitely lose, so the x is a winning state. Alright, otherwise if there is no state x dp of x minus ai, there is no state which is a losing state, then x will be a losing state, right? So guys, hopefully the explanation is clear to you and we can move forward towards the implementation. I'll just explain one sample input using this logic and then we'll implement it. All right. Okay. So let's take the sample input 2, 5 and 2, 3. Yeah. So we have a pile of 5 stones. So we need to find out DP of 5, and 2 and 3 are the valid move set. We saw that DP of 0 is obviously 0 because it is a losing state. Then 1 is also 0 because we cannot make any valid move. Again for 2, from 2 it is possible to make a move and reach a losing state, right? I could remove 2 stones here and reach 0, and DP of 0 is 0, therefore 0 is a losing state, so 2 is of course a winning state. Again for 3 I could reach 0, and then since it is possible to reach a losing state from 3, so 3 is a winning state. Then from 4, okay, from 4 it is possible to reach the state 1 by removing 3 stones, and 1 is a losing state, so 4 is again a winning state. And for 5, from 5 I can either reach state number 3 or 2, right? And both state number 3 and 2 are winning states, so since I cannot reach any state from 5 which is a losing state, therefore 5 is a losing state and my answer will be second. All right, so we can check our confirm our answer. Yeah, so the answer is second, and now I'll be implementing the same logic that we have discussed. Hopefully it is clear to you, and if it is not, with the implementation it will be very much clear. Okay, yeah, so here I've passed a vector v, and then this k represents the number of stones in the pile, v represents the valid move set. I'll declare a vector. I can have booleans, right? So let's just say bool dp, and the size will be k plus 1, and I can do mem set dp comma 0 comma sets of dp. So initially I'm okay, I'll initialize all the states to losing states. Cool. Then dp of 0 is 0, of course. I've already initialized it using mem set. Now I'll be doing this for integer I equal to 1. I'll be checking if dp of I is a winning state or a losing state. I less than equal to n I plus plus, and here I'll simply see if it is possible to reach any losing state from this current state. So I can make a move integer move any valid move. So move should belong to the set of valid moves. So if dp at I minus move equals to 0, then dp of I is a winning state, right? Also I need to make sure that move is basically less than equal to I. If move is greater than I, it's not possible to remove that many stones, and I should simply continue. Right, and if it is possible to move number of stones from this particular pile currently, then I'll check if it is a good thing to do. If it is, then dp of I is a winning state. Finally, okay, I'll return a string here. Sure, so once this is done, finally I'll check for dp of k. So return first. In fact, wait a second, I'll see what dp of n is, dp of k is. If dp of k is 1, I return first, otherwise I return second. And I guess this code should work now. I'll simply check a test case. Also, yeah, I need to make this capital here. Sure, alright. So let's just check a sample test case. Answer should be first. Okay, just a second. Yeah, this has to be k here. Alright, so I'm getting the correct output for this case. Let's just try this one too, and then we'll submit. Answer has to be second, and we're getting it. Let's just submit it. Alright, so the code should hopefully work. Till then, we'll simply discuss the time and space complexities. Of course, the space complexity here is big O of k, because I'm declaring a k-sized vector, and k was up to 10 to the power 5, so it's no problem. Also, the time complexity here will be, this loop runs n times, and this internal loop will run, this outer loop runs k times, right, up to k, and the inner loop will iterate over all the elements of the valid set, which can be at most n. So it's going to be a n into k complexity, but n is up to 100 and k is up to 10 to the power 5. So an overall 10 to the power 7 operations is very much doable in the given time, and so TLE must not be a worry. Alright, let's just check if we get an AC. Alright, so the solution received an AC. So guys, hopefully the video was helpful to you, and I'll see you in the next video. Thanks for watching. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem L, that is deck. Okay, so you can read the problem once and then I'll explain it to you. Okay guys, so two players are playing a game, and in the game there is an array of let's say n integers, and each time the players are alternating turns. So in the turn of any particular player, let's say player number 1 or P1, let's say two players P1 and P2, here they have named them Taro and Jiro, I'll just call them P1 and P2. So in P1's turn, he can choose one of the integers on the extreme left or the extreme right of the array and remove that particular element from the array. So let's say initially the array was A1, A2 up to AN, right? So in his turn, he could remove either A1 or AN from the array, okay, and get that many points for making that move. So let's say if the array was A1, A2 and A3 and A4, then if he removed A1, his score increases by A1, and we're left with the following array A2, A3 and A4. And now it's player 2's turn. So he can again do the same thing, either remove the extreme left element or the extreme right element. So he can either remove A2 and A4 or A4, and let's say if he removed A4, then the remaining array will be A2, A3, and A4 will be added to his score. So hopefully the game is clear to you, and the objective of the problem is that assume that the players play optimally. They'll try their best to win and maximize their total scores. What we have to do is, okay, so the problem says that Taro tries to maximize x minus y. X is his own score and y is the other player's score, whereas Jiro tries to minimize this quantity. So it's basically, if P1 is trying to maximize this, he's in short trying to maximize x and minimizing y. I'll prove it to you how, but for now you can assume that, in short, player 1 is trying to maximize his own score, whereas player 2 is trying to maximize his own score. I'll prove it to you how these two things are the same or equivalent, right? Let's just go through a sample input. Yeah. So in the first sample input, as you can see, there are 4 elements initially in the array. So it's 10, I'll say 1, 8, 9 and 3 instead of 10, 8, 10, 80. So we have 1, 8, 9 and 3. Initially what happens is that, Taro can either remove 1 or 3. So there were two possibilities, either remove 1 and get a score of 1 in his own total. So the player 1 makes a move, remove 1, and we are left with the following array. Or the player 1 can make the following move. He could remove 3 and we are left with the following array. In this step, if he would have removed 1, he would have got a 1 in his total, and if he removes a 3, he gets 3 in his total. Now player 2 gets to make a move again. The player 2 can make the following 2 moves. If we are at the state 8, 9, 3, he could either remove 8 or he could remove 3. So if he removes 8, then we are left with 9 and 3, whereas if he removes 3, we are left with 8 and 9, right? So guys, hopefully the statement is clear to you what the game actually is. We'll see how we are getting the answer 10 here. Okay, so we are getting the answer 10, which is the difference between x and y. So x's score and y's score, or player 1's score and player 2's score. Okay, so they say that player 1 will initially remove 30. So this gives x a score of 30, or player 1 a score of 30. Then after that the other player will remove 90. Alright, so his score becomes 90. Now player 1 will remove 80, so his score gets another 80 points. And finally player 2 will remove the last remaining element, which is 10. So overall x becomes 110, y becomes 100, and we output 110 minus 100. Alright, so if both of these play optimally, this is the score that we have to output. So we have to output 10, right? We'll see the sample input 2 as well, and then we'll move to the solution. Alright, so in this case we are given with the array 10, 100 and 10. So since so the observation here is that no matter what move the player 1 will make, the output is always going to be minus 80. Okay, so here initially the first player removes this 10 and gets a score of 10. Now we're left with the array 110. Player 2 removes 100, then it's player 1's turn again. He removes the last remaining element, that is 10. So we have a score of 20 and 100, and we output 20 minus 100, which is minus 80. Alright, so guys, hopefully the problem statement is very much clear to you. We just have to find out the maximized value of x minus y. Okay, not really the maximized value of x minus y, we have to find out the value of x minus y given that the two players play optimally and player 1 tries to maximize x minus y, whereas player 2 tries to minimize x minus y. Alright, so let's move towards the solution and it will be very much clear to you. So we're just trying to solve the problem, I guess, L deck, right? Okay, so first of all, there's an observation, like as I said, the problem statement says that player 1 tries to maximize x minus y. He tries to maximize this thing, whereas player 2 tries to minimize this quantity, right? Okay, so this is what basically means here is that player 1 tries to maximize x and player 2 tries to maximize y, or in other words, he tries to minimize x. For now, let's just say he tries to maximize y. Okay, how this is correct? Since player 1 is trying to maximize x minus y, the positive quantity here is x, so he will try to make it as much positive as possible, so he tries to maximize x. Okay, whereas player 2 is trying to minimize x minus y, so he will try to make it as negative as possible, and the negative quantity here is y, or basically he'll try to maximize y so that overall it becomes negative of that value and overall x minus y gets minimized. Okay, and another way to look at it is, let's make another observation here. So since we're given the array a1, a2 and so on till an, right? There are n elements in the array. The observation here will be that what will be x plus y? The sum of the scores of the two players at the end of the game, right? What is the sum of the scores at the end of the game? Alright, let's just check the sample input. So in this case, you saw that one player's score was 20 and the other one was 100. So sum was 120. Again, here you saw that. Alright, so basically the point is, just a second. Yeah, so the basic point here is that the scores are basically removing some of the elements, and if X had removed some of the elements, the score X is basically player 1 had removed some of the elements, then the score X is simply the sum of those elements, and player 2 will remove the elements that are not removed by player 1. So these are basically all the elements of the array which were not removed by player 1, and at the end of the game all the elements are removed, so X plus Y is nothing but the sum of the elements of the array, right? So hopefully this observation is very much clear to you, right? So whatever is the sum of the elements of the array, at the end of the game the scores, the sum of the scores will be equal to the sum of the elements of the array. So in short, if X plus Y is equals to some constant which is the sum of the array, then maximizing X obviously means that you are minimizing Y. Since X plus Y is a constant, if you maximize X, then obviously you are minimizing Y. So player 1 tries to maximize his own score and player 2 tries to maximize Y. Since he is trying to maximize Y, this simply means that he's in the same, basically he's trying to minimize X. Since if Y is maximized here and X plus Y is a constant, then obviously if Y is the maximum possible value, then X has to be the minimum possible value, right? Because their sum is a constant. Alright, so we have this observation in place, and we'll try to play the game using these rules. We're playing the game with the rules in mind that player 1 is trying to maximize X, and X is player 1's own score, and player 2 is trying to minimize X, which is player 1's score. P2 tries to minimize X. Okay, so initially it is P1's turn. Okay, and we have the array A1, A2, AN. Okay, he has two options: either remove A1 and his score becomes A1, whereas the remaining array becomes A2 to AN, or he has the other option of removing AN, his score becomes AN, and we're left with the array A1, A2, and so on till AN minus 1. So which of the two options will player 1 choose, right? So player 1 will choose the option which leads to an overall higher value of X, right? So let's say if you go here, X will come out to be maybe some value small x1, and if you go to the right side, X turns out to be some value small x2. Okay, then he will choose the one option which leads to a higher X value. Okay, so we will choose the option in which basically if x1 is greater than x2, he will choose to remove A1, otherwise he will choose to remove AN, right? Now after this, okay, from here again we'll have two options for player 2: either remove A2 and we'll be left with the array A3 to AN, or remove AN and we're left with the array A2 to AN minus 1. Now what happens in this case is, here we'll not choose the better of these two options or the higher of these two options. Since this is player 2's turn, since at this moment player 2 is playing and he wants to minimize, so he'll be taking the smaller of these two options, right? So if this case leads to a value which is higher than the case here, he'll definitely choose the case in which the value is smaller, so he'll remove AN. Alright, so guys, hopefully the intuition here is clear to you, and now I'll be defining a term. Okay, so dp, let's just say dp of ij Yeah, so let's say dp of I comma j has the optimal score for player 1, that is the optimal value of x, in which so that we are left with the subarray I comma j. Okay, so dp of ij is simply the optimal value of x. X is player 1's score, optimal value of x, so that we're left with the subarray I2j. So if we're playing the game for with the remaining subarray I comma j, what is the optimal value of x, or what is the optimal score that player 1 can make? Okay, right, x is simply the score that player 1 can make, so that we're left with the subarray I comma j. Okay, now one thing here is that we need to know whose turn it is. Okay, so let's add another dummy variable here. Let's, instead of calling dp I comma j, let's call it dp of I comma j comma turn. Turn represents here whose turn we are at. Okay, so dp of I comma j comma turn, if turn is 1, then this means that we're left with the subarray of elements I comma j, and it is player 1's turn. Turn is a boolean variable, and if turn equals to 0, then this means we're left with the subarray from I to j, and this is player 2's turn. Okay, and of course player 1 is trying to maximize the score that he can get, whereas player 2 is trying to minimize the score that player 1 can get. So he tries to maximize x, whereas he tries to minimize x. Okay, now let's try to write a recurrence for dpij turn. So let's first of all write dpij comma 1, so that this means that it is player 1's turn. dp of ij comma 1 will simply be the maximum of the two options. So since player 1 is trying to maximize his score, so out of the two options he will choose the higher, right, the max of the two options. So the two options he has is, first he can get a score of ai, and then we'll be left with the subarray I plus 1 to j, and the turn has to be given to the other player, so this is 0. And the second option that he's left with is, he can select aj to be added to his score, and then we'll be left with the subarray from I to j minus 1, and of course the turn has to be given to the other player. Okay, and he'll choose the max of these two. So dpij1, so the recurrence for dpij1 is clear here. Let's just try and write a recurrence for dpij0 also. This means it is player 2's turn. Now since dpij0 is also simply representing the score for x, the score that the player 1 gets, so here the two options will be simply either the player 2 will get a score of ai, and they will move to the state I plus 1 comma j comma 1, or he takes score aj and move to the state dpi comma j minus 1 comma 0, and out of these two, the second player will choose the lower of them, because he is trying to minimize the score that player 1 can make. So here I have not added the plus ai and plus aj, because the scores are going to the player number 2, and dpij0 is simply representing the optimal value of player 1's score, so that we are left with the subarray I2j, and it is player 2's turn. And minimum of these two is chosen because player 2 is trying to minimize the value of player 1's score. So hopefully the recurrences are very much clear to you guys, and now we'll be moving forward towards the solution. Yeah, so yes, I've written this code already, and now I'll be removing these recurrences. Yeah, so here I've simply taken the input already. I've declared this dp array this will be storing the results as we have defined. Okay, and I've taken this vector v for getting the scores in the input. I've taken the number of elements in the array. This is a one based vector, and here this sum is the total sum of values in the array. Okay, since s, the sum, was equal to x plus y, as we saw, we'll be calculating score x, and then score y will simply be s minus x, and then we'll be displaying x minus y. Yeah, just a second. Okay, so hopefully this is clear. I'll add another dimension to my DP array, and later on I'll explain why this is not needed. Okay, yeah, so this dimension is simply to hold the turn. So initially I'm passing here v, the vector of the scores, and 1 comma n, the subarray I'm currently looking at. Currently I'm looking at the complete array, and 1 meaning that it is player 1's turn. Alright, so first of all, a base case, if the subarray is invalid, so let's say if I is greater than j, then this is an invalid subarray, and of course no score can be made by any of the players, so I'll be returning 0 here. Yeah, so I'll be returning a 0 here. After this, as we saw that depending upon turn there are two kinds of recurrences. So let's say also one thing here, if I've already seen this particular sub problem before, so if dpij at turn is not -1, that means if it is not an invalid score, then I'll be returning it there, since I've already solved this sub problem before. So return dpij at turn. Alright, otherwise if it's first player's turn, if turn equals to 1, in that case I have two options, and I'll be returning the larger of these two because it is player 1. So return max of the two options I have, and while returning also store it into dpij and turn. Okay, so the two options we had were either remove the ith element or remove the jth element. If I remove the ith element, I'll have a score of vi added to my total, plus I'll be reaching the following state. I'll be reaching the state in which I'm looking at the subarray from I plus 1 to j, and the turn will be given to the other player, which is simply player number 0. Yeah, so this is alright, and the other option I have is to remove the jth element, and in this case I'll be reaching the following sub problem or the following state. This is the subarray from I to j minus 1, since I've removed the jth element, and I'll be giving the turn to the other player. Okay, and choose the higher of these two. So this looks completely alright to me. And in the other case, in which turn was equals to 0, I'll be storing and I'll be returning the lower of the two possible options. Here I'll be using this to be min. Of course vi won't be added, since vi goes to the total of player 2 and we are looking at the score for player 1, so it did not get added. And I will solve. Okay, I plus 1, give the turn to player number 1 again. Vj is not added since it went to the total of player 2, and here give turn to the player 1. So alright, the code looks alright to me now. We'll be trying it on a sample test case and then we'll submit it. So let's try sample input 5. The output should be 2, right? Okay, so we're getting the correct output. Okay guys, there's one thing I'd like to mention is that this third dimension is not really needed. So I'll be commenting this out and submitting it, proving it to you that it is not needed, or let's just submit it this way and I'll just explain it to you why it is not needed. Alright, so guys, this code should hopefully work. Till then I'll explain the time and space complexities. So again, the space complexity here is big of n square. and n was up to 3000. So yeah, space complexity was n square, and again the transition time, any particular state depends upon only two other states, so transition time was O1. So overall my time complexity was also n squared, right? So space and complexity were both n square, and now I said that we don't really need this particular third dimension. This is because if you reach at a particular state I comma j, okay, if you reach at some particular state I comma j, you have removed the first 1 to I minus 1 elements. So you have removed a total of I minus 1 elements, and you have removed some elements from j plus 1 to n. So you have removed, let's say, a total of let's say some variable r equals to all the elements from n to j plus 1, so n minus j plus 1, something like that, right? So some r number of elements from the suffix have been removed, so a total of something capital R elements are removed, and initially to r, capital R equals to 0, which means no element has been removed and it is player 1's turn. So if r equals to 1, it is player 2's turn, right? Because one element was removed by player 1 and now turn goes to player 2, and since they were alternating turns, so whenever r is even, it is player 1's turn, whereas whenever r is odd, it is player 2's turn, right? So given any I and j, you could determine whether this particular r value is even or odd, and the turn is completely dependent upon I and j. So it is impossible to reach a state I comma j comma 1 if you have reached some state I comma j comma 0 in the past. Alright, so hopefully this thing is also clear to you why the third dimension wasn't needed. However, for simplicity and clarity, I've used it. So I'll just check if you're getting an AC. So yeah, we're getting an AC verdict. So guys, hopefully the problem was helpful to you, and I'll see you in the next video. Thanks for watching. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem M candies. Okay, so guys, you can go through the problem statement once on your own, and then I'll guide you through the problem statement and the solution to the problem. So in this problem there are n children and they have a total of k candies with themselves, and they like to distribute these candies among themselves. Okay, so there are n children in C1, C2 up to Cn, and we have k number of candies, and we would like to distribute it among these children in such a way that the first child gets candies anywhere from 0 to A1, the second child gets any candies either 0, 1, 2 and so on till A2, okay, and the last guy gets either 0 candies or at most an candies, right? So the last guy will get at least 0 candies or no candies, and at most an candies, right? So we are given with this array a1, a2 and up to so until an in our input, and what we would like to find out is the total number of ways in which we could distribute candies. Also the problem statement states that no candies should be left over, so we should be able to distribute all the k candies, and the constraint of 0 to ai must be followed for the ith child. So the ith child must receive at least 0 candies, that is no candies, and at most ai candies. So hopefully the problem statement is clear to you, and I'll explain one sample input now. Just a second. Okay, so you can see the input format here. We are first given the number of children and then the number of candies, and then we are given a1, a2 and an, which is the maximum candies a child should get. Okay, basically the maximum candies that the ith child can get. So guys, you can go through the sample input. Here we have 3 children, C1, C2 and let's say C3, and C1 can get at most 1 candy, C2 can get at most 2 candies, and C3 can get at most 3 candies, and at least anyone can get no candies. Okay, right? So we have a total of 4 candies, and we'd like to find out what is the total number of ways in which we can distribute. So as you can see, they have provided a very nice explanation here. So there is a way in which I could give 0 candies to the first child, 1 candy to the second child, and 3 candies to the third one. In this way all my 4 candies are used up, and the constraint is also followed everywhere. Okay, same way 0 2 2 follows the constraint, 1 0 3 1 1 2 and 2 1 2 1. So overall my answer is 5. Also I'll show what cases are invalid here. So a case like 2 2 1 is invalid because, just a second, a case like 2 2 0 is invalid because child 1 is getting more than 1 candy and he should have received at most 1 candy. Therefore a case like this should not be counted, it is invalid. Also a case like 1 2 and 2 is invalid because here we have distributed more candies than 4, a total of 5 candies, so this is also invalid. Also another case, let's just consider 1 1 and 1. This case is also invalid, we should not be counting this, even though we could distribute the candies, but we'll be left over with 1 candy as we have distributed only 3 of them, and the question asks us to distribute all the candies. Okay, so this is also invalid. So hopefully the problem statement is now clear to you. Let's just look at another sample input. So here there is just one child and we have 10 candies, and this child can receive at most 9 candies. Since it is impossible to distribute in any way so that all candies are also distributed and this child gets only less than equal to 9 candies, no such case can exist, so our answer is 0. Okay, alright, so you can go through these other sample inputs as well if you'd like. Also, since the number of ways can be very large, we should print our answer modulo 10 to the power 9 plus 7. So guys, now I'll be moving forward towards the solution. Alright guys, so we're solving the problem M, that is candies. So we're solving M candies. So guys, we'll now think of the solution. So the problem says that there are n children and we wish to find the number of ways to distribute candies among these. Okay, so there will be a case in which the nth child will get 0 candies. Okay, there will be many ways in which the nth child gets 0 candies, and there will be many ways in which the nth child gets 1 candy, and so on till an, right? An is the maximum he could get. So we need to count all such ways, okay, in which the nth firstly I'd like to calculate all the ways in which the nth child is getting 0 candies. Then I would like to calculate all the ways in which the nth child is getting 1 candy, and so on up till a of n. Okay, so I will think about the last child, right? I will say, okay, let's give him 0 candies, and my problem will reduce down to the first n minus 1 children and finding what is the total number of ways to distribute exactly k candies among the n minus 1 children. Is it right? Because let's say if there exists some ways in which I could distribute exactly k candies to the first n minus 1 children. Okay, there exist some ways, some x number of ways in which I could distribute k candies to the first n minus 1 children. Then in all these x ways I could give the nth child 0 candies, and then these ways can be counted while I am distributing k candies for all the children, right? Same way, if I give the nth child 1 candy, then if I am able to find out what is the total number of ways in which I could distribute k minus 1 candies, among the first n minus 1 children, the number of ways to do this, then simply all these ways can be extended to k candies and n children by giving one candy to the nth child, right? So we can see that we'll be able to basically decompose our problem into smaller sub problems, right? So hopefully this is giving you some intuition, and we will now be moving forward towards the solution. So let me define dp of I comma j as the number of ways to distribute j candies among the first I children. So it's the number of ways to distribute j candies among the first I children, among children 1 to I. Okay, so now we have defined dp of ij, and according to the problem statement we would like to find out dp of nk, right? So we'll think of a way to relate dp of nk with smaller states, and we'll think of a base case, and then we'll be able to come up with a solution to the problem. Okay, so let's think dp of nk. dp of nk is the number of ways to distribute k candies to the first n children, right? So let's think about the nth children, or the nth child basically. So the nth child can get from anywhere from 0 to an candies, right? So let's say I give the nth child 0 candies, then I'm left with the first n minus 1 children and k candies. Okay, so the number of ways to do that can be added to dp of nk, because all those ways can be followed up by the nth child getting 0 candies, right? So dp of nk will be at least as large as dp of n minus 1 comma k, because all these ways can simply be followed by giving the nth child 0 candies, and then we have distributed k candies among the first n children. Okay, then I could decide to give one candy to the nth child, and in that case all the ways in which I could distribute k minus 1 candies to the first n minus 1 children will also get added to dp of nk, right? Same way, if I give 2 candies to this child, the nth child, then I will be left with k minus 2 candies for the first n minus 1 children, and plus so on till if I give this child an candies, then I will be left with the first n minus 1 children, and I'd like to distribute k minus an candies among them. So guys, as you can see, there is a recurrence available to us now, and I'll be writing it in a more succinct form. So dp of ij will simply be either give this child 0 candies or give this child 1 candy, 2 candy, and so on till ai candies. And as we saw, dp of ij will be dp of I minus 1 comma j minus, if I give this child x candies, then I am left with j minus x candies for the first I minus 1 children, and then I have to sum all these from x goes from 0 up till ai. So guys, hopefully this thing is clear to you. I've simply wrote it in the summation format instead of the expanded form. Okay, now let's think of a base case. So what if there is just one child and we'd like to give him some x number of candies? So maybe dp of 1 comma x, or let's just take dp of 1 comma j. There is just one child, or the first one children, or the first child in fact. Then what are the number of ways to give him j candies? Okay, So if j is less than equal to a of 1, then there is one way, give all the candies to the first child, and we have one way to do that, given that j is less than equal to a of 1. But if j is greater than a of 1, then there is no way to distribute all the j candies, right? Because then even if I give the first child the maximum candies that he can get, that is a1, I'll still be left with some candies, and the problem asked me to distribute all the candies, so I don't have to count such ways in which candies are left over. So we have a base case now, right? So now I can move towards the implementation. However, let's look at the constraints of the problem and the time complexity in which we have solved the problem right now. Okay, so guys, as you can see that n is up to 100 and k is up to 10 to the power 5. Now what is the time complexity here? So you might be mistaken that the time complexity here is n into k, but it is not. Let's see how. So space complexity here will be big of n into k, the space complexity, because I'll be declaring a dp table to store my results, and the number of states I can be anywhere from 1 to n and j can be up to k. So overall space complexity will be big of n into k, but my time complexity will not be big of n into k, because for every state this loop will be running up to ai, and ai can be up to k. So my transition time here is big O of k and not big O of 1. So overall the number of states are n into k, and the transition time for every state is big O of k. So my time complexity is big O of nk squared, right? And since k is up to 10 to the power 5, this solution will definitely time out, right? So we need to think better. So this is a very good problem to learn a very basic optimization to dynamic programming. Okay, so we saw that let's say dp of I comma k, we see that dp of I comma k depends upon the following states. Depends upon I minus 1 comma k when I give the ith child 0 candies, and it depends upon I minus 1 comma k minus 1 if I give the ith child 1 candy. Same way it depends upon I minus 1 comma k minus 2, and so on. It also depends upon I minus 1 comma k minus a of I when I give the ith child I candies. Okay, so overall dp of ik was the sum of all these states, right? Now let's think what I comma k minus 1 depends upon. So I comma k minus 1 depends upon the following state. It depends upon I minus 1 comma k minus 1. It depends upon I minus 1 comma k minus 2, or I could, let's say, write it as k minus 1 minus 1, because I'm giving the ith child 1 candy here, and I had a total of k minus 1 candies. So for the first I minus 1 children, there are k minus 2 candies available, and so on. It finally also depends upon I minus 1 comma k minus 1 minus ai, right? So what we can see that is ik was the sum of these states, and I comma k minus 1 is the sum of all these states. Here the states starting from here till here are common, right? These states are all common. This state was extra here, whereas for I comma k minus 1 all the states till here are included in I comma k as well, except for this state, right? So what I could do is I could use dp of I comma k. Once I've already evaluated dp of I comma k, I could use its result to evaluate dp of I comma k minus 1 in a more efficient manner. I could use this exact same result, and I could remove this particular entry, because I comma k minus 1 does not depend upon that entry, whereas I comma k was depending upon it. So I can subtract this from I comma k minus 1, whereas I could add this entry to I comma k minus 1, and then I'll be able to evaluate I comma k minus 1 in big O of 1, given that I know dp of I comma k. So I'll write a formula and it will be very much clear to you what I'm trying to convey here. So let's say I have dp of ik, then to calculate dp of I comma k minus 1, I could say that it is equal to dp of I comma k minus this one state, which is dp of I minus 1 comma k, plus this one extra state, which is dp of I minus 1 comma k minus 1 minus a of I. So guys, with this I'll be able to calculate this one particular state in big O of 1, and then my transition time reduces from big O of k to big O of 1, and my overall time complexity will become big O of n into k. So guys, hopefully this must be clear to you, and if you still have some doubt, it will be clear to you while we'll be implementing the code. But before I move towards the implementation, I'd like to mention here that in my code, like I said, if I know dp of I comma k, I can quickly evaluate I comma k minus 1. In my code, I'll be knowing dp of I comma k minus 1, and then evaluating dp of I comma k. I'll quickly write a recurrence for that as well. So let's say I know dp of I comma j, and I wish to calculate dp of I comma j plus 1. Okay, I know dp of I comma j and I want to calculate dp of I comma j plus 1. Then this will be simply dp of I comma j, right? And one extra state that dp of I comma j plus 1 depends upon is dp of I minus 1 comma j plus 1, and one state on which dp of I comma j depends but dp of I comma j minus 1 dp of I comma j plus 1 does not depend upon is, so dp of I comma j also depends upon I comma j minus ai, whereas I comma j plus 1 does not depend upon this state. The lowest state it depends upon is I comma j plus 1 minus ai, right? So I'll be removing dp of I comma j minus ai. So guys, I'll be using this recurrence in my code, and now we'll be moving towards the recurrence, moving towards the implementation. And now I'll be erasing this. Okay, so here I've simply written some basic code taking the input and stuff, and now we'll be implementing the solve function as always. So you can see that I've taken the input as the number of children here is n, the number of candies I wish to distribute is k. This is a one based vector in which I'll be storing the maximum number of candies that can be given to the ith child, and then I'll be calling the solve function with the vector, the number of children and the number of candies to get the result, and I'll be printing it simply. Here I've taken this integer solve. This integer returns basically this solve returns the number of ways to distribute the candies, and we'll be implementing this now. Okay guys, so I'll be implementing this bottom up, and so as discussed, I'll declare a dp array to store my results. So let's just take LLDP so that we don't make any mistake due to any possible overflow, even though we are taking modulo at every step. So I'll say n plus 1 and maybe yeah, sure. So I'm taking an n into k array, and first of all we'd like to write the base case, or basically fill the base conditions. So for I'll be filling dp of 1 comma x, so integer x goes from 0, let's take it to be j, the number of candies I want to distribute to the first child. J less than equal to the total number of candies that I have, that is k, and j plus plus. So I'll write dp of 1 j equals to, so if the number of candies I'm going to give to the first child is greater than the maximum he could get, so if j is greater than a of 1, if this is true, then there is no way to do this, otherwise there is one way to do it. Okay, so hopefully the base case is clear. Now I'll be evaluating for the first I children. So for the first, considering the first I children, and I goes from 2 to n, I want to distribute, just a second. So for the first I children, I'd like to distribute j candies among them, and integer j can go from 0 up to k, which is the maximum number of candies I have, and j plus plus. Okay, so now as we discussed, so first of all, if j is 0, if j equals to 0, then I have 0 candies in hand, and my dp of ij will simply be dp of I minus 1 j, right? Because I could only give 0 candies to this particular person, since I have a total of 0 candies. Otherwise, else dp of ij, I use the previously calculated value, that is dp of I comma j minus 1, and we say that yeah, we need to add one value to this, which is dp of I minus 1 at j, because dp of I j minus 1 did not depend upon I minus 1 j, the dependency started from I minus 1 comma j minus 1. So we will have to add this value, whereas we'll have to subtract the value dp of I minus 1 and j minus the maximum candies this per ith guy can get, which is vi. So we'll have to subtract j minus vi minus 1 from this, right? Of course that this thing should be positive, in fact greater than equal to 0. So if this thing is greater than equal to 0, if it is greater than equal to 0, then remove the state from dpij, because dpij does not depend upon it, but I comma j minus 1 did depend upon it. So I have to remove this thing. Otherwise, both of these states depend upon this particular state, and then I remove nothing, so I put a 0 here. Alright, so guys, hopefully that thing is clear to you. And after these loops, I should have my answer at dp of n, that is thinking about the first n children and distributing k candies among them. Alright guys, so hopefully this code should work. I will be trying out a sample input. Oh, just a second, before we try out anything, we need to make sure that we take modulo at every place, otherwise we'll get an integer overflow error. So I'll be taking mod. Here I have defined mod as 10 to the power 9 plus 7. So yeah, with this the code should work properly now. Just a second, I'm also subtracting this thing here. So what if this thing becomes negative? So there is a possibility that after subtracting this thing becomes negative. So what I'll be doing is I'll be adding mod to this all. Now it cannot go negative, because all these values are smaller than mod, definitely smaller than mod. Okay, and since I am taking modulo mod, so overall effect is 0, but I am keeping things positive in the intermediate situation. Okay, so let's try the sample input, maybe this one, or is there some better input? Maybe let's try this one. Just a second guys. So I cannot see anywhere run option. Just a second, let's just save it as code. Like, shouldn't there be run option somewhere else? Alright, so now I'm getting the run option. I'll run it. Thankfully the code is still there. The output should be 5 and A was not declared in the scope. This one should be V. Alright, so I'm getting the correct output. Let's try and submit. And as always, I'll discuss the time and space complexity once again. Although we had discussed it already, space, as you can clearly see, is n into k here, and time complexity is again n into k because we have used our optimization. Otherwise, our time complexity was n square into k, right? So yeah, this code got an AC. So guys, hopefully the video was helpful to you, and I'll see you in the next video, guys. Thank you for watching. And in this video we'll be solving the problem in slimes. Yeah, so you can go through the problem once on your own and then I'll be explaining it to you. So we're given n slimes in a row, okay? So slime number 1, slime number 2 and so on till slime number n. Slime is any thick liquid substance and these slimes are lined up in a row from the first one to the nth one. Now what we would like to do is we would like to combine all these slimes into a single slime. Just a second. Okay, so we'd like to combine all these slimes into one single slime. However, to do this, there is just one kind of operation that can help us, and the operation is to take any of the two current adjacent slimes and combine them into one slime. So let's say if some slime of height x and slime of height y are adjacent to each other, I could combine these two into a single slime, and this new slime will be of height x plus y, and a cost will be incurred to combine these two slimes, and that cost is also equal to x plus y. Alright, so basically a cost incurred will be the cost of the will be equal to the height of the newly created slime. Okay, so hopefully the problem statement is clear. If it is not, it will be clear once you go through a sample input. So you can see the sample input format. So the format is that we'll be given a number n, which represents the number of slimes, and then we'll be given a1 to an, which are the heights of the n slimes, and in the order in which they are kept. Alright. Okay, so we'll look at sample input 1 now. So we have the slimes 1, 2, 3 and 4. Okay, so in the first operation I can choose to combine the slimes of height 1 and 2 with each other as they are adjacent, and I reach the following state. In doing this, a cost of 3 is incurred since the newly created slime is of height 3. Okay, next step, I could maybe again combine these two slimes, 3 and 3 heights, to get a slime of height 6, and I reach the state. To do this, a cost of 6 is incurred, which is the height of the new slime created. Again, I could finally combine these two left slimes to get a single slime of height 10, and a cost of 10 is incurred. So overall, 10 plus 6 plus 3 equal to 19 is the overall cost as shown in the sample output 1. So they had taken 10, 20, 30 and 40 as the sample input. I have taken 1, 2, 3 and 4, and that is why my output is 19 instead of 190. So guys, if you'd like, you can go through the sample input 2 as well. I'll just show you one other way of combining these slimes in which the answer is greater than 19, so that the problem is clear to you. Okay, so let's say I had 1, 2, 3 and 4 and I had combined them this way. So a cost of 7 incurred here, then I combine 2 and 7 maybe to reach this state, and a cost of 9 gets incurred here, and finally I combine these two and a cost of 10 gets incurred here. So overall this time the cost is 26, which is worse. So this proves that there is one good way of combining, or maybe there are more good ways of combining. We just have to find the best possible way in which the cost is minimized. So at the end we are going to get a single slime whose height is the same as the sum of all the heights of each and every slime. However, we would like to combine them in such a way that the cost of combining all the slimes into one is minimized, the overall cost. Okay, so guys, now I'll be moving towards the solution. Hopefully the problem statement is clear to you. If you'd like, you can go through the sample input, other sample inputs as well. Yeah, and like sample in output 3 says that yeah, we'll have to use long instead of integer. So I'll be moving towards the solution now. Okay. Yeah guys, so we're solving problem in slimes. Okay, so to combine all the slimes into a single slime, all the slimes from S1, S2 to Sn into one single slime S, we'll be doing some number of operations, n-1 operations to be exact. Okay, in one operation 2 slimes become 1. Overall in n-1 operations all the n slimes become basically converge into a single slime. There will be some good way of combining all these slimes, isn't it? So let's say that the good way is the way in which the overall cost to combine all these slimes into a single slime S is the minimum possible. And then let's think what will be the final move in our good way. Okay, so there will be one final move in which two slimes, we are given with 2 slimes, and these 2 slimes become our final slime, isn't it? So to get S, we would have 2 slimes, Si and maybe Si plus 1, and we'll be combining these 2 into a single slime. So if I could guess what is the final move that is taking place, then I could try to find out the overall minimal cost. Okay, so of course this operation, the cost incurred will be simply the height of this final slime, which is the sum of the heights of each and every slime, which is, let's say, sum of 1 comma n. Okay, sum of heights of all the slimes from first till the nth. Right, now what is the final move? I have to think. So in the final move I'll be combining 2 slimes, that is for sure, and one of these slimes is made out of a prefix of the n slimes and the other slime. So we have 2 slimes which are going to be combined to get our final slime S, and this slime is made out of a prefix of the n slimes, whereas this is made out of the remaining slimes or a suffix of the slimes. Isn't it right? Because if you're combining 2 slimes, this one has to be made out of some slimes of 1 to I, whereas this has to be made out of the remaining slimes from I plus 1 to n. So guys, hopefully you're getting some intuition here. Like, we are sure that to get the final slime, we are combining a prefix of slimes from 1 to I, and we are combining the remaining slimes from I plus 1 to n into a single slime that represents our entire range of slimes. Right, here to combine these, a cost of sum 1 comma n is getting incurred, and if I knew what is the cost needed to make this particular slime and the cost needed to make this particular slime, I could simply add these two values to sum of 1 comma n and get the minimum possible cost of making the slime, making the single slime that represents the range 1 to n using if I combine the prefix 1 to I with the suffix I plus 1 to n. Okay, so guys, now I'll be making this intuition more concrete and then we'll be moving towards the solution. Alright, so let me define dp of I comma j as the minimum cost to combine all the slimes in the range I to j into a single slime. So I'm defining dpij as the minimum cost to combine all slimes in range I to j, all slimes from I to j into a single slime, right? Into one slime. So once I've defined this, we know that we would like to find out dp of 1 comma n, which is the minimum cost to combine all the slimes in the range 1 to n into a single slime, right? So we'd like to find out dp of 1 comma n. And as we saw that dp of 1 comma n, basically combining all the slimes into a single slime, all these operations will be accompanied by the final move in which we combine a prefix 1 to I, with the remaining elements from I plus 1 to n, right? Here this I can vary from 1 to n minus 1. So basically the final move could be either combine the first slime from 1 to 1 and the slime from 2 to n, or the slime from 1 to 2, something like this, from 1 to 1 and 2 to n, and combine these to get a single slime. Or I could have the slimes from 1 to 2 as a single slime and the slimes from 3 to n as a single slime, and then combine these two slimes. So overall I could choose any I and I could combine the slimes 1 to I and I plus 1 to n, where my I can be anywhere from 1 to n minus 1. So guys, hopefully this thing is clear to you, and overall I'd like to find out dp of 1 comma n. Now I'll move forward towards writing the recurrence and the solution to this problem. Also I'd like to discuss a simple base case. So dp of I comma I will simply be 0. Since there is just one slime, then because it is already combined into a single slime, I do not need to do any further operation, and dp of I comma I is 0. Now let's move towards writing the recurrence. Okay, so we wish to calculate dpij. Now the minimum cost to combine all the slimes from I to j. Even for this, there will be one final move, in which we will be combining two slimes, and one of the slimes is made up of all the slimes from I to I plus k, right? From I to I plus k, and the other slime is made up of all the slimes from the range I plus k plus 1 to j. Is it right? Because in the final move we'll be combining two slimes, exactly, and this k can be anywhere from 0 to, let's say, like this particular term has to be less than j or less than equal to j. So I plus k plus 1 has to be less than equal to j, and k can be at most, k has to be less than equal to k has to be less than equal to j minus 1 minus I. So its basic idea is that select a prefix of slimes and a suffix of slimes and combine them into a single slime and see what is the minimum cost to do so. Alright, so I can now try and write my recurrence. So let's say that the best move was to combine basically the final move was to combine the first k slimes and the remaining slimes into a single slime. So basically the best thing to do was take the firstly combine the slimes from I to I plus k in the best possible manner and obtain a single slime, and then combine all the slimes from I plus k plus 1 to j and combine them into a single slime in some way so that the cost to do so is minimum, and then finally combine these two slimes to get a single slime that represents all the elements or all the slimes in the range I to j. So the cost to combine these two slimes is basically the sum of the heights of these two slimes. So basic idea will be, or in short, it will be the sum of I to j, right? It will be sum of all the elements in the range I to j, because the height of the slime is going to be the sum of all the slimes, and that is the cost incurred to make this slime, plus what is the minimum cost to make this slime, and what is the minimum cost to make this slime. This will simply be dp of I, I plus k plus dp of I plus k plus 1, j, right? Or what I could do is I could write dp of I, k, that is the range I to k is one slime, and here I could write k plus 1 to j, right? So that k plus 1 to j is one slime, so I selected a prefix and suffix and combined them into a single slime. And of course this k can be anywhere from 0, not 0, k can be anywhere from I to j minus 1, okay? And I'll be selecting the best option out of all these possibilities. So yeah, so we have a recurrence now, and we'll be choosing dpij using all the valid values of k and whichever gives me the minimum, right? The minimum possible cost to combine all the slimes from range I to j into a single slime. So hopefully this recurrence is now clear to you guys. We'll discuss a base case and we'll move towards the implementation. So what is the cost to combine all the slimes in the range I to I? This is simply 0 because it is already a single slime. Okay, so guys, now we will be moving towards the implementation, and if some part is not clear, it will be clear while implementing. So yeah guys, as discussed, we'll be implementing a recurrence, and as we saw that we need sum of I to j elements as well in our recurrence, so let's calculate that also. So let's keep ll sum, and the sum will be storing all these sums. Basically sum of ij will represent what is the sum of heights of all these slimes in the range I to j, okay? Yeah. Here I've taken the input, n is the number of slimes, then I've declared dp to be -1, and then I've taken a 1 based vector which will be storing the height of the slimes, and finally I'll be outputting what is the minimum cost to combine all the slimes in the range 1 to n. Okay, so here, as we discussed, we'll discuss a base case. If I is equals to j, then I should return 0 because it is already a single slime and no operation needs to be done. If I've already solved this problem before, then dp of ij will not be -1, and I'll return it. Okay, otherwise I have to solve the problem, and as we discussed that dp of ij is either combine the first k slimes into 1 and the remaining slimes into 1 and then combine these two slimes into a single one. So basic idea was take first k slimes from I to I plus k, and then take the remaining slimes from k plus 1 to j, maybe from I to k and from k plus 1 to j, and combine them into a single slime. And this k had to go from I to j minus 1, and I'll be simply implementing the same thing here in code. So we like to find the minimum cost to combine all these slimes into a single one. Then my k goes from, for integer k goes from I, and k should be less than j, k plus plus. Okay. Let's keep a variable dll min cost and initialize it to maybe some very large value. The height of the slimes can be up to 10 to the power 9. This is 400. I'll define infinity to be something very large that is greater than 10 to the power 12 or 13. Okay, so I'll define infinity to be 2 to the power maybe 60. This is quite a large value. Yeah. Now if I take the first I to k elements as the prefix or as the first slime to be combined, then my cost will be sum ij plus the minimum cost to combine all these slimes from the range I to I plus k plus the cost to combine the remaining slimes into a single slime. Right. So this looks alright to me, and whatever this cost comes out to be, if it is less than the minimum cost till now, I'll select this to be the minimum cost. Alright, so min cost is basically the minimum cost to combine all these slimes from I to j, and dp of ij simply becomes equal to min cost, and then I can return this value. Yeah, so this looks alright, except that I haven't calculated sum till now. Now I need to calculate this sum array as well, so let's make another function void preprocess. Here I can pass simply the vector int v. This will help me calculate the sums array. Yeah, so first of all, okay, for every integer I goes from 0 to less than, in fact from 1, less than equal to n I plus plus okay. So guys, this is simply a pre-processing step building up the sum array, and sum at ij will be equal to the element here. I am currently sum at ij is basically the sum of all the elements from I to j. Add the jth element vj plus sum at I to j, basically the sum from I to j minus 1. And yeah, here j should not be equal to I. If j is equals to I, then 0, otherwise sum to I to j, sum from I to j minus 1. And I guess this pre-processing step should correctly calculate my sum array as well. Alright, so looks alright to me. Let's just try a sample input. So output should be 68. Okay, I haven't called preprocess. Alright, so I'll test the sample input now. Guys, this code works in big O of n square preprocessing. Okay, I'm getting the incorrect output. I'll just check why. Maybe something with the sums array. Alright, so yeah, so guys, the problem here was that I have sent it for pre-processing before taking the input, right? And after doing that, the output is correct and it is giving me the output to be 68. Alright, so let's just try and submit and see if it works. So guys, hopefully the video was helpful to you. This code should hopefully pass. Till then, let's just quickly discuss the time complexities. Okay, the space complexity here is big O of n squared, as I've taken two arrays. This pre-processing works in big O of n square. This is also dynamic programming. I've used sum ij is equals to the element at the jth position plus the sum of the subarray I to j minus 1. Okay, and this code, so many will make a mistake here. This code, they'll say that this works in big O of n square. However, here the transition time is not big O of 1, but it is big O of big O of n. So overall it is n square states into the transition time. So it is big O of n cube here. Okay, so time complexity is big O of n cube, and since n was up to 400, so time it should pass, right? Yeah, so we are getting an AC. So I'll see you in the next video, guys. Thanks for watching. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem O, that is matching. Okay, so you can go through the problem once, and this is a really nice problem, and hopefully with this problem you'll be able to learn a new concept, a new DP concept, a technique basically. Okay, so in this problem what we are given with n men and n women. So m1, just a second. So basically n men, man 1, man 2, and so on till man n. So we are given with n men and n women, w1, w2, and so on till wn. Okay, so what we would like to do is we would like to make n pairs. Okay, we want to make n pairs, and each pair consists of one man and one woman. Okay, we would like to find the number of ways to make n pairs. However, a constraint must be followed. Whenever we make a pair of, let's say, the ith man and the jth woman, man I and woman j must be compatible with each other, and we are given the compatibility matrix which tells us whether this particular man I is or is not compatible with the woman j. We'd like to find the number of ways in which we could make our total n pairs. So if the problem statement is not clear, it will be clear after we go through a sample input. So okay, so also you can look at the constraints. The constraints are very much small. N is only up to 21, and aij simply tells whether man I is compatible with woman j or not. So 0 if not compatible, 1 if compatible. You can also see the input format. So let's see the sample input one. So we wanted to make n pairs. So there is one way, they have shown us 3 ways to make the pairs, and therefore our answer is 3. The total number of ways in which n pairs can be made is 3. So one pair is 1, 2, 2, 1, and 3, 3. You can see in the matrix that the entry at the first row and second column is 1. Same way the entry at second row and first column is also 1, and again 3, 3 is also 1. Therefore this is a valid pairing, whereas I'll show you what an invalid pairing will be. So let's say I make the pair 1 comma 1 and 2 comma 2 and 3 comma 3. This is an invalid pairing because the first man and the first woman are incompatible with each other, therefore this is invalid. Also the second man and the second woman are also incompatible with each other, therefore this is not a valid way to make n pairs, therefore our answer is 3. Okay, since there were 3 ways. Let's look at the sample input 2 as well. So this is comparatively larger way, and they have shown that there is just one possible way to pair all the men and women with each other, or basically to make 4 pairs, and the way is shown. Again, in the sample input 3, the input is just one man and one woman, and both the man 1 and woman 1 are incompatible with each other, so there is no way we can make one pair, therefore output is 0. And sample input is quite a large input, which is basically there to show that we have to print our answers modulo 10 to the power 9 plus 7. Okay, so guys, hopefully the problem statement is now very much clear to you, and we'll be moving forward towards the solution. So guys, we are solving problem O, matching. Okay, so in this problem we'll first of all think of a brute force solution. Okay, we'll try to think of a brute force solution, and then we'll use dynamic programming to optimize it further. Alright, so guys, initially we have n men and n women, and we would like to make n pairs, and basically we'll find out the number of ways to pair, or basically the number of ways to make n pairs, right? So in a brute force manner, what I could do is I could take the first man and I could pair this guy with the ith woman, okay, such that the compatibility matrix C of 1 comma I should be equal to 1. That means first man and ith woman should be compatible, and then I can find the number of ways in which I can make n minus 1 pairs. Okay, the number of ways in which I could make n minus 1 pairs for all the men from 2 to n and all the women except the ith woman, because the ith woman has been paired up with the first man, right? So hopefully you are getting an intuition for a brute force solution. We'll basically be generating all the possible, we'll basically be calculating all the possibilities, and whenever we are able to make exactly n pairs, I'll be counting that possibility into my answer. Okay, so if I make n pairs, then answer plus plus. Okay, this in short means that when I reach the last man, if there is still a woman available to me which is compatible with the nth man, then I will be adding 1 to the answer. Okay, and for the first man, I will try to pair him with all the women with whomever he is compatible with, and I will recur for the remaining woman and all the men from 2 to n. So guys, hopefully the brute force idea is a little bit clear to you. Even if it is not, we will move towards a better solution which involves DP. Okay, yeah, so even if the brute force is not clear, you don't need to worry. The thing is that the DP solution should be clear to you. Okay, so now I have n men, and currently I have all the women from 1 to n. So let's say I represent their availability by a 1, and unavailability by a 0. Okay, so initially I wanted to find the number of ways to make n pairs such that I have all the men from 1 to n and I am available with the women's 1, 2, 3 and so on till n. Okay. Now in any of the ways, the first man will be paired with some jth woman such that compatibility matrix C at 1 comma j is equals to 1, right? Now let's say I make this pair. Now I am left with all the men from 2 to n and all the women except the jth woman. So I'm left with the women 1, 2, so on till j minus 1, and then from j plus 1 to n. Basically I'm left with a subset of these n women's and a subset of these n women except the jth woman, right? Okay. And I would like to find the number of ways to make pairs of these men from 2 to n and all the women except the jth woman, right? So if I knew the answer to this, then I'll have the number of ways in which I could pair all the men from 1 to n such that man 1 is paired with the jth woman. Okay. Then again I can try and pair man 1 with some other woman whomever he is compatible with, and then I could recur for all the men from 2 to n and a subset of women which contains all women from 1 to n other than the woman who one got paired with, because that woman will no longer be available for pairing with the men from 2 to n. Alright. So with this idea in mind, I'll define the term dp of I comma x. So I will define dp of I comma x as the number of ways to make valid pairings, okay, when I am available with the ith man to the nth man. So I have all the men from I to n, man I plus 1, man I plus 2 and so on till man n, and I have the women that are represented by the set x. So number of ways to make valid pairings of man and woman, make valid pairings of man and woman such that all the men from I to n are available and the woman represented by the set x are available, and women represented by set x are available. Okay, so here you can see that x is a set, okay, and I want to find dp of ix, the number of ways to make valid pairings so that all the men from ith till nth men are available and the women which are represented by the set x are available to me. So initially I would like to find out, okay, I'll be erasing this right now and you can just have a look at what dp of ix stands for. Yeah, so what I am actually wanting to find out as per the question is dp of 1. So 1 meaning that all the men from 1 to n are available, comma s or maybe w, let's say w. Here w is a set and w equals to 1 comma 2 comma 3 comma so on till n, because initially all the women from 1 to n are available. Okay, so now I have defined dp of 1 comma w, and I would like to calculate dp of 1 comma w through some maybe recurrence. Okay, so as we discussed, now the first man could be paired with any woman in the set w such that compatibility at 1 comma the woman I am pairing with, let's say x, the xth woman, then this should be equal to 1. Okay, so I can write a recurrence for this. So dp of 1 comma w will simply become, if I pair the first man with the xth woman, okay, I'm pairing the man number 1 with the xth woman, of course c of 1 comma x equals to 1. Then once that pairing is done, I would like to find out all the number of ways in which I could make valid pairings so that all the men from 2 to n are available and all the women in the set W are available except the xth woman. Okay, so dp of 2, all the men from 2 to n are available, and all the women in the set W are available except the xth woman, because I just paired the xth woman with the first man and summed over all the valid x. So C1x equals to 1, compatibility of first man and the xth woman is equals to 1, and x belongs to W. So guys, hopefully this recurrence is clear to you, and with this recurrence we can move forward towards a better approach and basically a way to implement this. We have to discuss how we can implement this. Okay, so first of all, you can just look at the recurrence, and hopefully this must be very much clear to you. I'll also be doing it on a sample input so that it gets more clear. So let's write dp of I comma the set x. So dp of I comma x is simply equal to pair the ith man with any woman x, small x, available in the set capital X, such that C of I comma x is equals to 1, and then find the number of ways to pair all the men from I plus 1 to n and all the women that are represented by the set X minus the woman I am pairing with the ith man. Okay, so this is simply equal to summation C of I comma small x equals to 1, x belongs to capital X, and summation dp of I plus 1 comma capital X minus small x. Right, so guys, hopefully this thing is clear to you. Now how do we implement this thing? Okay, now X is a set. Till now we have dealt with integers, and basically we have dealt with integers as in the index of our dp table, but here our dp table one dimension is a set itself. Okay, so one way to deal with this is that instead of having an integer dp and then 2 dimensions, what I could declare is I could declare a dp map. Okay, so I could have something like this, a map of where the key is an integer comma a set. Okay, my key is an integer and a set comma the value related with this pair I comma x, this is I and this is the set x, is the answer, and I could store my values in this type of data structure. Right, this is absolutely correct, there is no problem with this. However, using a map is again a little slower, and we could make things even more faster. Now let's discuss a good approach to representing sets. Okay, so let's discuss an efficient way of representing a set in C++. Okay, so first of all, I could represent any set in which my numbers are in a limited range. So I know that initially my woman set was 1, 2 and so on till n, and after some time it will be a subset of this set. Okay, so one way of representing this is I could represent it using a boolean array, and if the ith woman is still in the set, then let's say I'm representing my set as bool set and n, and I could say that yeah, if set at I equal to 1, then the ith woman is still in the set, and if set at I equal to 0, then the ith woman is not in the set. So initially my set will look like this. All my integers will be 1 because initially all women are present, and let's say I paired the first man with the fourth woman, then my set will become, for the next call, my set will look like this. All the other women are still available, the fourth woman is not available anymore, and my set looks something like this. Right, so this is a really good way of representing basically a set in C++ by using a boolean array of zeros and ones. 0 meaning that this particular woman is not available, this particular element is not available in the set, and 1 meaning that this element is present in the set. But still this does not solve our problem. Our problem was that dp of ix, one of the dimension is integer, and it's cool that I could use the operator. Basically I could use the square bracket operator and write the integer here, but again the other is still an array, so I'll still have to use a map or something. But the thing here is, in C++, integers are stored as boolean, basically in their binary values, right? So an integer is nothing but a 32-bit string, or you can say it's a 32-bit value. Okay, so a computer stores the value 1 as something like this. Okay, it stores a 2 as this, and hopefully you are clear with this concept. So what we could do is we could use an integer to represent our set, right? So initially when we have n women and all the women are available in the set, then I could use an integer whose binary is basically 111. So I could use an integer to represent my set, and initially all the bits of that integer will be 1, meaning that all the women are currently present in this set. Okay, so now what we're doing is we are using an integer x to represent our set, and if the ith bit of x is on, then that means that the ith woman is still available for pairing, and if the ith bit of x is off, then the ith woman is not available for pairing. All right, so guys, like if initially all the women are available, then my number should look something like this, and there should be like n ones, right? So if n equals to 5, my number will be this. Okay, so what I'll do is, this is basically nothing but 2 to the power 6 minus 1. Okay, yeah, or I think 2 to the power 5 minus 1, like 1 itself is 2 to the power 0, and 1 0 is 2 to the power 1. Then yes, I guess okay, so this will be 2 to the power 5 minus 1, right? So initially what I could do is I could generate the number 2 to the power n minus 1, and that represents the set of women available to me, and then I could use this integer to represent my set, and finally my dp of I comma x can be made up as a table in which both the dimensions can be indexed by an integer itself. Okay, this concept of using an integer to represent a set is known as bit masking, and using such kind of techniques to basically optimize your dynamic programming solution is known as dp with bit masking. Okay, so this is a dp plus bit mask problem. So guys, hopefully the recurrence was clear to you, and the way we'll be using an integer to represent an entire set, that is also clear to you. I'll just discuss a base case and then we'll move forward to the implementation. Okay, let's say that yeah, what we can say is that we are available with no man and no woman. Then what are the number of ways to make valid pairs? There's just one way, don't do anything. Okay, so if dp of n plus 1 meaning that all the men from n plus 1 to n, which makes no sense, so this means an empty set of men and an empty set of women are available to me, and an empty set of women are available to me, then the number of ways to make pairs is to do nothing, that is one way. Okay, but if x was not 0, basically if there was any woman left to pair, then if there is still any woman left to pair, then that woman cannot be added to any pair because there is no man available. Then dp of n plus 1 x will be 0, and what I could say is dp of n plus 1 comma x is 1. If x is 0, that means there is no more woman to pair, and if there is still any woman is available to pair, but since no man is available, this woman cannot belong to any valid pair, then dp of n plus 1 comma x will be 0. So guys, now we have a recurrence, we have a base case. I'll move towards the implementation, and if you have still any doubt, it will be cleared while implementing. So again guys, I have here written some code, some basic code to take input, and made a function, declared the dp array. Yeah, so initially I've taken the input n, the number of men and women available, and the number of pairs that I have to make. Then I've taken the compatibility matrix. So again, I've taken the input here, the compatibility matrix, then I've called the solve function. It will be implemented top down by me, and here I'm passing the compatibility matrix to check if the ith man is compatible with the jth woman or not. I represents the number of basically the I have the I men I to n available to me to pair, and this integer woman subset will tell me which all women are still available to pair. Okay, and this dp array will be storing results, and since this dimension represents the number of men, this can go from 1 to n, and this represents the subset of women available to me, and initially all the women are available, so it will be something like 2 to the power 22. I have taken this dimension as, because there are a total of 21 women, and initially my bit mask can be at most 21 ones. So this is a value equal to 2 to the power n minus 1. Okay, so now we will be implementing the code. Alright, so guys, here firstly I'll be checking if it is that is no more men are available. So if I equals to n plus 1, I will also like to pass here the n, that is the number of men and women available to me. So I'll also be passing n. Let me just pass it here. Also you can see that here I have passed this should be 2 to the power n minus 1, representing the subset of women available. Okay, so if I equal to n plus 1, that means all men have already been paired. Then if woman subset is 0, that means no more woman is also required to be paired, then I could return a 1. Otherwise, this woman, the woman that are still left to pair, can never be paired again, and therefore this is an invalid pairing, and I return a 0. Alright, then now I am at the ith man, and I will be pairing it with the available woman if he is compatible with them. So let's say ll answer equals to 0, and then I will be looping through all the available women for the ith man. So let's say integer woman equal to 0, and woman less than capital N, maybe woman plus plus. First of all, this woman should be available to be paired. Okay, if she has already been paired, then I cannot pair her again with this man, and that will be that I'll know through this woman subset. Okay, so first of all, let's check if she's available or not. So I'll say take bool available equal to, so if she's available, then the z, if then basically this woman bit will be on. Okay, and how do I check if the woman bit is on in the woman subset? I will simply take 2 to the power woman and AND it with the woman subset, and then if both these bits were 1, then my answer will be a non-zero value, otherwise my answer will be a 0 value. Okay, so I'll take 2 to the power woman. Basically, if this is the 0th woman, then it will be 2 to the power 0, and I'll AND this with the woman subset, and if this value is a non-zero, then this woman was present in the subset, otherwise she was not. So if this value turns out to be a 0, So if this value turns out to be 0, then she is not available. Otherwise she is available. Okay. Now if she is available, what I'm going to do is I'm going to pair her with this particular man if they both are compatible, of course. So if available and compatible, how will I check the compatibility? Compatibility at the ith man and the woman number woman. Here I'll be using +1 because I have taken my compatibility matrix as a 1 based matrix, so I'll be using woman +1, whereas this is 0 based, so I'll have to add a 1 here. Okay, so if the ith woman, if this basically woman number woman is available to me and ith man and the woman are compatible, then I could make a pair of them, and then answer will be answer plus the number of ways to pair the remaining men from I+1 to n and the woman subset other than the particular woman I am currently pairing with the ith man. So answer plus solve. Of course I'll be passing compatibility matrix, then I'll be passing I+1, then I'll be passing a woman subset minus, or basically in this subset I would like the woman number bit to be off. Okay, because now she will no longer be available. So how can I turn this particular bit off? So what I could do here is to turn this particular bit off, I could XOR it with 2 to the power woman, this particular value. Okay, I'll just quickly explain how this will do the work. So woman subset is some number like this. Okay, and let's say I've paired this particular woman, then this will, then woman value here will be 0, 1, 2, 3 and 4. I will take 2 to the power 4. 2 to the power 4 is simply, right, it is all 0 bits except 1 bit, which is the 4th bit, 0, 1, 2, 3 and 4th. Okay, so what will happen is 1 XOR 0 will be 1, 0 XOR 0 will be 0, again this will be 1, this will be 1, this will be 0. So as you can see that, yeah, this will do the work, that it will turn only this 1 bit off and all the other bits are still the same. So this is what I basically needed. I wanted to turn this 1 bit off, and since this is doing my work, I'll be XORing it with 2 to the power woman and I'll be passing this subset forward. Okay, also I need to pass n. Okay, so once I get the result, I will take a modulo of it. Okay, and once I have done this for every woman, I'll return I'll return my answer while storing it. So I'll store dp of I at woman subset equal to answer, and I'll return it. Also, if I had already solved this problem before, I should have checked for it. So if dp of I at woman subset is not equal to -1, then return dp of I at woman subset. Okay, so guys, hopefully this solution should work. Let's just try out a sample input. So let's try this one. I should get the output 3. So it's taking a little bit time to run. Okay, so there's some error here, not declared in function, error n was not declared in this scope. Okay, here I'm getting integer n. This looks alright to me. I guess the small n is giving me the problem. Okay, so this has to be n, and I'll run it again. Okay, again some compilation error. So too few arguments. I've parsed compat I plus 1. I've parsed this thing. Oh, just a second. Yeah. Okay, now there is one extra brace. Right, now this should work and give me the output to be 3. Okay, so yeah, I'm familiar with this error. However, I don't know how to fix this. So I'll hope that this run and submit and check. If it does not, then we'll see what to do. This has to do something with the input output. Maybe I can just copy the complete code, refresh the page and see. So if this works, then we'll see. Alright, so it's getting a WA. I'll quickly check why. Alright guys, so here I've made a very basically a mistake that is very peculiar to the precedence of different operators. So here what's happening is that instead of calculating 2 to the power n and then minus 1, what it is doing is it is calculating 2 to the power n minus 1. Alright, and that is why we are getting a WA. Instead we should calculate 2 to the power n first and then minus 1. This is a very peculiar problem of the precedence of operators here, and if we do that correctly, then we'll get the correct answer, I guess. So I'll submit it after doing that thing. All right, so yeah, I'll be submitting it now. And I guess this is why learning the precedence of operators is also very much important lessons here. Yeah, I guess okay, so it's getting a WA again. Let me check why. All right, so I guess the problem is that I did not remove this thing. So while debugging, I had inserted this to check what's the problem, and I found out that it's calculating 2 to the power n minus 1 instead of 2 to the power n and then minus 1. So I was printing that as well. I'll simply remove that and try again. Yeah, okay. So now I'm not printing anything randomly. Okay, now let me just see if this passes, and then we can discuss the time and space complexities. Okay, so I guess this one will pass. It has not given WA yet. Now let's just discuss the space and time complexities for the problem. Here, as you can see, that the space complexity is n into 2 to the power n for the first dimension and 2 to the power n for the second dimension. Now what is the time complexity? Okay, so time complexity is also interesting here. We see that the number of states is equals to n into 2 to the power n. Now what is the time complexity? So the transition time, we'd like to find out the transition time here. Okay, the transition time here is big O of n, because I'm looking at all the n women and then checking if they are in the subset or not. So for every state, the transition time is big O of n, and my overall time complexity then becomes n squared 2 to the power n. But yeah, n is only up to 21, so I guess it's not much of a big problem. Alright, now guys, let's just see if the code passed or not. So yeah, it got an AC. So guys, thanks for watching. Hopefully the video was helpful to you, and I'll see you in the next video. Yeah, bye. Hi guys, my name is Karthik Arora, and in this video we'll be discussing the problem P, that is independent set. So this is a very nice problem, and it is based upon DP on trees. Okay, so this is a nice problem to get introduced to DP on tree concept. Okay, so what we're given is that we're given a tree with n nodes, and we would like to paint this tree using two colors that are black and white under the constraint that no two adjacent vertices can be black. Okay, so if we have a tree something like this, right, then let's say if I choose to color this vertex black, then all the other vertices can only be white, right? So the constraint is that no two adjacent vertices can be black. Alright, but two adjacent vertices can of course be white. Let's look at sample input. You can also look at the constraints. N is up to 10 to the power 5, so they are probably expecting a big O of n algorithm. Yeah, so here you can see a sample input. We would like to basically, so we would like to find the number of ways, valid ways in which we can paint the tree using only two colors, and in none of these ways two adjacent vertices may be black. So this is one way. In this way all the three vertices are white. In this way one vertex is black and these two are white. Then again this one is black and two white, and you can see all of these, and a total of 5 possibilities are there to paint the tree under the constraints. Also consider this kind of tree. So this type of tree is not valid because there are more than one or two adjacent nodes whose color is black. Okay, so two black nodes cannot be neighbors. So if you'd like, you can go through the other inputs. The crux of the problem is to find the valid ways in which we can color our tree. Okay, so let's move towards the solution. So first of all, the thing to notice here is that a tree is not a rooted tree. Okay, so let's root the tree at some arbitrary node, at any arbitrary node. Yeah, P independent set, right? So I'm saying let's root the tree at any arbitrary node. First of all, given a tree within nodes, root the tree at any of the arbitrary nodes. So let's say we choose to root the tree at node number 1. So root tree at node number 1. Okay, so now we would like our tree looks something like this. Now it's a rooted tree and it looks something like this, right? We would like to find the number of ways to paint it. So let's paint the root first. Okay, so I could paint the root either black or white, of course, because I haven't painted any other node yet. So I could choose to paint the root as either black or white. Let's say I choose to paint the root as black, then none of its children could be painted black, isn't it? Since it is black, then any of its direct child cannot be painted black because they are adjacent to it, and our constraint in the problem is that no adjacent nodes may be black. So these are definitely white. However, if I paint the root to be white, now these nodes can either be black or be white. It depends. We could paint them in any of the two colors. Alright, so let me just erase this and we'll see how we can solve this problem. So let me define dp of root or dp of some node. Or maybe before that, let's just make our intuition stronger about how to solve the problem. Yeah. So you can look at this tree. Let's say you had painted it black, then you could, the constraint here is that the root of this subtree has to be white, okay? Because this node is black, then the root of this subtree has to be white, and under this condition that the root has to be white, we can find the number of ways for this particular portion, right? The number of ways to paint this particular tree independent of this tree, given that the root of this portion has to be white. And again, since this is black, I can find out the number of ways to paint this tree independent of the remaining tree, given that the root of this subtree has to be white. Same for this. And once I found out all these ways, I could multiply them, and overall this will be the number of ways to paint the tree given that the root of the tree is black. Okay. The other way for the root is that if we paint it to be white, then we are left with this subtree and there is no constraint on the root. This root of this subtree may be white, may be black, it could be anything. So it's the same problem again, except on a smaller tree, right? Same way for this and this. And overall we could simply multiply these possibilities, and that will be the total number of ways. So let's move to the solution now. So guys, as you saw, a node might be under the constraint. So let's say if you wanted to find the answer for a subtree rooted at some node u, so u might be under the constraint that it has to be black, or it might be under no constraint. In that case, it might either be black or white. So we want to find the ways to paint the tree that is rooted at node u. Okay. So let's define dp of u. But we also have to model the idea that u might be under a constraint. Okay. So the constraint may be that it has to be white, given that the parent of node u, if it was painted black here, then u has to be white. Okay. So let's take a boolean to represent this constraint, and let's say dp of maybe u comma 0, and this might mean that okay, u is under no constraint, and the other thing is dp of u comma 1, and if this is 1, then this means that the parent of u was painted black, so u has to be painted white. Okay. So if we were able to find out dp of u0 and dp of u1, then our final answer will simply be dp of root comma 1. Okay guys, just a small correction here. We have to find out dp of root comma 0. 0 means no constraint and 1 means there is constraint. So let's just say this dimension represents if there is a constraint or not, and since there is no constraint on the root, so we have to find out dp of root comma 0. I'll now quickly write what dp of u0 and u1 mean. So dp of u comma 0 is simply the number of ways to paint the subtree rooted at node number u, given that u is under no constraint. That means u may either be black or white. So ways to paint subtree rooted at node u, and u is under no constraint, given u may be painted black or white. U may be black or white, any of these colors. And then dp of u comma 1 can be defined as the number of ways to paint the subtree rooted at node u so that u is under a constraint. So that means u has to be black. Oh sorry, has to be white, because its parent is black, that is why it is under a constraint. So dp of u comma 1 means that u has to be white. And finally we would like to find out dp of root comma 0, the number of ways to paint the subtree rooted at the node root, that is the complete tree, given that we are allowed to paint the root in either black or white. Alright guys, so now I'll be erasing this and we'll see how we can write transitions for these recurrence. Basically how we can prepare a recurrence to find dp of u0 and u1. Okay, so dp of First of all, let's find write a recurrence for u0. Okay, so dp of u comma 0. Now I'm painting my node number u as, given that it is not under any constraint, let's say I paint it to be black. Okay, then in that case, my the children of this basically node are under a constraint. Since this is black, they have to be white. So if I knew the number of ways to paint these subtrees, given that their roots have to be white, then I could multiply these with each number of ways for these subtrees and get the overall number of ways for this complete subtree rooted at node u. Okay, so simply, since I've painted this node u to be black, in that case all the children nodes have to be painted white, so they are under constraint. So dpu1 and product over all these, where c is a child of u. So product over dp of c comma 1, c is a child of u, plus in the other way I could have painted dp or basically the node number u to be white, and in that case the children node of this particular node u are not under any constraint. They may be black, they may be white, it's up to them. So we'll be taking the product of the ways to paint these subtrees rooted at some of the children of node u, given that they are under no constraint. Okay, since I've painted this white, they are not under any constraint. So pi ways to paint these children subtrees, given that they are under no constraint, that is signified by a 0, 0 meaning no constraint, product over all children of u. Again, so we have found dp of u comma 0, and dp of u comma 1 is that u has to be black, which is this particular possibility. So dp of u comma 1 is simply pi of dp just a second, I'm sorry. So basically it's not that possibility, basically not this one. I'll tell you what's happening here. So dp of u comma 1 means that node u is under a constraint, so I have to paint this node to be white. Alright, now since this node is being painted white, none of its children will be under any constraint. They may be black or white. Since we are allowed to have two white adjacent nodes, so dp of u comma 1 means that u was under constraint, but none of its children is going to be under constraint. So for them we will be taking dp of c comma 0, and c is a child of u. Alright, so once we have these two recurrences, all we need is a base case, and then we'll be getting our answer at dp of root comma 0. Okay, since root is under no constraint. So let's think of some base case. So if the node is a leaf node, the number of ways to paint it if it is under no constraint is 2, because I could either paint it black or white. And if it is under a constraint, then there is just one way, because I have to paint it white. Alright, so we have discussed the base case also. Now we can move towards the implementation. I'll write the base case once here. So dp of some leaf, leaf meaning that there is no child to this node and it is under no constraint. Then there are two ways, paint it either black or white. Again, dp of leaf comma 1. Now this node is under a constraint, so I have to paint it white because most likely its parent would have been black. So this is one. Now let's move towards the implementation. Yeah, so here I've taken the input and okay. So here this vector in tree is basically used to store my tree, and tree at I represents the nodes which are adjacent to the ith node, okay, basically which have a edge with the ith node. And here this is dp table to store my results, solve function. Again I've taken the input And finally we'll be printing, we are assuming the root to be node number 1. We could have assumed the node to be any node, but let's take it to be the node number 1, and we'll be printing the answer that node number 1, it is under no constraint. The subtree rooted at node number 1 and it is under no constraint, and I'll explain what this -1 means here. So because when we are trying to find the answer for a particular node rooted at SRC, or let's just make it U again, we don't have to bother about the remaining tree, okay? But in our representation of the tree, the parent of U is also adjacent to U, and we might assume it to be a child. So what we'll do is we'll pass the parent the node number of the parent to this node U, so that we don't mistakenly assume that that is also a child of U, okay? That is simply there to represent who is the parent of node number U. Since root of the tree has no parent, so I have taken a value that represents, okay, basically a garbage value, -1, since there is no node numbered -1. Okay, so now what we'll do is we'll simply implement our recurrence. This color represents, or let's write constraint. So constraint will be 1 if this node is under a constraint and we are only allowed to paint it white. Otherwise it will be 0 and we may paint it black or white. Alright, so now I'll be implementing it. So let's just take the answer to be 0 first of all, and let's assume that I'm painting this node white. So even if the node is under constraint or not, it does not matter, I can always paint it white, okay? So let's say I paint it white. So for every child of this node, I may paint any of it to be black or white. So for every child of this node, given that child is not parent, since tree at SRC only represents the neighboring nodes of this U, so it also has the parent, okay? But of course we would not like to go back to the parent, we are considering only the children. So child is not equal to the parent. Then what we'll do is we'll get the answer for this child, and just a second, LLW1. So for every child is not equal to parent, ways 1 equal to ways 1 into W1 represents the number of ways when I am painting this node white, and since it is painted white, none of the children is under any constraint after this. So solve child comma no constraint comma the parent is U itself, okay, and I will mod it with 10 to the power 9 plus 7, okay? So if the child was not equal to parent, I called this, and this was a recurrence, right? Again, I could also paint this node black if it is not under any constraint. So if no constraint, here my answer becomes answer plus equal to W1, and if there is no constraint, then what? Then I could also have painted this node to be black, so the recurrence will be very much similar. Just a second. So when I'm painting it black, let's take it LLW2 equals 1, and again the same recurrence. So since this is painted black, the children are under a constraint and they cannot be black, and we'll calculate at W2. So once we have calculated W2, I'll simply add it to the overall answer, and answer equal to answer plus W2, and I'll mod it with 10 to the power 9 plus 7. Okay, so once we're done with this, I'll simply return the answer. I should also store it somewhere, so dp at u equals to answer. Also, if I had already calculated it, I should have returned here only. So if dp of u was not equal to maybe -1, then return dp at u. Alright, so guys, hopefully the code is clear. Let's try if it works or not. Let's take this example. Answer should be 157. And there's some error, I guess. So I also between pointer and, oh, I'm sorry. So I have to compare dpu constraint, of course, because yeah. Just a second again. This is line number 19. Yeah. So yeah, we're getting the right answer. I'll submit and we'll discuss the times and space complexities. Okay, so this solve function is nothing but a DFS, since it's also storing the results at every point once it's calculated. So whenever a node is recalled or called again, the result is already stored at u constraint and it is returned. So overall the number of states here is 10 to the power 5 or big O of n, and the transition time is the number of children a node has. And on average, when you will have, basically when you will add up all the children a node has, the transition time, the average transition time becomes big O of 1, and your time complexity becomes big O of n. Alright, so here we are getting an AC. So guys, I hope the video was helpful to you, and I'll see you in the next video. Thanks for watching. Hi guys, my name is Karthik Arora, and in this video we'll be solving the problem Q flowers. Okay, so you can go through the problem statement once. Alright, so we are given with n flowers arranged in a row, and each flower has a height. Each flower has some height and some beauty. Okay, and we are given these flowers in a row, and we are given the heights and beauties of these flowers. What we would like to do is, we would like to pull out some of these flowers or pluck some of these flowers, such that the remaining flowers, okay, the remaining flowers, their heights should be in increasing order. So if hi1, hi2 and some hik, these are the remaining flowers after plucking some number of flowers, these heights should be in increasing order, and the sum of the beauties of the remaining flowers should be maximized. Okay, so that's what we would like to do. We would like to pluck some of the flowers so that the beauty of the remaining flowers is maximum and their heights are arranged in increasing order. Alright, so we'll go through a sample input now. Also, you can see the constraints here. It's up to 10 to the power 5. So I think the solution should be of n log n or n. It should be big O of n log n or n in time complexity. Right, so guys, you can go through the first input. We are given with 4 flowers, their heights are 3, 1, 4, 2, and what we can do is we can remove the flower. Let's say I remove 3 and 4, I am left with 1, 2. This is monotonically increasing and here beauty is 60, or I could be left with 3, 4. This is also monotonically increasing. However, here beauty of this flower is 10, and for this it is 30, so it is 30 plus 10 equal to 40. So we would like to keep the flowers, flower number 1 and the the flowers with the height 1 and 2. Yeah, we'd like to keep those flowers and therefore pluck these two. So hopefully the problem is now clear to you, and you can go through the sample input too if you'd like. Let me check. So it's a straightforward sample. There is just one flower and we pluck no flower. The beauty is of that flower is 10 and that is our output. Again, this is to show that we have to use longs. Sample input 4 is a little bit of longer input. So guys, hopefully the problem is clear, and now we'll move towards the solution. Right, we're solving Q flowers. Right, now what we would like to do is basically, out of the flowers from F1 to Fn, we are plucking some of the flowers, and the remaining flowers, their beauties should be maximized and their heights should be in monotonically increasing order. All right, so that's okay, but we can also rephrase the same problem. We would like to find a monotonically increasing subsequence of these flowers such that the sum of the elements of that subsequence is maximized. So this problem can be rephrased as finding a subsequence which is monotonically increasing, or I'll just write increasing, find a subsequence which is increasing, so that basic point is that the elements in that subsequence should be increasing, which is increasing, and the sum is maximum. Sum of elements of the subsequence is maximum. We don't really want to find the subsequence, we are only interested in the sum, the maximum sum. Okay, so we have rephrased this problem and now we'll try to solve this. Alright, so now I'll be erasing this. Okay, now let's try to think of a solution. Okay, so whenever you are trying to solve a problem that involves the subsequences or subarrays, you should always think of it in this manner. What if I'm able to find out the best or the required possible subsequence which ends at the ith element? So subsequence or subarray ending at the ith element. Okay, ending at ith element. So we'll do the same thing. Okay, this is a general trick. Whenever you are trying to solve for subsequences or subarrays, try to think what is the best possible subsequence which ends at the ith element. So in our case, we'll try to think what subsequence ends at the ith element and is monotonically increasing and has the maximum possible sum. Okay, all right, so let's say dp of I is the best possible subsequence, or the subsequence, the sum of the subsequence ending at the ith element and whose sum is maximum. Okay, so among all the subsequences that end at the ith element, and of course all these subsequences should also be monotonically increasing, the subsequence which has the maximum sum, it is represented by dp of I. So it is the sum of the maximum best possible subsequence that ends at the ith index. Okay, so if we were able to calculate dp of I for all possible I, that is from 1 to n, we would also be able to find out what is the answer to a problem, and that will simply be maximum out of all the dp of 1, 2, 3, because our answer is also a subsequence and it ends at some of the at the ith index. Okay, it could end at the first, second, or maybe the nth index. So our answer is going to be max of dpi for all I. Okay, So guys, hopefully the intuition is clear to you. Now we'll see how we can build a recurrence for dp of I. So first of all, let's see what dp of 1 is. So the best possible subsequence that ends at the first element. Okay, so it is obviously the first element itself, because there is no other element before the first element. So dp of 1 will simply be the beauty of the first flower. So let's call it bt by 1. Okay, now let's think of dp of I. This is the base case, and now we'll try to build a recurrence for the general case. So when I'm thinking about the ith index, okay, so there's a flower at the ith index. It has some height hi and some beauty pi. Okay, and since the subsequence ends at the ith element, so of course the ith element is definitely included, and this subsequence could extend any subsequence that ends at any index j and j is less than I. Okay, so if there were some subsequences ending at I minus 1, I minus 2 and I minus 3, then the subsequence which ends here is basically any subsequence that can be extended from here. Okay, or it could simply be these only element I. Okay, so there are two options. Either it could be only the ith element itself, or the ith element and some subsequence which ended before the ith index. Okay, so hopefully the idea is clear to you. And of course, since we want it to be monotonically increasing, then if we are thinking of extending some previous subsequence which ended at some index j less than I, then of course h of j should be less than h of I. Alright, only then can we think of extending that subsequence. Otherwise our subsequence will be invalid, because it will not be monotonically increasing in the heights of the flowers. So what we would like to do is, we will either take dp of I to be equal to the beauty of the ith element, or we will take it to be the beauty of the ith element plus the best possible subsequence which ended at some jth index and hj was less than hi, and we'll choose the best possible option. Okay, so let's say you had 5 possible subsequences where hj is less than hi. So of course you'll be choosing the maximum out of these and extending it to the ith element, and that will be the best possible subsequence which ends at the ith index. Alright, so now I'll be writing a recurrence for this. So what we do is dp of I equals to, it is out of the either of the two options. Okay, so it's either beauty of the ith element, or it is beauty of the ith element plus extend some previously ended subsequence. Okay, so if I'm extending the jth element or the subsequence ending at the jth element, of course I'd like to extend the highest some subsequence which ended at the jth element. So we will take dp of j for all j less than I and height j less than height I. Only then can we extend it. So first option, second option, this is max over all j, max over all j, and once this second point is calculated, then we'll compare 1 and 2, and dp of I becomes max of 1 and 2. So guys, hopefully the recurrence is clear to you and we have a base case. However, now let's think what the time complexity for the solution is. Okay, so for every ith index, the ith dp of I, the state dp of I depends upon previous I minus 1 states, right? So the first state depends upon one state, the second depends upon 2, and so on till the nth state it depends upon n minus 1 states, right? And the time complexity is going to be big of n squared. Of course, this is not a good solution because this will time out, given that n is up to 2 into 10 to the power 5. So we have to think of a way to implement or evaluate dp of I in a faster way, maybe n log n or big O of n. Okay, all right. So before we actually discuss the optimization that can help us make this solution faster, I'd like to give you some intuition towards it, and then we'll see how it helps. Okay, so let's say that there is some index I, and here we have the best subsequence ending dp of I, and the height here is hi. Okay, now consider some index j, so that j is less than I, right? And dp of j is also less than dp of I. However, h of j is greater than h of I. Okay, consider some possibility like this, where we have two indices and j is less than I, and again dp of j is also less than dp of I, but the height of the jth flower is greater than the height of the ith flower. Okay, so this could be something like, let's say first flower has height 10 and beauty maybe 1, then next flower has height 1, then 2, then 3. Here beauty can be 2, 1, 1. Okay, so here dp of 1 will be simply 10, here dp will be 1. Oh sorry, yeah, dp of 1 will be 1 because the beauty here of the flower here is 1. Here it will be 1, here it can be, sorry, it will be 2 because the beauty here is 2, and here it can be 1 plus 2. So the point here is, if there exist any two such indices, then there is no point of for any index that is greater than I, it is basically, it does not make sense for any index greater than I to extend the answer of the jth index. Okay, so hopefully you're getting the point that it does not make any sense to extend this particular index. So after the ith index, jth index will never be extended by anyone, because if the jth index can be extended, then of course the index we are currently at, the height of that flower is greater than hj, then of course it is greater than hi as well. And since the ith index can be extended, we are getting a better answer at dp of I instead of dp of j. So after reaching the ith element and having dp of I, the jth index or the answer of the jth value becomes useless, and it will never be used for extending any other subsequence. Okay, so basically no other subsequence will use this particular index to ever to extend it. Okay, since there is a better option in the form of the ith subsequence. So let's see how we can use this to faster up the overall algorithm. All right, so now we know that this kind of indices are useless, basically the jth index. So what we can do is we can maintain some kind of valid indices that can be extended or will ever be extended in the future, and we can remove this guy. Once ith enters it, we can remove the jth guy, and now our valid people reduces. Okay, the people who have to be checked reduces. However, this will still be big O of n even if we keep removing some of the indices. So let us try to maybe have a set in which only valid indices appear. Okay, so if there was any invalid indice, like where j is less than I, or in fact, yeah, okay, first of all, like j is less than I and dp of I, j is less than dp of I, but the height of the jth flower is greater than the height of the ith flower. So let's try to maintain such a data structure in which this kind of senseless basically useless indices can be avoided and not kept for further extend, basically to check further on. Okay, so this kind of structure in which I only keep the good indices, or basically the indices which have any future chance of being extended, one property will be followed. If I maintain such a structure in which only meaningful indices are present, meaningful indices in the sense that these indices have a chance of being extended in the future, then such a data structure will have the following kind of property. So if there is some index I1 present in the data structure and I2 present in the data structure, then if height of I1 is less than height of I2, then dp of I1 is also less than dp of I2. Okay, so if I'm able to maintain such a data structure which only has the meaningful indices, then I can be assured of the property that the height of any of these index, if basically I could choose any two indices from this data structure, then if the heights are in this order, hi1 less than hi2, then definitely dp of I1 is less than dp of I2. Otherwise, one of these indices would have been deleted from this data structure. I'll show it to you how it would have been deleted. Okay, so like let's just say if there was some dp of some index present, basically some index 2 present here, okay, in this data structure, and a new index comes, that is, let's say 3. However, dp of 3 is greater than dp of 2. Let's say it is greater than dp of 2. However, the height of the third flower is less than the height of the second flower. So what I'm going to do is I'm going to delete 2 and insert 3, because 2 becomes meaningless now. Okay, and this is one case. The other case possibility is, let's say that a flower of a larger height comes. Now in that case, do I need to delete anything? No, I do not need to delete anything. If a new flower comes and whose height is greater than all the flowers, then its dp will also be greater than all the flowers, since it could extend any of the previous guys, and the answer becomes the dp of j that it is extending plus the beauty of current flower, which is at least 1. Okay, so any data structure, I'm going to maintain such a structure in which if two indices are present, I1 and I2, and if hi1 is less than hi2, then dp of I1 is also less than dp of I2. Okay, now what advantage do I get by maintaining this kind of structure? So basically, the advantage that I'm getting is, if at some point I'm trying to evaluate dp at k, okay, and my meaningful indices set says there are some indices I1, I2, I3 up to ij in my set, okay, then dp of k will extend some index such that height at that index hi some index, it is extending some index j, ij, such that height at that index hij is less than height at k. Okay, and here is the interesting part. It will extend that particular guy which has the highest height less than k. Okay, I'll prove it again. So we had the kth guy. This is thinking about the meaningful indices it currently has that can be extended. It will pick that index to extend such that the height at that index is greatest, the largest possible, but less than h at k. Okay, because it could not extend any guy which has height more than this guy, and if it extends some guy which has some lesser height, then the dp of that will also be smaller, and it will end up extending a smaller value instead. So here is the point, that it will extend the largest possible height less than equal to hk. Now how does this help to faster up the algorithm? This kind of thing, finding the largest person less than equal to h of k, can easily be done in big O of log n using binary search kind of thing. Okay, and the deletion part. Okay, so once some guy enters such that dp of this guy entering, so that let's say some j ith index is entering, and dp of I, the value here is the best subsequence ending at the ith element is dp of I, and height is hi, and there exists some previous index where height is greater but dp is smaller, then we're gonna delete those. Okay, so what I do is I insert this thing into my data structure, and now check the value greater than hi, the smallest value greater than hi, if let's say it's some hi plus 1, or maybe some index basically, where this was my set, something like this, hi1 corresponding dpi1, then hi2 corresponding dpi2, and so on. This was something like my set. Okay, and this particular guy I entered here hi dpi, and the values greater here. This is my data structure that I'm going to maintain, and let's say the value here some hi maybe k, let's say x, and here dp of ix, and so on. Okay, so I'll simply check if of course hi is less than hix. Definitely I've inserted into the correct place where, so that these heights are in ascending order. My data structure maintains these heights in the ascending order, and by default these dp of these should also be in ascending order. Okay, now after inserting this condition might violate. Okay, so if dp of I is greater than dp of ix, then there is no more need of keeping this into my data structure. Okay, so I'll be deleting this guy. Again, after deleting this guy, I'll check if the guy just right to this is needs to be deleted. If it needs to be deleted, I'll delete it again. Okay, till this kind of property is maintained once again, so that yeah, so till this property is maintained again, that dp of I is less than the just greater height guy. Okay, so this is what my data structure is going to maintain, and then we can query in big O of login to find out the largest height greater than the height of the current flower and extend that particular guy. Since these dp of i's are also in ascending order, we will obviously pick the largest height. So this is the benefit of keeping this data structure, and now we'll be able to solve this in big O of n log n. If you have any doubt till here, it will most probably be cleared once you start implementing it. So pay focus to it. Okay, so now I'll move towards the implementation. Okay, so as always I have taken the input and made a solve function. Here this is a structure to model the flowers. Hi is the height of the flower, bty is the beauty. Solve will be called with the array of flowers and the total number of flowers n. Again, here I have taken the input of the heights and the beauties, and solve is being called. We'll simply be implementing as discussed. Okay, so let's have vector dp. Yeah, so let's have a vector long dp. This represents the best possible subsequence ending at the ith element, and let's keep the size to be n plus 1. Alright, now what we can do is dp of 1 is simply the beauty of the first flower as we discussed. So v at 1 dot bty. Alright, so this is alright. Now this is a meaningful index that can be extended. So let me keep a map. Okay, we'll keep a map from int comma int, and here this mapping is from height to the answer at that particular height flower. Okay, so once I've got dp of 1, okay, so meaningful indices. Okay, so what I'm going to do is in my map meaningful at the height of this guy, that is v1 at hi, becomes equal to dp of 1. Okay, so till now it must be clear. Now what I'm going to do is to calculate at a particular dp of I, I'm going to use this meaningful indices map. So for integer I from 2 to n, Now this guy has to extend some previous guy, and if it's unable to extend, of course it will be same as what the beauty is here. So let's first assume that it is unable to extend, then dp of I becomes v of I dot bty. Okay, now if it is able to extend, then v of I dot bty plus the best possible thing it can extend. Since the meaningful indices are in a sorted manner, so I would like to extend the largest height from that map, largest possible height. Okay, so the largest height less than equal to vi dot hi. Okay, the ith flower has the height vi dot hi. Extend the largest height in the meaningful map, because the larger is the height in this map, the greater is the value corresponding to that height. And I want the largest thing to extend, but I also want that the monotonic condition is maintained. So what I'm going to do is I'm going to take the lower bound here. So meaningful dot lower bound. What lower bound does is it returns me an iterator to the smallest value in the map, which is greater than equal to the height of this guy. Okay, but of course it has returned me a height which is greater than equal to hi. Okay, so if it is equal to, then there is no problem, but if it is greater than, then there is a problem. So what I'm going to do is, first of all, I'm going to extend +1. Okay, now it is definitely greater than the height of this guy, so I'm getting an iterator which is definitely pointing to an element greater than this guy's height. I'm gonna basically decrease this pointer. Now I am at an index which is basically less than equal to vihi. Okay, now I'm going to use the answer at the iterator. However, it was possible that iterator was pointing to the beginning of the map. So if iterator was pointing to the beginning of the map, then there is no guy till now which could have been extended by the ith flower. This simply means that till now this is the smallest height we have seen. So if this was the case, then simply ignore this, or let's say if this is not the case. So if it is not equal to the beginning, then there is some guy which has a height less than ith flower's height, and we reach to the flower. We use the answer at it second, and my dpi becomes it second. Okay, and now I'm gonna insert this value, or I'll insert it here. So insert it into the meaningful map. Meaningful at this guy's height, which is vi dot hi, becomes equal to dp of I. And now if there is any guy which has a height greater than this, but dp value smaller, I'm going to delete it. Okay, so let's do this. Auto it equals to meaningful dot upper bound. Upper bound returns me an iterator to some value which is greater than this guy's the value I'm passing it. Not equal to, greater than. Okay, so now I have my iterator pointing to the value just greater than this guy's height. So while it at second is less than this guy's answer, and in fact even equal to, then I'm gonna delete this. What I do is meaningful dot erase iterator. Alright, there are a few things to keep track of here. First of all, once I delete it, I have to go to the next element also. So before deleting it, I keep an auto temp equals to it, and before deleting I go to the next guy, since it might get deleted again. And now after deleting, it becomes equal to temporary, I've come to the next guy in this sequence. Okay, and there is also one more possibility that all the guys after it get deleted and we reach the end of the map, so it is not equal to meaningful.end. Alright, so guys, hopefully this is clear. This is simply inserting the particular element's answer into the sequence in a correct order, and then if the next guy in the order has of course it has a height greater than this guy's height, but it could have the answer less than the answer at this height, then I'm going to delete it, because I have to maintain my structure in the correct order. If the height is less, then the answer is also less. Okay, this is simply doing that thing. So once we are done with this, my answer will be maximum out of dp of 1 to n. Okay, I could even keep track of it with a single variable. Let's say answer equal to 0. So answer equals to max of answer comma dp at I, and here I could initialize answer as dp of 1. Once I'm done with this, I'll return the answer. Alright, so now we can check a sample input. Let's try sample input 4. So this was a tricky problem, and hopefully you were able to understand it. Okay, so 20, yeah, we should get the output 31. Alright, we're getting the correct output. I'll try and submit. Okay, so this should most likely work, and then we'll discuss the time and space complexities. Alright, there is some problem here. Let me check. Alright, so what I'm guessing is this might be because of this thing, and this has to be long. Okay, since my values could be very large, so I'll just try it once again by keeping it long, and rest I'll keep the same for now. This might work. And although hi and bty can be integer, but let me just make them long as well, although they can definitely be integers. Alright, so I guess this time it will work. Yeah. So guys, this time the time complexity here is n log n, and space is big O of n. As we discussed, this map thing here, these functions lower bound and upper bound work in big O of n, big O of log n, and this loop runs n times. Here this thing deletion, see, the point is any element can be added and deleted. So for any element we can do at most 2 operations, add and delete, and addition is log n and deletion is log n. So overall, even if we do both the operations for every element, add it and delete it, overall it is going to be 2 times n log n. So this loop here does not cause any problems with the complexity. And so guys, I hope the solution was very much clear to you, and I'll see you in the next video. Thanks for watching. Also, you can see that we've got the AC, and thanks for watching guys. Bye.